Hello and welcome. My name is John Horvath. This presentation is about deep foundation design and the changes that I feel need to be made in the way that we go about doing this. This is the 15th narrated PowerPoint presentation that I've done for my YouTube channel that I established back in 2020. And this presentation is by far the longest that I've done. Now, when I set out to start this presentation a year or so ago, I didn't intend for it to be the longest or the length it turned out to be. But I've been a professional civil engineer for over 53 years now. And I've been involved in both design practice as well as academic instruction and research. And I have been involved with deep foundations since literally the first days of my professional career in June 1972. I've remained active in both design practice and research with deep foundations throughout my entire career. For example, I'm a charter individual member of the Deep Foundations Institute, which, as I'm sure most of you know, is now an international organization, a professional and technical organization devoted to all forms of deep foundations. So in order to meet YouTube's video length requirements, I've had to divide this presentation into two parts, and as you can see, this is part one. I feel that it is essential that you view part one in its entirety before moving on to part two, because all of the specific technical subjects I talk about in part two, all of the background and groundwork for those that discussion is contained here in the part one of this presentation. This anonymous quote, which has been incorrectly attributed to Samuel Clemens, who wrote under the pen name Mark Twain, applies to deep foundation design practice in many ways. Humans have been installing deep foundations to support structures for at least 7,000 years. And it's just human nature that when something has been done for a long time, it tends to lead to a certain complacency. Now, complacency is not bad per se. However, it can stifle creative thinking. It can stifle being receptive to new ideas or looking at old ideas in a different way. And I think that's very true of the current state of practice of deep foundation design. Because of the length of this presentation and the volume of material that I'm going to cover, I've broken up this presentation into modules that you see listed here. I think you'll find it convenient to space out your time and view this presentation module by module as you have available time and interest. Part one of this presentation will cover the 5 modules that you see highlighted here. Basically, what is covered in this part one is to give you some background information as to why I decided to make this presentation, why I feel that change is necessary in design practice for deep foundation elements subjected to axial loading. I will provide some background information as to how we got to where we are and the way that we design deep foundation elements for axial loads. Then move on to an overview of what I will be covering in the remainder of this presentation. And I will conclude this part one by discussing what I call a change in thinking phase one. And this is basically a discussion of doing better at what we're doing now before moving on to doing something different. So let's begin with a prologue to explain how this presentation came to be, why I decided to make it. This quote from Professor Benk-Felinius, I think, concisely explains the root cause, what hobbles and retards many efforts to advance the state of practice in civil engineering. And this is often very frustrating to those who are championing these advancements. I'll give you a minute to read the quote for yourself. Unfortunately, memes have long been a part of geotechnical engineering and related structural engineering for foundations and earth retaining structures. And I refer to geotechnical and these aspects of structural engineering together as what I call geostructural engineering. I'll use that term. I've used it in past presentations and publications, and I will use it in this presentation. So these memes in geostructural engineering have been perpetuated by a combination of groupthink that permeates textbooks as well as standards and codes. Now, I've spent a good part of my professional career in academia, both part-time and full-time, and I've had many textbook publishers approach me over the years saying, gee, write an undergraduate textbook on soil mechanics or foundation engineering, whatever. And when I've discussed this with them, it turns out they really didn't want anything new. They just wanted a book that was just like every other book that already existed on the market, but just, maybe had some new graphics, a more modern looking cover, fresh face on old ideas, as I call it. I've also been on committees that develop standards and codes, and these committees tend to pride themselves on being consensus committees, and they go around telling the public, well, this is a consensus committee, we all vote, this is a democracy in action. But the reality is, when you belong to these committees, is that it takes a lot of time, it takes a lot of money. You've got to travel to places for committee meetings, take time away from making a living to go to these meetings, participate in these meetings, prepare for these meetings. And the bottom line is that it turns out that the people who tend to be on these committees are people who basically their participation is bankrolled by their employer. And their employer tends to be an organization, or more times a private business, that has an agenda. In other words, the committee is developing some code that is going to apply to their product. So it's in the interest of these organizations or corporations to basically fund their employees to go and participate and basically get their way. And that's what happens in my experience. So as a result of all these things, memes tend to have an outsized influence on both the design state of practice as well as all aspects of academia, both instruction and research in geostructural engineering. A very notable, significant example of a meme that I'm very familiar with that dominates geostructural engineering design practice as well as academic instruction and research is the chronic near universal misunderstanding of the concept of subgrade reaction, and in particular the Winkler hypothesis subgrade model. This has led to the widely held belief that the Winkler coefficient of subgrade reaction, which I'm sure most of you have heard called the soil spring constant or the K value or some similar term, the belief that this is a fundamental soil property, and I can guarantee you it is not. This fallacy that the Winkler coefficient of subgrade reaction is a fundamental soil property has resulted in decades of wasted resources, and I'm talking about research time and money, looking for a concept that really is the unicorn of mythology. It doesn't exist. And I can say this with some certainty, as I've spent most of my professional career looking at the subject. I wrote my doctoral dissertation on the subject in 1979. More recently, a scholarly monograph and a couple of YouTube presentations summarizing that monograph that explain why there is no such thing as the soil spring constant. Well, the subject of this presentation is another notable significant meme in geostructural engineering that I have considerable experience with, literally going back to the first days of my professional career, which began in June of 1972. And that is the analysis and design of deep foundation elements for axial loading. Historically and to the present, the primary consideration for this very, very common, globally common application of foundation engineering has been the geotechnical ultimate failure, which is formally known as the geotechnical ultimate limit state, or ULS. I'm going to be using the ULS abbreviation throughout this presentation. So it's the ULS between a deep foundation element and surrounding ground, and their secondary consideration of the structural ultimate limit state of the material that comprises the deep foundation element shaft. Now, as I will show you, if you're not already aware, this meme of how we design deep foundation elements for axial loading reflects foundationeering practice that evolved in the early decades of the 19th century, which was long before the concepts of modern soil mechanics were developed in the 1920s and 1930s. This geotechnical ULS-based state of practice for deep foundation elements subjected to axial loading has become even more ingrained in design practice as well as academic research in recent decades due to the migration from allowable stress design, or also called working stress design, to load and resistance factor design, LRFD, and is also called ultimate strength design. And LRFD, by definition, focuses on the ultimate strength of a material. Now, as an aside, in my opinion, LRFD is ill-suited for use with particular materials such as soil, because soil inherently and simultaneously both produces load and provides load resistance. But this has not deterred those who are LRFD fans from promulgating codes and standards that embrace LRFD and basically have forced its use in practice. As you might sense, I'm not a fan of LRFD. I don't think it's really meant to be used with soils, but a discussion of whether LRFD is relevant or not in geotechnical and geostructural engineering is beyond the scope of this presentation. However, I do address it extensively in a monograph that I wrote back in 2023, as well as a YouTube presentation I have posted on geostructural forensics. So the thesis of this presentation is that the meme that the geotechnical ultimate limit state is the most important aspect of the behavior of deep foundation elements subjected to axial loading is deeply flawed, and is deeply flawed for a number of significant reasons and thus needs to change. Specifically, this change needs to be to design deep foundation elements for axial loading based primarily on geotechnical serviceability, which is formally known as the Serviceability Limit State, SLS. And in this case, serviceability is defined by the axial displacement of the deep foundation element, and by extension, the vertical displacement of the structure that is supported by the deep foundation element. It's important to note that it's not a new concept and not one that I hold alone. This idea that we should be designing based on serviceability, geotechnical serviceability, has been proposed and promulgated by numerous researchers for decades now. And Professor Flenius is by far and away the most consistent, persistent, and loudest voice in this regard. And I think this quote that has been attributed to him really states his position clearly and succinctly. Don't get stuck in the capacity singularity, rise above the pack, and let settlement issues govern your foundation design. So that, in a nutshell, is the change that I will be addressing in this presentation. Now, Fellinius' recommendations that we should be using the geotechnical SLS for deep foundation design is part of what he calls the unified piled foundation design method, although it's more commonly and widely referred to simply as the unified method, and that's the term I will be using throughout this presentation. The unified method was first presented in a paper by Fellinius in the 1980s, and it has undergone considerable evolution and quite a bit of what I call mission creep. And this is the result of computational tools changing from handheld pocket calculators to digital computers, additional field observations and measurements, and additional research. So as a result, over the last 4 decades, the unified method really has evolved into a conceptual umbrella of several geostructural assumptions, behavior, and analytical methods. So to summarize as to how this presentation came to be, why I decided to make it, geostructural design practice and academic instruction and research, which I have more than 50 years experience in both of these areas, have a long history of memeing certain technical subjects. They just, they fixate on an idea and they just don't let go of it. So this memeing has resulted in repeatedly simply refurbishing old ideas without pausing to first give zero-based critical thought if those old ideas are worth perpetuating. As I said, memes and habit are not bad per se, but every now and then you need to stop and think, wait a second, I've been doing this a long time. Should I still keep doing it this way? And sometimes you should. There are things that, why there's no reason to change the way we do things. But every now and then, when you've been doing something for a long time, you should really stop and think about what you do, why you do it, and if you need to keep on doing it or maybe do something differently. So the purpose of this presentation is to present a zero-based critical thought on the subject of deep foundation elements subjected to axial loading, and in doing so, hopefully illustrate why a lot of design professionals and academicians think what they know for sure about deep foundations just ain't so. So this is why I decided to make this presentation. Large part of the reason why it is such a lengthy presentation is that we've been doing things the same way for some 7,000 plus years, so there's a lot of history to explain, to lay the groundwork as to why we need this change. So in this next module, I would like to present some background information that sets the stage for the modules that will follow. So despite the decades-long efforts by Fellinius and others to promote deep foundation design for axial loading based primarily on the geotechnical serviceability limit state settlement as opposed to the geotechnical ultimate limit state, design codes and design manuals have remained stubbornly focused on the geotechnical-ULS as the primary, if not exclusive, metric for this foundation application. And as I said in the preceding module, the migration in recent decades to using LRFD for both the geotechnical and structural components of deep foundation element design appears to only reinforce the status quo of using the geotechnical-ULS for design that was established in the early decades of the 19th century. However, the most recent edition, 2020, this year, 2025, of Fellinius's textbook titled Basics of Foundation Design, that both Fellinius and others refer to colloquially as the Red Book, which has been available online in digital form at no cost for several years now and is updated annually, usually in January. Fellinius has noted that in recent years there has been growing recognition and acceptance in some countries, some business sectors, and some market segments of at least some aspects of the unified method that focuses on serviceability. However, this recognition and acceptance is far from global and comprehensive, so the thesis of and the need for this presentation still remains valid. There's still far too much emphasis on the geotechnical ultimate limit state in deep foundation element design. So given the entrenched nature of the status quo, that is, designing deep foundation elements for axial load based on the geotechnical ultimate limit state, it's reasonable to pose two questions. Why does the current state of practice for deep foundation elements under axial loading need to change? And perhaps more importantly, given the decades-long efforts of Fellinius and others to try to effect change, such a change is warranted, why hasn't it been done already? I can remember a magazine article several decades ago in the early years of geosynthetics, when everybody was saying, we use geosynthetics, use geosynthetics. The title of the article, and this was a magazine published in the United Kingdom, was, if geosynthetics are so bloomin' good, why isn't everybody using them? And it was a reasonable question. So this is a reasonable question. These are reasonable questions to ask here. So the answers to these questions are a complex, interrelated combination of factors that I think can best be understood by first presenting a timeline of the evolution of deep foundation element analysis and design for axial loading. I've done a tremendous amount of forensic work in geostructural engineering throughout my career, and especially in recent decades. And I have found that when you're trying to reconstruct why something fails, the best place to start is to try to create a timeline. Just put everything into a temporal sequence to see how pieces happen. And it goes a long way to helping to understand why things are the way they are, or why they happened. So we're going to do that here. And we're going to see that this timeline actually answers the second question. If change is warranted, why hasn't it been done already? It's going to answer that second question first by illustrating why deep foundation element analysis and design for axial loading based on geotechnical failure has become so firmly ingrained with all stakeholders. And this goes from academic instructors and researchers, design professionals, construction contractors, and project owners, and includes the professional and technical organizations and their committees that often play an outside role in deciding and guiding the course of technological evolution. As I said, I've been in professional practice for over 5 decades now, and I've interacted with many professional organizations, technical organizations, and their committees. I've been on those committees, been members of these organizations. And I will tell you that these committees and the things that they come up with really play an outsized role in shaping design practice. So before proceeding with this temporal or timeline presentation of how the current state of practice came to be, I'm aware that these presentations of mine do have an international audience. So I've learned that definition of terminology is really essential for clarity. In this global community that we all live in now, we all speak the same language, but very often with a different accent, if you will. And in this case, in the US and perhaps elsewhere, the term pile, when we use it alone, generally has a very implied limited definition. And I say that as someone who has lived and been based in the U.S. for their entire professional career. And this limited definition is a preformed structural element of wood, steel, Portland cement, concrete, or perhaps nowadays some other type of solid material, used either alone or in some combinations, such as steel reinforced concrete, that is installed into the ground, typically by impact driving using a pile hammer. So if someone in the U.S. says pile, it has this very narrow definition. However, in much of the world outside the U.S., the term pile has a much broader meaning, as any relatively slender, nominally cylindrical structural element that is either installed or created in the ground using any one of several construction processes. So this broader definition of pile is synonymous with the generic term deep foundation element that I introduced earlier and will use throughout this presentation. So when we use this broader definition of pile to mean pretty much any kind of deep foundation element, it's necessary to add an adjective to distinguish among the different types of piles. So driven pile, jack pile, bored pile, which in the U.S. is called a drilled shaft, etc. So to maintain clarity and avoid ambiguity for an international audience, I'm going to use this broader, more global definition of pile with an adjective so that we all understand what we're talking about. So this timeline of understanding the science behind how deep foundation element resists axial load dates back to the early decades of the 19th century, the early 1800s, when driven piles of untreated timber, which are essentially inverted trunks of trees devoid of bark, were installed by drop hammer. This was the norm as it had been for thousands of years up to that point in time. Okay, if we go back to these ancient lake settlements 7,000 years ago, these are on timber-driven piles or driven timber piles. And certainly for thousands of years, this was done simply by human labor. So note that this early 19th century time frame was roughly a century before modern soil mechanics began to emerge in the 1920s and 1930s. And as we know, modern soil mechanics provides a rational applied science framework for foundation engineering. These 19th century analytical efforts to treat driven pile installations drew on simple problems in classical physics that involved the basic concept of work as a form of energy and later on as the impact of rigid bodies. These early analytical efforts resulted in resistance forecasting methodology that we now call dynamic formulas. Many dynamic formulas, which are just algebraic expressions, have been developed over the years. If you look at Chellis's classical second edition text on deep foundations that was published in 1961, he identifies about 24 different formulas. There are even more now. But the common element of all these formulas is that each includes a term that is the ultimate geotechnical resistance, the geotechnical-ULS of the driven pile. And this ultimate resistance is produced by some combination of pile hammer, which is either ram times a drop height for a drop hammer or some equivalent energy for a mechanical hammer, and what we call the set or penetration that has units of length of the driven pile per hammer blow. So note that the only way that these calculated outcomes from dynamic formulas could be verified or calibrated in the past was by loading the installed driven pile in a static load test. And this was typically done using an assemblage of dead weights. And it was loaded until what was assumed to be the geotechnical ultimate limit state had occurred. That is, the pile penetrated several inches or tens of millimeters into the ground. Now, the reliance on dynamic formulas and the geotechnical ultimate limit state as the basis for assessing driven pile foundations persisted well into the 20th century, and even after the evolution of modern soil mechanics in the 1920s and 1930s, as evidenced in this quote from Terzagh's seminal 1943 textbook, Theoretical Soil Mechanics. And it's clear from this quote that Terzaghi viewed the behavior of deep foundation elements under axial loading as a problem in bearing capacity, that is, the geotechnical ultimate limit state. You don't see any mention or implication of settlement in this quote. So this thesis that the behavior of deep foundation elements under axial loading was best defined by the geotechnical ultimate limit state was no doubt aided by the fact that well into the 1970s, and this is true at least in the US, geotechnical engineering was not universally accepted among civil engineers, especially those in design practice in the US, as a quote-unquote legitimate field of specialization in civil engineering. And I can attest to this firsthand. Early in my professional career, when I was involved in private consulting practice on a full-time basis, working for large international consulting firms, I would interact all the time with structural engineers who were older than me, a lot more experience, and they would often be really sarcastic. Oh, geotechnical engineer, what's that, you know? And they would come right out and say it. They thought that geotechnical engineering was really a solution in search of a problem. At the time, it was thought that foundation design was simply another task that structural engineering specialists would perform. And as we know, structural engineers are used to, at least at the time, were used to reducing the ultimate strength of a material, structural material, to some allowable value as dictated by a building or design code. So understandably, you know, structural engineers used to dealing with wood and Portland cement concrete and steel would focus on the ultimate strength of material, would reduce that to some allowable strength, and that the code dictated, and that was that. So they viewed the ground as just another structural material. It's also useful to remember that well into the 1960s, at least in the United States, an undergraduate course in soil mechanics was not required at many colleges and universities. Right? If you look at the catalog from engineering schools, and in very round numbers, at least years ago, I sat down one time, this was in the 1990s, and I found that there was something just a little bit more than 200 undergraduate civil engineering programs in the United States at that time. In a lot of schools, one could get a bachelor's degree in civil engineering without having to take even an introductory course in soil mechanics, later called geotechnical engineering. So you had a lot of people, and at that time it's useful to remember that a graduate degree, a master's degree, for example, was not considered a necessity in design practice. One could go through an entire professional career with nothing more than a bachelor's degree in civil engineering. So there was a lot of people out in practice who never had a formal introduction to soil mechanics, no less foundation engineering. So despite all of these handicaps, the seeds for developing a more modern approach to foundation engineering that is based on rational application of soil mechanics principles were planted and began to grow rapidly after the Second World War, as evidenced by the fact that by the 1950s, concepts and analytical methodologies and methods for how shallow and deep foundations could be rationally analyzed and designed using soil mechanics began to emerge. So it soon became apparent in the 1950s that the behavior of shallow foundations, when used to support axial structures, was in most cases governed by settlement, the geotechnical serviceability limit state. Although bearing failure, the ultimate limit state, still was possible in some cases, so needed to be checked. But really, design was governed by settlement. Now, because construction of a shallow foundation is typically done on an undisturbed subgrade, it was quickly realized that analysis and design of shallow foundation for settlement could reliably be based on an assessment of ground stiffness prior to construction, using either lab test data from odometer test or field test data from the standard penetration test, the then novel idea of cone penetrometer, pressure meter, or perhaps some other in situ testing device. So as a result, shallow foundation research in the 1950s and thereafter really focused on developing settlement-based analytical methods that struck a balance between accuracy and ease of use in routine practice, and this effort has continued to the present. However, a different development path evolved for deep foundation elements. Although there was initial research attempts in the 1950s to forecast deep foundation settlement under working or service loads, they were empirical in nature and very, very crude. And it soon became apparent that there were some unique issues and challenges associated with deep foundations compared to shallow foundations that made the development of theoretically rigorous analytical methods for forecasting deep foundation settlement much more difficult than it was for footings. And this is the fact that when you install or construct deep foundation elements, it inherently disturbs the ground. And also the fact that we use deep foundation elements in groups or clusters. So this made development of analytical methodologies and methods for evaluating the geotechnical serviceability settlement of deep foundation elements that were reliable yet reasonably simple to use in practice, pretty much impossible given the knowledge base and the tools of the era. And we're talking about SPTN values and hand calculations using a slide rule, or a little bit later on in the 1970s, the handheld or so-called pocket calculator. So as a result, the inability to be able to forecast the adequacy of a deep foundation element prior to construction placed the burden of what constituted an acceptable deep foundation element entirely on the person inspecting the installation of deep foundation elements in the field. And that was one of the reasons that even decades ago, and certainly the New York City Building Code was typical in this regard, it required that someone inspecting the installation of deep foundation elements had to have a professional engineer's license. So this reliance on field observations really led to continued use of dynamic formulas, especially the so-called engineering news formula in the United States that required nothing more than someone in the field counting pile hammer blows for some arbitrary driven length, typically foot or inch in the US. So you count the number of blows per foot or blows per inch, you plug it into a formula, and very quickly you get an answer. The outcome of this continued use of dynamic formulas, which, by the way, it was already known as early as the 1930s that these dynamic formulas really did not correctly model the actual physics involved in the pile driving process. So it was known fairly early in the 20th century that dynamic formulas are pretty much worthless because they don't model what's going on during the installation of deep foundations. But nevertheless, there was this continued focus on the geotechnical ultimate limit state as being the primary, if not sole, metric for the design of driven piles at least. Now, this focus on the geotechnical ultimate limit state was perpetuated by many improvements that occurred in the 1960s and beyond. This was the digital computer, the miniaturization of electronic instruments, more recently development of cellular communications. So this made possible to solve the one-dimensional wave equation, which, as we know, more accurately models the physics involved with driven piles on a routine basis, and to extend wave-based technology to field measurements, and thus we can replace dynamic formulas, at least in principle. Unfortunately, the one-dimensional wave equation is also crafted around the concept of the geotechnical ultimate limit state. So this has only perpetuated the focus of deep foundation analysis design for axial load based on the geotechnical ultimate limit state or failure. And by the way, this is one of my pet peeves, to set the record straight, E.A.L. Smith in the United States did not, and I repeat, did not invent, quote unquote, the application of one-dimensional wave equation to pile driving around 1960, as often stated in published work on this topic. If you look into the history of the wave equation, the basic theoretical elements of the wave equation applied to the pile driving process were developed in the United Kingdom in around 1930 by D.V. Isaacs, and there was follow-on work by others in the UK. Unfortunately, at the time Isaacs did his work in the 1930s, the computational tools did not exist to be able to readily solve the one-dimensional wave equation. As we know, this requires a digital computer. So the concept languished until the development and proliferation of the digital computer decades later. Well, parallel with the temporal evolution of wave-based field measurements and wave-based resistance forecasting methods, such as the case method and CAPWAP that we're very familiar with these days, beginning in the 1950s, there were so-called static methods for forecasting. And by the way, I don't like the term predicting or prediction. I know that in geotechnical and geostructural engineering since forever, we say, we use the word predict. Let's predict how much settlement. Let's predict the bearing capacity. We have these prediction symposiums, for example. I think the word prediction implies a certain crystal ball. I can predict, I know the answer for certain, and here's my prediction. I like the word forecasting. I mean, forecasting, certainly as we use it in weather forecasting, for example, it says, look, I'm making an estimate based on science, but that science tells me there's a certain probability I may be wrong. And I think the word forecasting really better applies to what we do in geotechnical and geostructural engineering. So again, that's one of my personal pet peeves, why I use the term forecasting instead of prediction or predicting. Static resistance forecasting methodologies for the geotechnical ultimate limit state can be categorized in two ways. They can either be what we call indirect methodologies, also known as rational methodologies that are based on geomechanics principles, or they can be what are called direct methodologies that are purely empirical in nature, and they're based on some in situ test measurement that is calibrated against a database of measured outcomes from static load tests. These direct methodologies have become very popular in recent decades using data from cone penetrometer CPT soundings. You have some CPT results you have an empirical formula, you plug the CPT results in, and they forecast some ultimate geotechnical resistance of a deep foundation element for axial loads. Note that static resistance forecasting methodologies were and still are a useful complement to dynamic wave-based methodologies as both a comparative and verification tool, especially when we can compare the results from both against the measured outcomes from static load tests that historically and to the present, static load tests have been assumed to be the quote-unquote gold standard for providing the ground truth of the quote-unquote true value of the geotechnical ultimate limit state. Unfortunately, as I will show you later in this presentation, static load tests have their own issues and troubles. They can be reliable, they can be inaccurate. They are not the unquestionable gold standard as they are usually assumed to be. So to summarize up to this point, the assumption that the geotechnical ultimate limit state is the primary, if not sole, metric for assessing the performance of deep foundation elements subjected to axial loading has been around now for almost 2 centuries, and thus is a classic example of a civil engineering meme as Fellinius has defined it. A concept held as true, never questioned, only amended and developed within the original framework. It's what I said earlier on. It's an idea that is simply refurbished as time goes on. Now, there's no doubt that at one time the focus on the geotechnical ultimate limit state for deep foundation elements was justified, given the extreme limitations of the state of knowledge and the computational tools at the time, back in the 19th century, early 20th century. In the almost 200 years since then, that justification that first existed, there's no indication that the industry, the deep foundation industry as a whole, has ever stepped back and made a zero-based critical assessment of whether or not it still is justified. Right? What I'm talking about is, I'm not aware of any time that the deep foundation industry as a whole has stepped back and said, look, we've been doing this for some 200 years. Is this still the best way to do things? Or should we be doing something else? Rather, they just repackage these old ideas time and time again. Well, there's no doubt that the culprit of what I call intellectual inertia, supported by groupthink, that's based on the hoary chestnut of if it ain't broke, don't fix it, has played a significant role in this perpetuation of the focus on the geotechnical ultimate limit state for deep foundation analysis and design. I mean, this is a concept that I talk about quite a bit in my monograph on geostructural forensics, why things fail. A lot of times things fail because we simply do things the way we always did things without stopping to think whether it's still the best way to do things. I found that history has shown time and time again that significant change in civil engineering state of practice, unfortunately more times than not, only occurs when all the stakeholders are collectively motivated by some profound occurrence of failure. Now, this failure could be either some singular catastrophic event that usually involves a dramatic collapse of a major structure with unfortunately a significant loss of life, or if we have repeated occurrences of lesser failure events. Failure really is the only motivation, it seems, to get civil engineers to take a cold, hard look at things and change the way things are done. So it's reasonable to state that the current state of practice for deep foundation elements subjected to axial loading that focuses on the geotechnical ultimate limit state to really, I think, to the point of obsession at times, to simply become a blind fealty to an anachronism. Now, I know there are some of you who say, well, Horvath is, he's up on his soapbox and, he's getting carried away here, complaining about the profession. I don't think this is an overly harsh condemnation of the current herd mentality state of practice. I mean, stop and think. Here in the 21st century, there are those in positions of responsibility using public funds, public resources, time and money, who are calibrating dynamic formulas, which again, this is a concept that was proven a century ago to be wrong for LRFD design, right? Here's a research report that was done by the Washington State Department of Transportation earlier in this century, calibrating pile driving formulas, dynamic formulas for LRFD. All right? So here you're trying to take a concept that was proven wrong around 1930 and trying to make it work in LRFD. So I think you'd be hard pressed to find a better example of putting lipstick on the proverbial pig. I don't think that my comments about things are overly harsh. So in conclusion, it's clear that the answer to the second question that was posed at the beginning of this module, if such change is indeed warranted, why hasn't it been done already? We can state that it's really only the intellectual inertia supported by groupthink, and I think made worse by the recent migration of the state of practice to LRFD, is the reason that the current state of practice for deep foundation elements subjected to axial load that focuses on the geotechnical ultimate limit state has not been critically reevaluated by a majority of stakeholders. So I think that I've illustrated that there is no rational, compelling reason for blindly sticking with the status quo. And I've thus answered one of the two questions that were posed at the beginning of this presentation module. So I'd like to focus on the reasons for changing the state of practice for deep foundation elements subjected to axial load, why we should change to focus primarily on the geotechnical serviceability limit state as defined by axial displacements of the deep foundation element, and I'm not going to present that and discuss it at some length. So the presentation discussion that follow are intended to answer the other question that was posed at the beginning of this module. Why does the current state of practice for deep foundation elements under axial loading need to change? The answer to this question is very complex and multifaceted and has several parts, so this will take some time to go through. Well, to begin with, it's essential to note that in civil engineering context, the word failure has a very broad definition. It's defined as loss of function, where function in this case means the purpose or role that a given structure or structural component is intended or desired to perform. All right, so failure means it doesn't have to fall down to fail. Right? You could have something that stops short of falling down, and yet it is still failure in a civil engineering context. So it's clear that in a civil engineering context, the concept of failure has a far broader meaning than a typical colloquial usage, where it generally has a narrow definition or implication of some physical breakage, that is, the ultimate limit state. So with this broader definition of failure in mind, it's obvious that the traditional approach for deep foundation analysis design, based on solely the geotechnical ultimate limit state, does not adequately address the fact that it has long been known that the performance of all types of structures, in terms of their adequacy to function as intended is really governed in most cases by system stiffness, as reflected generally by displacements and the serviceability limit state, not system strength that is the focus of the ultimate limit state. I mean, for example, it's been known for a very long time, if you're designing a high-rise building, for example, the worry is not so much whether the wind is going to cause this building to fall over. The worry is this is going to cause it to sway in the wind so much that nobody wants to work there or live there, which has happened. In fact, there are numerous geostructural applications, such as both rigid and flexible earth retaining structures, where the soil component is intentionally desired and designed to fail, typically in the form of the active earth pressure state, which is the geotechnical ultimate limit state. And the design goal is to have an overall soil structure system with acceptable horizontal displacements, that is the serviceability limit state. So stated another way, there are times when we intentionally want the soil to fail as part of an efficient design. We just have to make sure that the overall soil structure system does not displace excessively. So the fact that system stiffness is more important than system strength applies to the performance of structure foundations as well. I mean, in particular, the fact that foundation geotechnical stiffness, as reflected in the magnitude of foundation settlement, is more important than foundation geotechnical strength has been known and well documented in the literature since the 1950s. This is nothing new. We've known this for some 70 years now. This focus on foundation settlement as opposed to strength has allowed for geostructural innovations such as high-rise buildings supported on what are called piled rafts, that is a pile-supported mat foundation, where in many cases the deep foundation elements are intentionally designed to be in a state of geotechnical failure, the geotechnical ultimate limit state, and the limiting concerns of the overall superstructure, foundation, ground system are typically differential settlement and rotation of the superstructure. All right, the fact that the deep foundations under the piled raft may be in a state of failure is irrelevant. We want them to fail. So the point is the geotechnical ultimate limit state of foundation supported by deep foundation elements does not adequately address the actual performance-based focus of modern 21st century foundation and geostructural design practice. That focuses more on the overall structural foundation system displacements as opposed to the strength state of one system component. Another important consideration is that historically it was thought that the only axial load that a deep foundation element had to be designed for was the post-installation load applied to the head of the deep foundation element by the structure that was supported by the deep foundation element. And as I said previously, the traditional static load test that's long been assumed to be the gold standard for determining the geotechnical ultimate limit state of a deep foundation element was based on this assumption. And the modern field testing methods that are based on one-dimensional wave mechanics are simply a dynamic variation of this static theme. Well, the reality is that it's been known for a long time, and going back to the 1950s, as it turns out, that there are several other ways in which axial displacements and loads of a deep foundation element can develop that are completely independent of the externally applied loads from a structure. And as I will show you in this presentation, the traditional deep foundation design methods that are based on the geotechnical ultimate limit state provide absolutely no insight and guidance into deep foundation behavior under these alternative displacement and load sources. I'll also show you that the only rational way to deal with all the potential axial displacement and axial load sources on a deep foundation element is by using a design methodology that is based on geotechnical serviceability, that explicitly considers axial displacements of a deep foundation element as the primary design metric. Another important consideration is the fact that the presumption that all deep foundation elements have an unambiguous, unique, single-valued geotechnical failure load or ultimate limit state in axial compression is a myth. Okay? We need to get rid of this. It's a unicorn. It's a myth. The reality is that the geotechnical ultimate limit state of a deep foundation element in axial loading is at best a range in values, and in many cases is ill-defined as the resistance continues to increase with increasing applied load. And this is supported by considering the interpretive results of a typical static load test, which, as I've now said several times, is generally taken to be or assumed to be the gold standard for defining the failure load of a deep foundation element under an externally applied axial load. This is a drilled shaft. Here's the dimensions, about 17 meters, a little bit more than 50 feet long, 760 millimeters diameter. And here's the load settlement curve from a static load test. And as you could see, there are quite a few different methods that have been proposed over the years for defining the quote-unquote failure load from this very specific static load test curve. They range from a low to a high, and we see that in this case, for the same bored pile or drilled shaft, the range in forecast or estimated failure loads is greater than 200%. And somewhere in the middle here, we have the Davison offset method that's very popular in the US, and we have the 10% settlement criterion that's very popular in Europe. So compounding the problem of just interpreting, even if you have a static load test curve, you have a problem interpreting this curve for the geotechnical ultimate limit state, is the fact that the static load test protocols are far from standard, but are subject to numerous mechanical and procedural variations that collectively can result in a wide variation in measured load settlement outcomes, even before you try to interpret that test curve using any one of the many methods I showed you on the preceding slide. In addition, in my personal experience, firsthand experience, is that in recent decades, at least in some geographical areas, there's been a very noticeable degradation in the overall quality and the performance of static load tests. And I say that with great certainty because literally in the first weeks of my professional career, I was out in the field monitoring static load tests. So I've been involved with static load tests on deep foundations for over 50 years now. I think the result in this degradation in quality is due to, in large part, to commoditization that is the direct result of significant contractual changes in how engineer construction is designed, built, operated, and maintained. Another important issue, and I'm going to elaborate on that later on, another important issue that is relevant to the discussion is that the ultimate limit state of a particulate material such as soil is fundamentally different from that of a solid material such as steel, Portland cement concrete, or wood. Specifically, the ultimate limit state or failure of a solid material is defined by a permanent, irreversible state of material rupture that is visually obvious. There's no ambiguity that the material has failed, and is accompanied by a total permanent loss of material strength at the point of rupture. I mean, when I was in academia, I would take a piece of chalk. It was back in the old days of drawing on a chalkboard. I'd take a piece of chalk and I'd break it. And I say to students, there's no ambiguity. This piece of chalk is broken, and it's going to stay broken forevermore. I can hold the pieces together. They're not going to magically knit back together. This piece of chalk is broken forever. And you could see where it broke, and there's no strength left at the point of breakage. Now, on the other hand, the ultimate limit state within a mass of particulate material such as soil is defined by interparticle slippage that is usually concentrated within a relatively narrow band of particles that we refer to as a shear zone or failure zone. Now, in geostructural applications, where you have soil up against some solid structural material like steel or Portland cement concrete or timber, this slippage is generally along the contact surface between the structural element and the soil. Now, in either case, this slippage results in relative displacement within and parallel to the failure zone or along the structure-soil interface, and this slippage continues until the new condition of static equilibrium is established and all the system components come to rest. Note, however, that while this slippage and displacement are occurring, there is still a non-zero shearing resistance, shear strength, between the particles within the failure zone or along the structure-soil interface. That is, failure does not result in a complete loss of material strength as it does with a solid material. In addition, after slippage and displacement have stopped, this failed mass of soil particles or the failed structure-soil interface retains its shear strength so that the failed soil or the failed structure-soil interface can be reused ad infinitum to resist applied loads. Well, the key point I'm trying to make here is that the ultimate limit state mechanism of a geotechnical or geostructural system is not one of outright material rupture that is accompanied by a total permanent loss of material strength as it is with a structural material, solid material. Rather, it's one of application-specific displacement due to contained plastic flow under shear, where a contained, spatially limited zone of failed soil or a failed structure-soil interface retains a non-zero shear strength at all times. The point I'm trying to make here is that the ultimate limit state or failure of a geotechnical or geostructural system is never inherently bad or dangerous, and that's something to avoid at all costs, which is what the goal of LRFD is. In fact, it's quite the opposite. In many cases, the state of failure, the ultimate limit state of a geotechnical or geostructural system, has long been used to advantage in countless applications, such as an earth retaining structure, where the active earth pressure state, which is a failure state, it is a state of ultimate limit state, is allowed to develop, or nowadays we intentionally induce it to develop using a structural material we call a compressible inclusion to create a condition of controlled yielding in order to reduce the earth load acting on the structure through horizontal arching. The point I'm getting at is a lot of times we look for the soil to fail. We don't try to avoid it. We want the soil to fail. As long as it fails in a controlled, predictable, forecastable way. Another application is underground conduits, where we take a structural compressible inclusion, as we call it, we place it above the crown of the conduit, and we create a condition of controlled yielding that induces vertical arching in the overlying soil with a reduction in vertical loads on the conduit. I mean, they investigated this over 100 years ago in the famous Iowa test, where they placed bales of straw or hay over conduits to try to reduce the load on the conduit. Now, of specific relevance to this presentation is that soil or soil structural interface can fail, that is, reach the ultimate limit state, and then it can reverse direction of displacement and fail again in the opposite direction with an intermediate transitional state of non-failure. So the interesting thing about soil or soil structure interface is that it can fail in two directions. It go back and forth, failing in different directions with a state of non-failure in between. Furthermore, the cyclical process of directional reversal of failure with non-failure in between can go on ad infinitum. Well, as we'll see in later modules in this presentation, this ability to reverse failure direction is a significant behavioral feature of the shaft resistance of deep foundation elements to axial loads. So in conclusion, there are many reasons why the current anachronistic state of practice for deep foundation elements subjected to axial loading that remains mired in 19th century concepts and focuses on the geotechnical ultimate limit state and avoiding the geotechnical ultimate limit state should be changed and replaced by an analytical philosophy and associated methodology that better recognizes and addresses actual foundation and geostructural behavior and design requirements as we understand them in the 21st century. You know, just because something was appropriate 200 years ago doesn't mean they're appropriate now. I'd like to believe that we've learned something as civil engineers in the last 200 years. And one of the things we've learned in the last 200 years is that system displacements and serviceability under those displacements really govern the design of most structures. This primary importance of the geotechnical structural limit state is hardly a radical concept for deep foundation elements. I mean, it's long been recognized that the analysis and design of deep foundations subjected to lateral or moment loading is governed in most cases by geotechnical serviceability. In this case, lateral displacements of the deep foundation soil system, as well as the structural ultimate limit state of the deep foundation element shaft. Another thing we'll see in this presentation is that the benefit of basing deep foundation analysis and design for axial loading on ground stiffness and system displacements is that it opens up possibilities to new methodologies for forecasting deep foundation behavior under externally applied axial load. Now, that having been said, it's relevant to note that the geotechnical failure, the ultimate limit state, as well as the structural failure and ultimate limit state, still play essential mission-critical roles in this change focus on geotechnical serviceability. But geotechnical and structural failure are now secondary and supportive to the primary focus on the geotechnical serviceability limit state. So, having shown you how we got to where we are when it comes to designing deep foundation elements for axial load, and why we need to change what we've been doing now for a very long time, in this module I'm going to give you an overview of how we can make those changes. And then in later modules I will go through the different steps in much greater detail. Very important to appreciate that the changes I'm going to show you are things that we could do today. We could do these things using knowledge that has been available and proven for decades. And even more importantly, any design professional anywhere in the world can make these changes using computational methodologies and other tools that are generic and readily available. It's very important to appreciate that the things that I'm going to discuss in the remainder of this presentation are practical to do. So we've established the fact that both science and logic dictate that deep foundation elements subjected to axial loading should always be analyzed and designed primarily for the geotechnical serviceability limit state, that is vertical displacement, and not the geotechnical ultimate limit state or failure, as has been done for the past 2 centuries. And as I said, the remainder of this presentation will focus on how this can be accomplished. And again, I want to emphasize can be accomplished today using existing knowledge and tools at the disposal of design professionals throughout the world. So the challenge is how to do this in a reasonable way that strikes a balance between theoretical rigor and ease of use so that whatever we come up with will be amenable for use in routine practice. This isn't a trivial statement. I've been a professional civil engineer for over 50 years now and have seen that the long road of geotechnical and geostructural engineering progress is strewn with very elegant theories that went nowhere because of their complexity. Somebody developed an elegant theory and a proprietary piece of software, but nobody wanted to use it. An example of this challenge that I'm familiar with personally is the subject of subgrade modeling and models. That was the subject of my doctoral research and dissertation in the 1970s, as I noted earlier. In my research years ago, I learned that efforts to improve on the Winkler hypothesis as a subgrade model date back to at least 1940 in the published literature. But it was not until many decades later that a practice-oriented methodology that can be implemented by any civil engineering practice using existing technology that is available worldwide was developed by me with significant collaboration with Mr. Regis J. Colasanti, PE. The Horvath-Colasanti methodology is based on a combination of modern site characterization and computer-based solution using structural engineering software that is readily available worldwide. And development of this methodology provides broad conceptual guidance for how the desired changes for deep foundation elements can be implemented. So the point I'm getting at is that I have extensive firsthand experience with improving on the way we do things in geostructural engineering, yet coming up with a practice-oriented practical solution. Note that with respect to deep foundations under axial loading, there are some very specific significant challenges and hurdles that need to be taken into account due to the fact that the current state of practice based on the geotechnical failure, the ultimate limit state, first of all, has been in use for a very long time. So it is well entrenched in textbooks, design manuals, codes, and standards. So we're trying to change something that has been around and just been enshrined in generations of published work. Designing for the ultimate limit state is the only design methodology that most stakeholders, and that's the range from knowledgeable owners such as state DOTs, design professionals, material suppliers, construction contractors, know and use. It's the only design methodology that most academicians know and thus teach and research, because that's all they learned when they were undergraduates. Designing for the ultimate limit state seems to produce design that performs satisfactorily in most cases. And a very important fact is that prudent engineering dictates that any significant change in some analysis and design methodology should always be phased in over time, because you have to both educate all stakeholders as well as show them that the new methodology performs satisfactorily in a broadly similar way to what is being done in the past. An example of this is the extended transition from allowable stress design to LRFD in structural engineering, steel design in particular, as well as other aspects of geostructural engineering. The point I'm getting at is you don't just go up to people and say, stop what you've been doing for the last 200 years, throw it all away, forget you ever did it, do it this way only. That's just not prudent. It may be correct, but it's not prudent. So even Professor Fellinius, who's been the biggest champion to date for design based on the geotechnical serviceability for deep foundations, admits this. As you can see from this quote he made in his current edition of the so-called Red Book, that he recognizes that you have to phase in any changes that you're going to propose. So because of these various pragmatic considerations, as well as other factors that I'll point out subsequently, especially some what I consider to be bad habits that have evolved in the current state of practice, in this presentation I'm going to present a two-phase approach to implementing the desired change that I'm suggesting that we do. The key elements of this phase are summarized in the following slides, and then each phase is given its own module subsequently in this presentation. So, phase one. The thesis put forth here is defining the overall goal of phase one is that sometimes you need to be better at what you are doing before trying to do better than what you are doing. And I think the current state of practice for analyzing and designing deep foundation elements for axial load is one of these sometimes. We simply need to be better at what we are already doing. Now, I base this opinion on more than 50 years of professional practice and observations, especially in recent decades, that a number of bad habits, dubious practices, and I think questionable professional judgments have crept into the deep foundation state of practice, so that in some ways the overall quality of the end product in the present is less than what it was in the not too distant past, even in the context of my professional career. I personally feel that the root cause of this deterioration in quality is to a very significant extent the result of the tectonic changes in project delivery methods that has progressed globally over the last few decades, especially for large major projects. These project delivery methods have created what I think is a race to the bottom mentality among project stakeholders, including project owners, and the concomitant commoditization of many tasks related to deep foundations by assuming these tasks are so mundane and routine that they are just a trivial commodity. And as we know, when you have a trivial commodity, you tend to purchase it based on price as the primary, if not sole, selection criterion. And this is done even though these tasks are important and mission critical with respect to the end product. Now, historically, construction projects, at least those in the United States, were executed using the design, bid, build, DBB project delivery method. And this is where the design process is legally, contractually, and financially completely segregated from the construction process. Now, under DBB, all professional services and costs related to design, as well as the review and oversight during construction, are budgeted independently of the construction cost and, very importantly, are paid for directly by the project owner. So these professional services for design and construction oversight are provided to the project owner either by design professionals, private consultants, retained by and reporting to the project owner, or by the project owner's in-house staff. And I have personally been involved in both variations. I have worked for a project owner that had a large engineering department and did their own design and project construction inspection. And I've worked extensively as a private consultant where you're hired to do this by a project owner. So I have firsthand experience with both sides of this. This latter was of a project owner in-house staff was especially common in the past with government entities such as state departments of transportation and other government agencies such as the Port Authority of New York and New Jersey that maintain relatively large engineering departments. I started my professional career working for the Port Authority of New York and New Jersey that manages and operates all the major airports, tunnels, and bridges in the New York City, New Jersey metropolitan area. Now, in either case, the project owner controls all the technical information developed during all stages of a project, including site characterization and the deep foundations, which are of greatest interest and relevance to the present discussion. You'll see this is not a trivial statement. I'm making this on purpose. Now, under design bid build, traditional DBB, the construction contractor really functions solely as a mechanic executing the work that has already been designed. Although contractor input is still important. I mean, contractors are engineers as well, and they have experience doing what they do, so they very often have good ideas. So contractor input in the form of value engineering type suggestions or requests is generally allowed by most contracts, but only once the construction contract has been awarded and the work begins and is progressing. Nowadays, the trend in project delivery, especially when the project owner is some sort of government entity or agency, is toward design build or design, build, operate, maintain. And this is where the project owner contracts with a single business entity at the very early stages of a project, very often when it's just a concept. And that business entity is responsible for both designing and building the project, and sometimes operating and maintaining it for some specified period of time afterwards, 10, 20 years, whatever. This single business entity is typically a project-specific joint venture of several independent businesses, and generally the primary and dominant JV entity is typically a large construction firm, and nowadays that firm often has international ownership and presence. And I think that international nature is important. There is nothing wrong with it per se, but in my personal experience, and again, I'm drawing on firsthand experience, especially in recent decades, if somebody basically leaves the United States after the job is done, you have to wonder what their concern is about the quality of the project being done. Now, in the past, design build was often referred to in the U.S. as turnkey construction. So note that under design build or design build with the operate maintain option, the cost of all professional services related to planning, design, and construction is included in what is typically a single lump sum price, and just as importantly, a fixed time to construct. I've come to see in recent years that the time element can be as important or even more important sometimes than the dollar component per se. So both the price and the time for construction agreed to between the project owner and the project JV, even before planning and design, no less construction even begin. I think very relevant to the present discussion is the fact that under design build or design build operate maintain, the primary design professionals involved in a project have a direct contractual relationship with the project joint venture, not the project owner. That's a really fundamental tectonic shift in contractual relationship for design professionals. Now, of course, the selling point of design build or design build operate maintain has always been portrayed as a proverbial win-win for all concerned. Both of these are assumed to greatly simplify the life for a project owner, as they only have to contract with one business entity, the project joint venture, for the entire project. In addition, the project joint venture assumes most, if not all, the risk in delivering and possibly operating and maintaining for some period of time the finished product within a specified period of time. Both design build and design build operate maintain are presumed to streamline and optimize the design and construction process. It's portrayed as being a single, seamless process run by a single organization that can be progressive and innovative. All these wonderful things to provide the best finished product at the lowest possible cost and least amount of time, no delays, no extra costs from RFIs, requests for information, change orders, claims for extras, etc., that occur during the traditional design bid build. That's the way it's portrayed. And I like to call this the one big happy family syndrome. All right? Project owner thinks everything's going to be wonderful. I deal with one party, they do it all. I'm going to get the best job, fastest time. What could go wrong? Well, let me tell you, in my personal first-hand experience, a lot, and always does to some extent. Nevertheless, it should come as no surprise that in recent years, project owners, especially government entities, which long ago tried to get rid of their in-house engineering departments and streamline their organizations, reduce their costs, have become enamored by and seduced by the design build, operate, maintain promises of one-stop, problem-free, fixed cost, guaranteed completion date for design and construction, and operation and maintenance in some cases. So to a project owner, especially a government agency that basically has little or no engineering staff anymore, it seems like the best thing that could ever happen. Well, in my experience, and again, this is firsthand experience, much of my work in recent decades has been in forensics, dealing with failures as well as construction-related litigation and arbitration. So the comments I'm making here, obviously I'm not a fan of design build, operate, maintain, and again, this is based on extensive firsthand experience in the last few decades of seeing what could happen in terms of litigation and arbitration. There's simply many more losses than wins for everybody concerned, especially the project owners. And I'll give you a very specific example in a minute. The reasons for this are many and vary, but the ones of greatest relevance to the present discussion are the fact that the most dominant member of a design build or design build operate maintain joint venture tends to be a construction contractor, simply because the dollar value of the construction work is by far the greatest percentage of the overall project cost. The cost and time, and again, don't forget, in the design build contracts, there's usually a very fixed date, years in advance, that's set when the contract is signed. So time is just as important as money in design build. The cost and time sensitive nature of design build projects put considerable pressure on design professionals who, as I pointed out, are now working for and thus beholden to the project joint venture and not the project owner as in the past. So the design professionals are really under a lot of pressure to deliver a design concept for as little money and the fastest time possible, a concept that can be built fast and cheap and does only what it has to do to check all the boxes to comply with contractually specified codes, standards, and design manuals. And again, I'm telling you this from firsthand experience. When these design build or design build operate and maintain contracts are signed, in the pages and pages of the project document, it usually says you're going to follow this code, what it says, and this is how you're going to design the drilled shafts, this is how you're going to design the driven piles, this is how you're going to do your site characterization. It's all spelled out that you're going to follow certain published documents. So as long as the project joint venture follows what those documents says, they checked every box. They've done their job in their mind. I think this is a classic case of design professionals doing the absolute statutory minimum to meet the letter of the law as specified in some project agreement and not the spirit of the law. And having spent my entire professional career as a design professional, I can tell you, you're kind of squeezed, because in this case, there is always the unspoken, ever-present underlying pressure on design professionals who are part of a project joint venture to, quote-unquote, keep the client happy. And client in this case is the contractor in the project joint venture, and to stay in the client's good graces. Because if they don't, the word's going to get out. All right? Even in this global environment, heavy construction is a relatively small business. Everybody knows everybody in the business. And if a particular consulting firm gets a reputation of, gee, they're trouble to work with, contractor says, oh, I know this firm, they're a pain to work with, they don't do what I ask them to do, they're always looking to do more. This consulting firm is going to go out of business simply because they're going to run out of business. They're going to get a reputation in the construction trade as being hard to deal with. So, we can talk all we want about professionalism, but we can't divorce ourselves from the fact that each of us is human. And when you deal with human nature, the fact of life is we've got to work to make a living. That's the way it is. And for consulting firms, if you want to stay in business nowadays in design build, you got to get a reputation of keeping the contractor happy. You got to get a reputation that you bend to the whims of the contractor, you do what the contractor wants, how a contractor wants, when a contractor wants. Another negative is that I found that project joint venture typically hoards technical knowledge because they want to use it for their proprietary benefit for future projects. In extreme cases, and again, I'm talking from personal first-hand experience, contract arrangements are such that the project owner can't even gain access to technical knowledge that they paid for on their own project. I'm thinking of a specific case here in recent years in which I had first-hand experience. I went to the project owner, who I actually knew them professionally, and in this case, I knew the person personally from previous experience. And I said, I'm doing some research. I would like to get some information about the site characterization and the driven piles and pile load tests that were done on your recent project. And they got back to me in a few days and said, I'd love to help you. I know you're just doing this as academic research, but the contractor says I can't have it. Even though I paid for it, I can't have it. And this to me was just, I was astounded. I really was astounded. Experience has shown that design, build, operate, maintain oversight by a project owner is still required. So the owner still winds up having to hire a shadow consulting firm to look over the shoulder. In fact, they use that expression in these contracts, OTS, over the shoulder of the contractors and design professionals. But the problem is the project owner's team of design professionals has very limited contractual control on the project. And I recently finished a huge, major, multi-year arbitration about construction. I can't mention names or even where the project was or what it was about, but it was, you could really sum it up that the engineers, the design professionals that the project owner hired to look over the shoulder of the project joint ventures engineers, design professionals, really can be summed up as look to but don't touch. But be sure you write plenty of memos and emails about all the problems you see, because I guarantee you, whatever litigation discovery happens years later, you want this information to be found. Again, I can tell you from firsthand experience, having been brought in as a forensic, in a forensic capacity, design, build, operate, maintain projects are never, ever, never problem-free, because you're going to have litigation or mandatory arbitration over language interpretation, claims for extras, project delays, and this litigation arbitration can drag on for years after a project is completed and in service. And I can give you, this is a public record. It's a project I was not involved in. It's a project that's I'm very familiar with because it's not far from where I've lived and worked for my entire life. This is the new Interstate 87 New York State Thruway Bridge that crosses the Hudson River at the Tappan Zee. Now, this is a cable-stayed span with long approaches that opened for traffic 2017, so 8 years ago at the time I'm recording this presentation. The litigation involving contractor claims for over $1 billion US for extra work and delays. And this is against an initial project contract of slightly over $3 billion. And owner counterclaims for construction defects of about 1/3 of the main cables of the cable stayed spans continues to the present. And present being at the time that this presentation is being recorded. I started this at the very end of July 2025. It will finish up in the early days of August 2025. So I just looked up at the time I was making this recording. This litigation is still going on. It has not been resolved 8 years later. Now, I mentioned earlier that one of the things that concerns me is we don't do things as well as we used to. And a specific example of the deterioration of deep foundation related state of practice brought on by commoditization related to design, build, operate, maintain, that is relevant to this presentation is the performance of the static load test. And again, as I've mentioned now several times, the static load test is held up as being the gold standard for telling us what the ultimate limit state geotechnical failure load, if you will, of a deep foundation element is. So don't believe me. Just believe Felinius, who made this statement in his textbook where he discusses static load tests. Right? Nothing is so bad that it cannot be made worse. That was his. You can look it up yourself. Here's the citation in the red book that he published earlier this year in the section dealing with static load tests. So as I said, static load tests have long been viewed as the inviolate, never questioned gold standard for defining the geotechnical ultimate limit state or failure load of deep foundation elements subjected to axial loading, and thus for comparing and evaluating any and all methodologies and methods for forecasting or measuring the geotechnical ultimate limit state of deep foundations under axial loads. And when that's important because the interpreted results from static load tests are widely used in construction contracts as the key, if not primary metric for meeting contractual requirements related to deep foundation elements. Unfortunately, my personal observations are that the quality of results from static load tests have suffered mightily in recent decades due to the commoditization. And I say that from really, again, personal experience. Literally, the first weeks of my professional career in June of 1972, I spent out at Kennedy Airport in the parking lot at night doing pile load tests for a test pile program. So, I've seen the technology of static load tests on deep foundation elements over the last 50 plus years. Nowadays, more times than not, the results of static load tests are more like I call fool's gold than the gold assumed historically, as well established that bad data are worse than no data at all. Bad data makes you think you know something when you really don't. It's worse than not knowing anything at all. Because commoditization focuses on cost above all else, this has created a race to the bottom in performing several aspects of static load tests that are really crucial and mission critical to a successful test outcome. This in turn has caused professional and technical quality to erode to the point of rendering the outcomes of static load tests problematic in many cases, and again, in my personal experience, completely worthless in some cases. Even though you can always find a licensed design professional who will approve and accept worthless test results anyway. There's never a shortage of somebody with a professional engineer's license who will sign and stamp a bad load test, in my experience. So for this and many reasons, the focus of phase one in this presentation is the things that need to be done, in my opinion, to improve the current state of practice that is based primarily on the geotechnical ultimate limit state of deep foundations subjected to axial loading. Again, what I said earlier, we got to be better at what we're doing now before we can even think about doing something or changing something in the future. It's also that these improvements to the current state of practice that I think need to be made are necessary to provide a proper groundwork and basis, a foundation for changing the state of practice to one that is based primarily on the geotechnical serviceability limit state. Well, let's now summarize what I am going to talk about in phase two, which is changing the state of practice. This quote, I think, illustrates how the state of practice for analyzing and designing deep foundations for axial loads can be changed to focus on the serviceability limit state instead of the ultimate limit state, simply by drawing on underutilized technical knowledge that already exists and, as we'll see, has been hiding in plain sight, if you will, for decades now. So we don't have to do a lot of new research. We can simply make better use of what we already have. As we'll see, I'm going to base things on the well-known TZ-QW methodology for analyzing axial load displacement of a deep foundation element. And the required spring stiffnesses for the TZ and QW springs are going to be determined by a novel combination of physical and mathematical models, coupled with the outcomes from current state of practice of site characterization. Again, as I've said now a couple times in this presentation, I'm going to show you how we can make these changes today based on knowledge we already have, based on tools we already have in site characterization and computation. We can start doing better today. I'll also discuss some possible future directions for forecasting deep foundation performance under axial load that are based on ground stiffness as opposed to ground strength as has been done historically. So I will illustrate some new ideas that I think are kind of interesting. Well, in the next two modules, I'm going to discuss phase one and then phase two in considerable detail. But before I get to that, there are some important housekeeping details to note. As I've mentioned earlier in this presentation, consistent set of units, terminology, and notation are really mission critical elements in civil engineering that are often not given the attention they deserve in presentations and publications. I've sat through countless presentations, read countless technical papers by very knowledgeable people, but they're very sloppy about their notation, their terminology. So I'm a bug about that. I try to be consistent and clear about these things, simple things. So with respect to units, even though metric units tend to be universally used nowadays, authors from some countries sometimes use metric units other than the preferred SI version of metric units because of long-standing habits or practices in that country. I mean, for example, one that I've seen a lot in geotechnical related publications is using the unit of kilograms per square centimeter that purports to be a stress unit. It clearly is not. Right? Kilogram is mass, it's not a force, and centimeters are deprecated in SI. All right? Length units in SI are either meters, millimeters, right? Not centimeters. Yet there's no shortage of geotechnical papers where people use kilograms per square centimeters as a stress unit. I think this practice was much more common in older publications, but unfortunately you still see it nowadays. So given the fact I'm trying to appeal to an international audience, I'm going to use the SI system and metric units as primary in this presentation, although I will give the imperial or US customary units secondary in most cases. There will be some cases for historic reasons I will use imperial units first. Now, with respect to imperial units, there's one bad habit in US practice that has always irked me. This is especially related to deep foundations, and it persists to the present for historical reasons. And this is the use of the ton as a force unit. And I think this really goes back to 19th century usage in the United States. Now in this context, 1 ton, that's sometimes called a short ton, is 2,000 pounds, 2 kips, or 8.9 kilonewtons. And by the way, you'll notice in this presentation, I use a decimal point to indicate a fraction amount. I'm well aware of the fact that in many countries and many regions, people use a comma to indicate a fractional amount of an integer. I will use a decimal point. Well, as we all know, geotechnical and geostructural engineering are notorious for their lack of standardization with regard to terminology and notation, even compared to other practice areas in civil engineering, such as structural engineering. This lack of standardization is exacerbated by the fact that terminology and notation have changed over time, and certainly in the US at least, there are regional preferences within the English language. To give you some specifics, this lack of standardized terminology and notation is particularly acute for deep foundations, where, for example, just in American English, there are at least 7 terms for the end of an installed deep foundation element that is farther from the ground surface: base, bottom, end, foot, point, tip, and toe. And I've highlighted toe because I'm going to use that term. And there are at least 3 terms for the other end of a deep foundation element: butt, head, and top. And I'm going to use the term head. I think head and toe are very good terms to use to define the 2 ends of a deep foundation element. First of all, they're logical. Second of all, they are easily translated into any language. So for the purpose of the presentation, so we're all clear about terminology, as I did earlier for the generic term pile. I'm going to show some additional slides that will define some of the terms I'm going to use. And the slides that follow are basically what I showed in 2020 monograph, and they're based on published recommendations made by Felinius in recent years in his publications. Now, as a rule, stresses are denoted with lowercase letters and forces with capital letters. Displacements use lowercase letters. One notable exception to what I've done in the past and in earlier publications and presentations that you'll find that I've done is I use, instead of using the term neutral plane, I will use the term equilibrium plane. And this reflects a change that Felinius himself has made only within the last few years. And I think actually equilibrium plane is actually an arguably much better term than neutral plane. So here are the terms and notations I will use for basic geometry. I already pointed out head and toe. These are the notation and terms I use for externally applied loads. Give you a second to look this over. And in terms of the interaction stresses between a deep foundation element and ground, lowercase r sub t is the unit toe resistance. That's a stress. We have negative shaft friction, which is a stress, and positive shaft friction, which is a stress. And both negative and positive shaft friction have additional names and specific notations depending on specific load cases and applications. And I will define them as they occur throughout the remainder of this presentation. What used to be called the neutral plane, I will now use the term equilibrium plane. Again, this is a change that Felinius has made only in the last few years. And as I said, I think this is actually a better term because it more clearly defines, as we'll see, what we are talking about. If you're not familiar with the concept of an equilibrium plane, this is, in my opinion, an extremely important concept in deep foundations when it comes to axial loading. And I'll be using it extensively throughout the remainder of this presentation. So if you're not familiar with this term already, I will illustrate what it means in specific applications in detail. Another item of note is the definition of deep foundation element taper. And there's at least 6 different ways to define this based on angle, percentage, or length. And either of these can be defined based on radius or diameter. I'm going to use the definition of taper angle, alpha, that is based on radius, and is defined in this graphic that you see here. There's a lot of inconsistency in literature. I know Felinius uses something different, and many other people throughout the world use different definitions of taper. I hesitate to say that one is better than the other. I think taper angle is a nice, concise way of defining taper. I know that SI system of units does not like to use degrees of angle, but I think in this application, taper angle, as I've illustrated here, as defined as I've shown here in this graphic, is a good way to define taper. And as I said, I've used this throughout all of my presentations and publications, and will in this presentation as well. Now, just for interest, to give you some specific numbers, timber piles typically have average taper angles between 0.2 and 0.3 degrees. However, they are non-uniform. Very important to emphasize this. I've done a tremendous amount of work with timber piles for over 50 years now. They're very popular in the eastern United States, where I've spent a good part of my professional career. And it's very important to recognize that they are non-uniform. For example, for the southern yellow pine treated timber piles that we tend to use here in the New York City metropolitan area, circa about 1990, these are some very typical dimensions of piles that were used and I will be talking about. So while this particular pile, and this is an actual pile that was used at Kennedy Airport in New York City, where I have a tremendous amount of professional experience and have done a lot of my research based on Kennedy Airport. While this pile has an average taper angle of 0.23 degrees of angle, the practice at the time was to determine the diameter and thus taper angle at quarter spacings along the pile shaft, and you see a rather significant variation in taper angles for these are quarterly markings of this pile shaft. So with southern yellow pine timber piles, in this case, they tend to have a much steeper taper angle down near the head, toe compared to the head. And this becomes important, as we'll see later on. Taper angle becomes a very important thing in terms of geotechnical resistance of tapered deep foundation elements. So, having concluded an overview of phases 1 and 2 that I will be talking about in considerable detail, before moving on to those two phases, I want to, in this presentation module, I want to talk about some reference data, because it's very important, I feel, that rather than say we should be doing this and we should be doing that, is to also put some numbers on it to show you some case history examples of actually using the methodologies and methods that I will be presenting. I think it's very important in terms of trying to convince you to make the changes I'm going to be talking about in phases 1 and 2, is to show you that the things I will be talking about actually produce results that agree well with what we observe in practice. So in this presentation module, I want to talk about some reference data just up front, just to give you some background for things that I will be using throughout the remainder of this presentation. So as I've said earlier, the overarching goal of this presentation is to show both design professionals and academicians that what I'm presenting in both phase 1 and phase 2 is not only necessary but practical, right? So we can implement this at the present time using present knowledge, present geotechnologies that are available worldwide, and they're straightforward to implement with nothing more than generic spreadsheet software. So the practicality of what I'm presenting here is just as important as the theoretical rigor of what I'm presenting here. As I said before in this presentation, there's far too many very useful, clever ideas and concepts in geotechnical and structural engineering that have never gotten implemented, simply because they're excessively complex or they're impractical for everyday use. And I say that as having spent a very good portion of my professional career in engineering practice and seeing things published by others. And I can attest to this firsthand based on my personal work with subgrade modeling and models. I came up with what I think was some very clever advances of the state of knowledge in 1979 in my doctoral dissertation. But it was really, I knew then at the time I wrote my dissertation, it was unfortunately not practical to use based on what was available to the everyday practicing engineer at that time. So it wasn't until decades later when site characterization technology and structural engineering computer software had caught up to the point where the models that I had developed in the 1970s could be implemented in routine practice using tools available to design professionals worldwide. And that's why in more recent years I collaborated with Regis Colasanti. Mr. Colasanti, very extensive professional career as a practicing engineer in structural engineering. And I partnered with him to be able to show that the everyday computational tools available to a structural engineer in practice anywhere in the world could solve the theoretical things I had come up with decades earlier. This issue of practicality is not unlike patents, where something like 95% of the patented concepts in the United States are never commercialized, no less a commercial success. And again, I say this as someone who holds 2 now expired U.S. patents. I can personally attest to the challenges involved with commercializing a clever idea that has been patented. So, in order to illustrate the practicality of what I'm going to present in the Phase 1 and the Phase 2 modules subsequently, actual site data and deep foundation case history material are presented on an ongoing basis throughout the remainder of this presentation as I address different topics. So the purpose of this module is to provide some broader background and foundational information on the site data and case history material that I will be presenting, so that when I provide it in the remainder of the presentation, you'll already have some background and context of what I'm talking about. So I'll provide some general ideas here, and then we'll get into specifics as I go through the remainder of this presentation. So to achieve the goals of this module, I'm going to focus on my extensive research into the axial compressive loading of driven piles in predominantly coarse-grained soil conditions. And I'm also going to illustrate the stated knowledge site characterization outcomes I've developed based on piezocone and size of piezocone soundings. My research in these areas included 2 broad topics. The geotechnical and foundation history of the John F. Kennedy International Airport in New York City. Kennedy Airport site provides an excellent opportunity to trace how both site characterization and deep foundation technology have changed over the course of the last 80 years since construction of Kennedy Airport began in the early 1940s. So transitioning from the era of hand calculations using a slide rule to the present. And as I said earlier, I began my professional career doing pile load tests at Kennedy Airport in 1972, so I have over 50 years of firsthand experience of work at Kennedy Airport. I'm also going to talk about the unique load-bearing mechanisms and behavior of driven tapered piles, which have been the deep foundation element of choice for the vast majority of deep foundation installations at Kennedy Airport from the 1940s to the present. As I'll show in the following slides, extensive technical information on both Kennedy Airport and driven tapered piles is available through several venues if you want additional information on these subjects that goes well beyond what I'm going to cover in this presentation. I have a tetralogy of white papers dealing with the geotechnical and foundation engineering history of Kennedy Airport available on my ResearchGate website. These publications are available at no cost. I also have 2 YouTube presentations that are available about Kennedy Airport. And my work with tapered piles, which my early work at Kennedy Airport in 1972 got me very interested in tapered piles. So my work at tapered piles, which culminated with a monograph I published a few years ago on the subject. This is available print on demand from any online bookseller, And there's also a YouTube presentation that summarizes the contents of that monograph. So the bottom line, there's a lot more information out there if you want to go well beyond what I will just summarize in this presentation. So, as I said, only a summary of the geotechnically relevant subsurface conditions at Kennedy Airport will be presented in the following slides. So you have some background information when I show some results later in this presentation. Kennedy Airport was the third major airport built in the New York City metropolitan area after Newark Airport in the 1920s, LaGuardia in the 1930s, and Kennedy opened in 1948. To talk a little bit about the geology of Kennedy Airport, the Atlantic Coastal Plain Physiographic Province covers much of the east coast of the United States, and the site of Kennedy Airport is at the very north end of this physiographic province. And this physiographic province is typified by sloping crystalline bedrock that slopes to the southeast into the Atlantic Ocean with multiple strata of sediments deposited on top of the crystalline bedrock. And in the Kennedy Airport area, which here, there are several Cretaceous strata and several Quaternary strata. I'm only going to focus on what is called the upper glacial aquifer. This is a Pleistocene stratum, and in the area of Kennedy Airport, it's generally around 40 meters, or roughly 125 feet thick. And the upper glacial aquifer, or UGA as it's called, has always been the foundation-bearing stratum for all the structures at Kennedy Airport. Everything from buildings to elevated roadways, parking garages, even the very tall light poles that you see in the parking lots are all supported on driven piles bearing in the upper glacial aquifer. There's been some more recent research as summarized in this paper by Moss, where we now appreciate that the upper glacial aquifer actually has three distinct strata. The Wantagh strata, which is predominantly fine-grained, is generally absent or extremely thin throughout Kennedy Airport. So generally, we're only going to look at the Merrick and the Belmore strata, which are predominantly coarse-grained. But as we'll see later on, they have very distinct, different signatures. Then because of significant sea level rise of maybe about 125, 130 meters, over 400 feet, since the peak of the Pleistocene, there was naturally a Holocene organic stratum, a marine tidal marsh stratum covering the site of most of Kennedy Airport. And this was covered over by a Holocene fill that was deposited, basically a hydraulic sand fill that was deposited in the 1940s to develop the airport. So this is the typical sequence we see at Kennedy Airport. A stratum of sand fill, relatively thin stratum of organic clay with some peat, underlain by natural coarse-grained strata. The New York City metropolitan area, here's New York City here, has a surprisingly significant seismic history that has actually been studied extensively only in the last few decades. And as we'll see, that has had a significant effect on the foundation design at Kennedy Airport in the last few decades as well. This map shows the result of some research that was done by seismologists. It shows the estimated epicenters of seismic events going back to, in history, at least to the time of the beginning of the European colonization and settlement of the New York City area in the 17th century. And the black lines are areas of known or believed brittle geologic faults, the most famous of which is the Ramapo Fault, that, as you see, cuts from eastern Pennsylvania across northern New Jersey into the southern part of New York State. Here's Kennedy Airport, and it's interesting that it's very close to the epicenter, or estimated epicenter, of what is the largest known seismic event in this recorded history, an event in the late 1800s that had an estimated magnitude of slightly over 5. More recently, there was a magnitude 3.5 earthquake that was epicentered close to Kennedy Airport. For those of you who follow recent history in the New York City area, may recall that there was a relatively significant event, at least for this area, almost magnitude 5, in early 2024 that originally was called the White House Station earthquake, and then they revised the name a little bit later to the Tewksbury earthquake, sited in the general vicinity of the Ramapo Fault. They're still trying to sort out whether it was how this event and its many foreshocks and aftershocks were related to the Ramapo Fault. I actually did a small YouTube presentation on this earthquake last year that you could look at if you're interested. So the point here is that seismicity is now a significant design requirement in building codes throughout the New York City metropolitan area. It wasn't when I can remember when I was an engineering student. I did all my education in New York City for all my advanced undergraduate and advanced degrees. And at that time, basically a professor would come in and say, well, there are these things called earthquakes, but we're in New York City, we don't have to worry about them. Well, now we realize we do have to worry about them. So that gives you a little bit of the geologic background of things I'm going to be talking about throughout the remainder of this presentation. I now want to get into one of two very significant and therefore lengthy presentation modules. This is the Phase 1 module that I'm going to be talking about in considerable detail. What are the things that we need to be better at the present time? Things that we have been doing for a long time that in a lot of ways are not quite as good as they could be or should be or even were in the relatively recent past. What are the things that we should be doing better now just to design deep foundation elements based on the ultimate limit state, that is for failure, as we have been doing? Well, as I said, this is a rather lengthy module, so I have broken it up into segments and subsegments. As you could see here, there's quite a variety of different topics I'm going to be going through. Again, this is a very long module, so you may find it useful to watch this module in segments as opposed to one sitting. Let me begin with an overview of what I'm going to be covering in this module. So again, this module focuses on topical areas where I feel the current state of practice for deep foundations subjected to axial loading that is based primarily on the geotechnical ultimate limit state or failure needs to be improved upon for several reasons. First of all, we need to eliminate the numerous deficiencies in the level and consistency of technical quality in the current state of practice that have developed and accumulated in recent decades. These deficiencies, in my opinion, are the combined result of cost cutting brought on by commoditization of numerous tasks related to deep foundation engineering practice, as well as the failure to make maximum use of advances in geotechnology. Also, the things I will be talking about in this module will lay the theoretical groundwork for Phase 2 that addresses making the change to using the geotechnical serviceability limit state as the primary metric for the analysis and design of deep foundation elements subjected to axial load. As I will show you in this module, this lack of explicit consideration of the geotechnical serviceability limit state for deep foundation elements is really out of step with a lot of things. First of all, it's out of step with the actual needs of deep foundation design based on the current state of knowledge of many potential sources of axial loads and displacements on deep foundations, in addition to the usual post-installation externally applied load from the structure to be supported by a deep foundation, which has been the basis for designing deep foundations historically. Again, historically, we thought we only had to design for whatever structure the deep foundation was going to be supporting. And we now know that there are many other sources of load and displacement that we need to consider. Currently, geostructural design is what we call performance-based. We don't obsess on some aspect of it. We look at the performance of the overall geostructure. And we now realize that the performance of most geostructures is governed by the serviceability failure. That is the serviceability limit state and not the ultimate limit state. Now, I've organized the many topics discussed in this presentation module into 4 broad topical areas. I'm first going to discuss site characterization. Then I'm going to be talking about geomechanics fundamentals. These are things that all of us have learned somewhere along the line, but maybe we have not learned them correctly or properly or in the detail that we should. I'm going to be talking about deep foundation and ground interaction, and then finally geotechnical axial resistance determination. So within each of these 4 topics, there will be, in some cases, some subtopics. I'm going to then illustrate these different topics in an integrated, coherent fashion into a framework that I will illustrate using actual data from Kennedy Airport, New York City, that I overviewed in the preceding presentation module. So let's now move on to the segment where I want to talk about site characterization in some detail. This is an area that has really been of considerable interest to me the last few decades, when I've done a lot of work using the cone penetrometer. Well, hopefully we all know that site characterization is, or at least should be, the cornerstone of any civil engineering activity that involves the ground. This is true whether the project involves design for new construction or analysis of an existing structure for forensic or other purposes, and it's independent of the size or importance of the project and the structure involved. Now, despite the essential mission-critical nature of site characterization, I feel there are 2 serious problems that exist in the present. One is that despite the tremendous advances in technology in recent decades, the state of practice remains stubbornly fixated and reliant on technologies such as the standard penetration test, SPT, that are now well over a century old. And this is especially true on routine projects and in certain geographical areas, with New York City being one of them. This is due in large part to the fact that the City of New York Building Code has always been and remains enamored of SPT end values. This might have been valid many decades ago, but certainly is not now. The second item is that there's been a regression in the overall quality of many aspects of site characterization. And again, I think this is due to the commoditization of many basic but essential tasks that have led to having the lowest price vendor do the bare minimum site investigation and characterization that is required by some code. Again, it's this check the boxes sort of approach to things. It's very important to note that these opinions are not just mine. They are held by many others, including those who are internationally acknowledged experts in site characterization. And I'll give you some examples now that you could look up on your own. There was a excellent state-of-the-art report in one of the international conferences back in 2009. These are names that hopefully everyone recognizes. And if you read this state-of-the-art assessment, you will see that the authors make the same points pretty much that I have already stated. This is from a presentation that Dr. Paul Main gave to the ASE Met section in 2012. And I like this because it illustrates the changes that have occurred from 1902 to 1950 to 2012, which was current at the time. And if you look at all the things that have changed in everyday life, what's constant, right? The standard penetration test and the standard split spoon. Now, that's not bad per se, but when you realize that there are many improvements that have not been used in the period covered by this slide. This was an article that appeared in ASC Geostrata magazine back in 2020. And again, look at the subtitle of this article, Have We Regressed from Decades Past? And again, the authors are well-known names in site characterization. So again, this is a theme that we've not only haven't advanced, but we've taken a step backward in recent decades. This is a theme that not only I have, but many others have as well. Nowadays, there's a large selection of invasive in situ testing devices to choose from. These are complemented by numerous non-invasive testing methods that measure some geophysical parameters such as wave velocities within the ground from the ground surface. Now, it's important to appreciate there is no one in situ testing tool that is the best for all ground conditions. You really need to pick the tool that fits the conditions. But the method that comes closest to being an all-purpose tool in my experience is the cone penetrometer that is used in the cone penetration test that has been evolving for almost a century now since it was first developed in the Netherlands in the 1930s. The two most widely used versions of the cone penetrometer at the present time are the piezo cone and the seismic piezo cone. The nice thing about the seismic piezo cone is that it combines both invasive and non-invasive methodologies. It measures the shear wave velocity profile through the ground. I've done a lot of work in recent years with both the piezo cone and seismic piezo cone that I will be talking about throughout the remainder of this presentation. So the position I'm taking in this presentation is that the current state of practice for analyzing and designing deep foundations subjected to axial loading really needs to make much greater use of in situ testing methods other than the standard penetration test, especially the piezo cone and seismic piezo cone. Now, while the use of the piezo cone and seismic piezo cone has been increasing, even in areas such as New York City, which was really long resisted using these newer technologies for site characterization. And again, I blame the New York City building code for a lot of this hanging on to ancient site characterization methods. If you review the published literature, it indicates that the piezo cone and seismic piezo cone data are not being post-processed and used for routine deep foundation design to anywhere near the full extent possible. What I'm talking about here is there's no shortage of papers, right? Case history paper talking about driven piles and coarse grained soils someplace in New York City. And they say, the authors say, well, we did SPTs, we did CPTs, and they present some data and they say, okay, here's how we designed the piles for using SPTs. Well, what'd you do with all that cone data you got? You mentioned you took it, but you didn't use it. Why? That's the thing that bothers me. Now, as I've discussed in many publications and YouTube presentations that I noticed in the preceding module, there are dozens, literally dozens of soil properties and parameters for both coarse and fine-grained soils that you can obtain by post-processing the QC, FS, and U2 data measured in a piezocone, the seismic piezocone sounding, with additional post-processor results from the shear wave velocities that you measure in a seismic piezocone sounding. And you got to note that the calculations required to post-process these data are simple enough to do by hand. I mean, I've done it, so I can attest to that personally. But it's really the sheer volume of data that's generated typically makes use of generic spreadsheet software as a practical necessity. Note that there's comprehensive post-processing, and I'm talking about dozens, that's no exaggeration, dozens of different soil properties and parameters, does not require purchasing proprietary software. Although I see a lot of people nowadays choose to do this, it saves them time and effort. Right? They don't have to sit down and program equations into a spreadsheet. But if you want to do this, all of the post-processing that you need to do, the equations you need for this can be found in numerous documents that are found online at no cost. So it's important to understand that there's nothing wrong with purchasing proprietary software. I actually did that some years ago just out of curiosity to see if they could offer something I couldn't do myself. And I will tell you that the people who write and sell this proprietary software for processing cone data, they use the same equations that you can find in online documents at no cost. And these are some of the documents that I've used that you can find online. They're a combination of work that has been research that has been supported by government agencies, as well as documents put out by the companies that offer cone penetration services in North America. Now, the final site characterization topic I want to discuss is the most important for the purposes of this presentation, and this involves which specific soil properties and parameters I found to be the most important for analyzing and designing deep foundation elements. As I said, there are literally dozens of properties and parameters, but there are a couple that really stand out as being really mission critical for deep foundations. They fall in two broad categories. One is defining the stress state, especially the horizontal effective stress that exists in the ground prior to deep foundation installation. And this is defined by the coefficient of lateral earth pressure at rest, KO. I'll illustrate the importance of stress state and KO later in this presentation module, as horizontal stress in the ground not only dominates shaft geotechnical resistance, but it may surprise you to see that it dominates toe geotechnical resistance as well. So the horizontal stress state in the ground is really essential for both the current state of practice based on the geotechnical ultimate limit state, as well as for the proposed change state of practice based on the geotechnical serviceability limit state. The other category of soil properties and parameters has to do with the soil stiffness as defined by the small strain shear modulus Gmax. Now, I want to point out that Gmax is the more common notation one finds used in the United States, but in much of the rest of the world, you'll find G0 or G0, the more common notation that is used. I will be using the Gmax notation. There's actually very good reasons why I don't use the G0. It turns out G0 was used in some other things that I found related to deep foundation. So to avoid any confusion and ambiguity, I've settled on using the Gmax notation. But many of you may be more familiar with the G0 notation. Now, it is really essential, and I can't emphasize this too much, that Gmax be determined based on a site-specific basis made by measuring the shear wave velocity and the size of piece of cone sounding, or some other methodology such as cross-hole or down-hole wave measurements. As opposed to, you will find empirical correlations based on QCFS and U2 data from cone penetrometer soundings. However, these empirical correlations are all for what are called young or well-behaved soils. And as such, they do not consider the structure or microstructure that one can encounter due to aging, cementation, etc., that you can only detect with site-specific measurements. And I will give you some very specific illustrations of this for Kennedy Airport later in this presentation, actually in the phase 2 module. Another benefit of site characterization using piece of cone and seismic piece of cone soundings is you get a freebie. You get an extra benefit because it's an extremely useful and cost-effective tool for site-specific liquefaction assessment. All right, seismic liquefaction is something that we need to do in many, many places nowadays, including in the New York City metropolitan area, as I showed you earlier. So we can do both static or flow liquefaction as well as dynamic or seismic liquefaction assessments using cone data. So as you know, there are 3 analytical phases or steps for assessing liquefaction, either static or dynamic. First, you have to do what is called a susceptibility analysis. And actually, you see the term liquefaction screening in publications dealing with site characterization. And I'm going to be using the term liquefaction screening because that's the more common term that you see in site characterization publications. So basically what this first phase is that you say the soil behavior type and state in the ground. And by state, I'm talking about relative to the critical state density of the soil. Do I have the type of ground at this site that is at least susceptible to liquefaction? If it is, then you need to do what we call a triggering analysis that says, I need to do a site-specific assessment of the potential that some natural or anthropogenic or human-caused event during the design life of a specific structure could actually trigger liquefaction in the potentially liquefiable soils that I've already defined by my first phase of liquefaction screening, the susceptibility analysis. And then the third and final step is the consequences analysis. Okay, I have triggered liquefaction. I need to do in site and event-specific assessment of how liquefaction would affect the ground conditions and structure at a site. So what I'm saying is what you basically get for free as part of doing a basic site characterization using cone penetrometer data is for basically no additional effort or little additional effort, you can get a liquefaction screening. And this is really what makes piece of cone and seismic piece of cone sounding so indispensable, in my opinion, is that they're a cost-effective tool that, in addition to giving you many, many soil properties and parameters for general site characterization purposes, they will also give you the necessary properties and parameters for this first phase of liquefaction assessment, what we call liquefaction screening. So you basically get this first order assessment of liquefaction potential for little or no additional effort beyond the initial effort to perform basic site characterization that you need to do anyway. And if you identify any subsurface zones as potentially liquefiable, you can of course then follow this up with a more detailed site-specific triggering analysis. Well, I now want to go on to the second of 4 topics I'm covering in this phase 1 module, and that is geotechnical fundamentals. And these are things that we've all learned, but what I'd like to point out is maybe some things you've forgotten or some nuances that you were not previously aware of. The most important fundamental geomechanics concept I want to talk about that is relevant to deep foundations that are subjected to axial loading is the unique nature of the ultimate limit state of particulate materials such as soil compared to that of solid materials. Now, this difference was highlighted and discussed earlier in this presentation, but is really relevant to repeat here as it sets the stage for subsequent topics in this module that address various aspects of deep foundation ground interaction in detail. Now, there are multiple aspects of the behaviorally unique nature of the ultimate limit state of soil that are relevant to deep foundation elements. To begin with, the ultimate limit state of a solid material results in localized physical rupture of the material that is irreversible and thus permanently renders the material with zero residual strength at the point of rupture. Now, on the other hand, the ultimate limit state of soil consists of interparticle slippage with a mass of particles that is moving relative to a mass of particles that is non-moving. So there's no physical rupture involved with the ultimate limit state of soil, although certainly there can be some localized particle crushing that can occur. More importantly, the shearing resistance between the moving and stationary masses of soil never decreases to zero, but plateaus at some non-zero value that remains more or less constant regardless of the magnitude of relative displacement between the moving and stationary soil masses. Furthermore, research and experience have shown that all of the relative displacement between the moving and stationary soil masses is concentrated within a relatively thin, what we call shear zone or failure zone, that is very commonly and adequately modeled with acceptable accuracy as a zero thickness surface. Alternatively, when we have a mass of soil that is in contact with the surface of a solid material, the displacement of the soil mass is relative to the solid material or vice versa, and is usually assumed to occur along the contact surface between the two dissimilar materials. So as we know, the magnitude of displacement that occurs during the ultimate limit state of soil or a soil structure interface can vary over a very wide range and really depends solely on how much relative displacement is required before a new state of static equilibrium develops within the overall system, which then allows displacement to cease. For example, mobilizing the frictional resistance between a solid material and soil typically requires only several millimeters, a fraction of 1 inch of relative displacement, whereas certainly you can have a slope failure of a hillside that might result in the mass of soil above the failure zone traveling a significant distance all the way down the hill before it comes to rest. But regardless of how much displacement accompanies the ultimate limit state of a soil mass or a soil-solid interface, there is never a permanent lasting effect as there is with a solid material. Consequently, the particles within the quote-unquote failed soil mass can always be removed, rearranged, and reused if desired, with no permanent effect or visual evidence of the prior failure, other than any localized particle crushing that might have occurred. Now, in the case of a soil-solid interface, this also means that the ultimate limit state is fully reversible by simply reversing the direction of relative displacement between the solid material and surrounding soil, so that this interface can unfail, if you will, and then fail again, but in the opposite direction. Throughout this whole process, there's no permanent reduction in shear strength along the interface. This reversible process of achieving the ultimate limit state in either direction of relative displacement along a solid soil interface can in principle continue indefinitely. And I'm emphasizing this point obviously because of its relevance to deep foundations. So in summary and conclusion, the key point I'm trying to make here is that from a mechanistic perspective, the ultimate limit state, the failure state, if you will, of soil or a soil structure system such as exists with deep foundation elements has absolutely nothing in common with the ultimate limit state or failure of solid materials such as steel, Portland cement concrete, or wood that are used in engineered construction. This is because the failure or ultimate limit state of a solid material involves a physical rupture that's permanent and results in a complete loss of material strength at the point of rupture, while the ultimate limit state of soil or a soil structure system solely involves displacement. In my opinion, I think it's clearly illogical to design both solid materials and soil or soil structure systems using the exact same concepts in order to provide a margin of safety against acceptable material and system behavior. I mean, no one is arguing that we should not build safety into our systems. I mean, that's a given. That's not the issue here. What's an issue is how do we best build safety into a system? And the point I'm trying to make is that because of the totally different way that a solid material versus soil or soil solid interface reach the ultimate limit state or failure state, because of the total difference between the two, the way that we apply safety to these different systems should not be the same. Obviously, I'm making this point because there's a lot of people who feel otherwise. So, while it's logical to design structural systems involving solid material for the ultimate limit state, now whether allowable stress design or LRFD is better for this purpose, I'm not going to get into here. That's beyond the scope of this presentation. But it is very clearly illogical to always design soil or soil structure systems for the ultimate limit state. As in most cases, designing soil or soil structure systems based on serviceability is both more rational as well as relevant to system behavior from a modern 21st century design perspective. Again, just because we did things a certain way with deep foundations in the 19th century doesn't mean that 200 years later we should be doing things the same way. I would like to believe that we've learned a few things and gotten a bit of insight into things in the last 200 years. It's very clear that failure, if you will, of a soil or soil structure system only involves displacements. And what magnitude of displacement is acceptable for a given specific geotechnical or geostructural application is solely a serviceability or displacement issue. So the only logical conclusion I feel we can come to is that geotechnical and geostructural systems should in most cases be designed primarily for the geotechnical serviceability limit state displacements that is deemed acceptable for a site and structure specific application. Well, I now want to move on to the topic of deep foundation ground interaction, and as you can see, there's many subtopics and subtopics I'm going to be covering here. So let me start out with an overview of what I'm going to be talking about in this part of the presentation module. The interaction between a deep foundation element subjected to axial loading and the surrounding ground is a classic problem in soil structure interaction, in which application-specific force displacement relationships of all the relevant problem components first need to be defined. By the way, as an aside, I know there's a certain way of thinking that soil structure interaction means seismic loading. That's a fallacy. I know some people think that way. They're entitled to think that way. They're entitled to be wrong. But soil structure interaction is a much broader concept. So the unique solution for a given loading condition when soil structure interaction is involved is then determined based on satisfying both force and displacement equilibrium for all relevant problem components. Now, traditional deep foundation design for axial loading that's based on the geotechnical ultimate limit state assumes, or at least implies, the simplest force displacement relationship of rigid plastic behavior for all problem components. So this inherently removes displacements from the problem consideration and solution and makes the problem solution trivial, as only vertical force equilibrium needs to be satisfied. So changing deep foundation element design for axial loading to a geotechnical serviceability limit state basis thus requires developing appropriate force displacement relationships for all the problem components. So the point I'm making here is that, for the last 200 years, when all we considered was the ultimate limit state when designing deep foundations for axial load, we could ignore displacements because basically we were, if we didn't assume it outright, at least implying that the system had rigid plastic behavior. That is, there was no displacement until boom, almost until everything all of a sudden failed. Well, now if we want to change things to explicitly consider displacements, we need to develop appropriate force displacement relationships. And a good part of the rest of this presentation, both in this module and the Phase 2 module, is devoted to this discussion of how to develop an appropriate force displacement relationship for all the problem components. So first discussed in the following segment are the geotechnical resistant modes and mechanisms for a deep foundation element subjected to axial loading, as these modes and mechanisms are a common element whether or not displacements are considered, and regardless of the source of loads and displacements on a deep foundation element. I'm then going to follow up with a discussion of the different load and displacement sources on a deep foundation element. As I indicated previously, it's a lot more than just the external axial load as we've assumed historically. I will then touch on a proposed methodology and method for defining all the force displacement relationships necessary to obtain solutions for the axial load displacement behavior of a deep foundation element. And then I'm going to look at these relationships in greater detail in the Phase 2 module that will follow. So let me first discuss the geotechnical axial resistance modes and mechanisms. How does a deep foundation element resist axial loading, regardless of where the axial loads come from? The geotechnical axial resistance modes of deep foundation elements and the physical mechanisms involved in these modes need to be discussed in some detail due to the fact that there is compelling evidence that the actual physical mechanisms for the two traditional modes of shaft resistance due to sliding friction and toe resistance due to end bearing are significantly different than what has been assumed historically and portrayed in textbooks and other published works. For deep foundation elements with a depth-wise variable shaft perimeter that I refer to as tapered deep foundation elements in this presentation, there is a need to recognize the existence of a third axial resistance mode and physical mechanism involved. This third mode of axial resistance I call shaft resistance due to wedging, and it takes its name from the physical mechanism of advancing a wedge into a solid material. The two traditional modes of shaft and toe resistance and their respective physical mechanisms are discussed first before I move on to discussing this third mode that is only applicable to the special case of tapered deep foundations. I'm going to discuss toe resistance first, as it also provides, as you'll see, a modern theoretical framework for understanding shaft resistance. So we're talking now about the unit toe resistance, stress at the toe of a deep foundation element. and the resultant force, capital R sub T, toe resistance. Now, historically, toe resistance due to end bearing was viewed as a straightforward application of traditional bearing capacity theory. As you know, it was one of the first things that Terzaghi developed when he was developing modern soil mechanics in the 1920s. However, when it comes to deep foundations, very often we use a different solution due to the unique quote-unquote deep nature of deep foundation applications. This is just a sampling of some of the more common solutions that have been used with deep foundations for bearing capacity. This is Terzaghi's mechanism in his 1943 textbook, Meyerhoff in the early 1950s, Skempton also and colleagues also in the early 1950s, Berezantsev in the early 1960s, and Vesage also in the early 1960s. This sole approach to the problem has now been replaced with four broad categories of alternatives. Alternative number one is the continued use of traditional bearing capacity theory, and this is the traditional three-term NC, NQ, and gamma equation. And of course, you have your choice of solutions. I've shown you several of them on the preceding slide. And this is all based on rigid plastic soil behavior and is governed by vertical effective stress at the deep foundation element toe. Alternative one is similar. Use a classical solution, but the three terms are modified by what we call compressibility or rigidity factors. And this is based on the research of the late Professor Fred Kulhawy, who demonstrated that soil compressibility should not be ignored in deep foundation engineering applications. Now, Terzaghi himself noted that with shallow foundations, there were some cases, for example, on loose sands, where soil compressibility needed to be considered. But in general, with shallow foundations, we can ignore soil compressibility, and the rigid plastic soil behavior assumption is adequate. However, Kulhawy showed pretty conclusively that it is never adequate with deep foundations. Alternative number three is to use an alternative bearing capacity solution, such as Vesage's spherical cavity expansion model that includes soil compressibility, as well as the more recent NTH method that was developed in Norway. And these all demonstrate that horizontal effective stresses govern behavior. And this is a real paradigm shift that we'll explore in some detail. And last but not least, we have the ever popular none of the above. And this is the position that's been taken by Fellenius for many years. And Fellenius has adopted the extreme position that geotechnical ultimate limit state simply never develops or exists at the toe of a deep foundation element. And he postulates that toe resistance just simply exhibits some ill-defined load settlement behavior ad infinitum. However, if you read Fellenius's work, as I have for many years now, you'll find that he is a bit inconsistent, because in some of his published work he implies that, well, yeah, the ultimate limit state, geotechnical ultimate limit state really does exist beneath the toe of a deep foundation element. Now, I've been researching deep foundations now extensively for several decades, and my personal conclusion is that the physical mechanism of what happens at the toe of a deep foundation element is nuanced. Although I think it's pretty clear that Fellenius's opinion that the geotechnical ultimate limit state does not exist is fundamentally flawed, and I think we can dismiss that outright. There is some sort of ultimate limit state of failure that occurs at the toe of a deep foundation element, but the details are certainly open to opinion. I think Fellenius' opinion that the deep foundation toe resistance always continues to increase with increasing toe penetration in some nonlinear manner is incorrect when you view it from the perspective of, say, tip resistance as measured in cone penetration test, where Q sub C at the tip of a cone penetrometer can increase, can decrease as the cone advances in the ground. It really depends on the nature and consistency of the soil encountered beneath the tip of the cone penetrometer. I think the genesis or source of Fellinius's flawed perceptions of toe resistance in deep foundations is related to the scale of his observations. He generally only looks at a few tens of millimeters, perhaps a couple of inches, in the instrument and static load test. When you look at displacements on a larger scale, it's pretty clear that there is some sort of ultimate resistance at the toe. So I've concluded long ago that all indications are that the geotechnical ultimate limit state or bearing failure does indeed occur beneath the toe of a deep foundation element, but the nature and consequences of this failure is very, very different when you compare that to the bearing capacity failure of a shallow foundation. And that's because for shallow foundations subjected to a downward axial load, for example, spread footing supporting a single building column, the physical mechanism of end bearing beneath the footing is really the only significant geotechnical resistance of that footing. Whatever vertical shear happens along the sides of the footing is really quite negligible in magnitude by comparison. So as a result, there is no redundancy in the overall geotechnical resistance for a footing. And bearing failure of that footing typically results in large-scale vertical displacements of the footing, development of a failure surface that in many cases extends up to the ground surface. This is also going to be accompanied by large-scale vertical displacements of the portion of the structure that is supported by that footing, with the concomitant partial or total collapse of that structure. So certainly there's many case histories of structures that have failed because they were supported on spread footings, and that spread footing had a bearing failure. So maintaining an adequate margins of safety against the geotechnical ultimate limit state for shallow foundations is certainly justified in all cases. On the other hand, for deep foundation elements, end bearing is not the only geotechnical resistance mechanism to axial compressive loads, as there's always redundancy in the geotechnical support supplied by the deep foundation shaft. In addition, the ultimate limit state failure surface that develops beneath the toe of a deep foundation element is confined to the region around the toe, and I'll show you some test results that are pretty conclusive about that. So really what happens is you have what we call contained plastic flow around the toe of a deep foundation element where the ultimate limit state has been reached. And this is very similar to developing a plastic hinge in a redundant structural member. You know, if you have a redundant structural member, just because you develop one plastic hinge does not necessarily mean that member is going to collapse. And the same thing is true of a deep foundation element. So if we put all these facts together, the point I'm trying to get at here is the geotechnical ultimate limit state for a deep foundation element and end bearing has really very different implications compared to the bearing failure of a shallow foundation, as the geotechnical ultimate limit state for a deep foundation end bearing simply results in a condition of continued toe resistance under additional settlement. So what I'm getting at is that even if the soil beneath the toe of a deep foundation element fails, you don't lose the strength. You may plateau the strength, or the strength gain may be very small with additional settlement, but you're going to have some continued resistance at the toe with additional settlement. So this resistance beneath the toe of a deep foundation element that has failed, I mean, if you keep on letting it settle, it may increase, may decrease, may stay the same. It really depends on the site-specific soil conditions and the magnitude of settlement that we're talking about. Note that this is broadly similar to what happens behind an earth retaining structure when we mobilize the active earth pressure state, which, as I pointed out earlier in this presentation, is a failure or ultimate limit state condition. I mean, if we have a rigid retaining wall where we mobilize the active earth pressure state, that wall may continue to move, but that earth pressure is going to stay more or less constant. Or if the overall soil earth retaining structure system remains stable, just because we have the soil behind the wall has failed does not have any negative consequences. In fact, when we design freestanding rigid retaining walls, we actually design them to fail geotechnically. So in summary, the calculation of the geotechnical ultimate limit state beneath the toe of a deep foundation element remains a requirement, both in design practice and academic research. So the only remaining question is how to best accomplish this from the three alternatives, 1, 2, and 3, that I listed previously. Well, again, I've been looking at this now for several decades, and my conclusion is that I tend to use a combination of alternatives 2 and 3. Alternative 2, which is conventional bearing capacity solution with rigidity or compressibility factors. And alternative 3 is Vestige's spherical cavity expansion model. I have looked at the Norwegian NTH method quite a bit. It's an interesting method and can provide some reasonable results. But there's a little bit more, I hate to say guesswork, but a little bit more difficulty in selecting the input parameters for the NTH method. So my practice now for a very long time is that when I'm calculating the ultimate geotechnical resistance of a deep foundation element in compressive loading, I calculate the toe resistance a couple different ways, and I found that in a given application, these different ways tend to produce results that are very close in magnitude. So I like computing the toe resistance a couple ways and using the calculated results to basically verify each other. I want to discuss Vestige's spherical cavity model in a bit detail. Simply because the model and its solution are not widely known. And also, it provides some interesting insight that I think is useful for some of the things I'm going to discuss later on in this segment. So this is, I'm going to be showing you this figure and similar figures several times in this presentation. Let me explain what's going on here. In some of the early laboratory testing of geotechnical systems, a very common test procedure was to embed layers of lead shot. Those are these dark circles that you see here. So spherical pieces of lead shot were deposited in horizontal layers in a body of soil, and usually that soil was sand, as it is here. And the reason for doing that is the researchers would take x-rays periodically, and of course the lead would show up very high contrast, as you could see here in an x-ray. So by following the pattern of the lead shot, which originally was a nice neat horizontal layer, as you see down here at the bottom, for example, you could see patterns of displacement and deformation within the soil. So that's what we're looking at, this sort of thing we're looking at here. So think of these traces of these dark gray dots as basically patterns of displacement and deformation in the soil. And in this case, it's under the loading of a cylindrical element that was modeling a deep foundation element. Now, traditional bearing capacity solutions that are functions of vertical overburden stress at the deep foundation element toe don't capture the actual wedge-shaped failure mechanism that is observed develop beneath the toe. So you can see here from the lead shot that beneath the toe, we develop a soil wedge that actually becomes pretty much like the pointed tip of this deep foundation element. And Vesage superimposed on this a failure mechanism based on spherical cavity expansion. So Vesage found that the actual failure mechanism is reasonably approximated by spherical cavity expansion model, and he first proposed this, as you could see, in the 1970s. The really interesting outcome of this Vesage's research is that spherical cavity expansion involves a horizontal overburden stress that depends on K sub O, the coefficient of lateral earth pressure at rest, through this well-known relationship between horizontal and vertical effective stresses. The interesting thing is that in the following decades, the dominance of KO and horizontal stresses for toe resistance was corroborated by research involving the cone penetrometer, where the uncorrected tip resistance QC. Now the QC in cone penetrometer is essentially the what I call R sub T, the toe resistance in a deep foundation element. They are conceptually identical. So research with the cone penetrometer that occurred in the latter decades of the 20th century into the 21st century showed unequivocally that it was the horizontal stresses that govern the tip resistance, not the vertical overburden stresses at the tip. So that's a very powerful conclusion. What we're saying is that when you push a right circular cylindrical object in the ground, now whether this object is a deep foundation element under axial compressive loading or a cone penetrometer being advanced in the ground, whatever the object is irrelevant. The point is that the resistance at the tip or toe of that element is going to be governed by horizontal effective stresses. And that's the main thing I want you to get from this discussion at this point, that whatever resistance you get at the toe of the deep foundation element, which is the same conceptually as the tip of a cone penetrometer, that resistance is going to be governed by horizontal effective stresses, not as vertical effective stresses as was thought originally, or you might think intuitively. So as I said, K sub O and horizontal stress dominate all aspects of deep foundation element toe resistance. Now, although the Vesage's spherical cavity expansion model and the solution were put forth almost 50 years ago, the practicality of using this model in the present is due in no small part to the tremendous advances in site characterization, especially due to the piezocone, the seismic piezocone. This is similar to what I talked about earlier in this presentation, that there's a lot of interesting solutions that people have developed, but it sometimes took years or decades for the peripheral technology to catch up to be able to allow us to use those solutions. The example I used earlier was my own research with subgrade models beneath, say, a mat or raft foundation. And here we're talking about toe resistance of deep foundation elements. So the implication of the spherical cavity model is that horizontal effective stresses are more important than the vertical stresses at the toe of a deep foundation element. And as a result, estimating K sub O prior to deep foundation element installation is an essential problem parameter for forecasting deep foundation toe resistance, as this is the starting point for the increase in horizontal stresses that results from the spherical cavity expansion model. And this is why I said in the segment earlier in this module about site characterization, when I was highlighting the two things that I feel are most important from site characterization. One I said was stress state. The stress state explicitly in terms of case above, the coefficient of lateral earth pressure at rest. And now I've illustrated to you why that is such an important parameter to estimate. And I will show you some examples from Kennedy Airport of how this all comes into play. The nice thing, of course, is that piezocone, seismic piezocone soundings provide the necessary data that can be interpreted to provide estimates of Case-Abo. Case-Abo is a notoriously difficult soil property to estimate, but we can make some pretty good estimates from cone penetrometer, post-processing cone penetrometer data nowadays. Now, up to this point, the spherical cavity expansion model has been discussed for its primary use to date to forecast deep foundation tow resistance under post-installation externally applied axial compressive loads. However, there's no reason why the spherical cavity model can't also be used for understanding what does or does not happen during the deep foundation installation process. And specifically, it would appear that the spherical cavity expansion model is valid for piles that are installed using traditional impact driving as well as jacking. Jacking piles in the ground does not appear to be very common in the US at the present time, but there are parts of the world where it is a common methodology for installing a pile. So the implication is that as a pile continues to be advanced by driving or jacking, it leaves the ground behind the toe and thus along the shaft with a horizontal effective stress that is greater than that which existed prior to installation. On the other hand, for a bored pile or drilled shaft where the soil is excavated during the installation process, the geotechnical ultimate limit state beneath the toe does not develop as it does with driving or jacking a pile in the ground. So excavation for the bored pile or drilled shaft is advanced in the ground. The horizontal effective stress along the shaft are at best the same as they were prior to installation. And at worst, the horizontal stresses are less due to stress relief around the excavated hole. This extended application of the spherical cavity expansion model to help us illustrate and understand what happens during deep foundation installation process naturally leads into the discussion of the geotechnical axial resistance mode of shaft resistance due to sliding frictions. At this point, I'm going to limit it to deep foundations with a depth-wise constant perimeter. Okay, I'm now going to discuss the physical mechanism of shaft resistance due to sliding friction. That is, strictly speaking, only applicable to deep foundation elements that have a depth-wise constant perimeter. The physical mechanism has historically been assumed to be that the DFE shaft slides vertically relative to the surrounding soil particles, and these soil particles are implied, if not explicitly assumed, to be stationary in space. And this sliding occurs along the nominally planar interface defined by the exterior of the deep foundation element shaft. This physical mechanism is typically modeled mathematically as a very classical application of what is called Coulomb dry friction, with the interface shear stress of the soil acting on the deep foundation element shaft in a direction opposite that of the axial load applied at the head of the deep foundation element. So using the terminology and notation defined earlier in this presentation, the interface shear stress that acts in response to an externally applied load at either compression or tension is called the unit shaft resistance. So unit shaft resistance can occur in either direction. It depends on the direction of the externally applied loading. Now, one persistent point of disagreement in the published literature over the years that continues to the present is whether or not the unit shaft resistance is the same in compression or uplift. for a given deep foundation element. The assumption I've made in this presentation is that it is the same regardless of the direction of the applied load. So shaft resistance due to sliding friction for compressive loading, the positive shaft friction mobilized as resistance, and we call this the unit shaft resistance in this case. And we have the resultant force that we call the shaft resistance. Now, if we have tensile or uplift loading, the negative shaft friction is mobilized as resistance. So both positive and negative shaft friction can be considered to be resistance. It depends on the direction of the externally applied load. Now, one of the most significant advances in the state of knowledge concerning shaft resistance has been the result of many years of seminal research that was performed at Cornell University under the direction of Professor Kolhawy. And you're going to see this ties into what I just talked about a little bit earlier with the case of O parameter. Now, it's long been known that shaft resistance is proportional to the horizontal effective stress, and the horizontal effective stress is proportional to K sub h, a dimensionless coefficient of lateral earth pressure acting along a deep foundation element. Now, the really seminal insight of the research of Kolhawy and his associates showed that this K sub h parameter is better expressed as the product of two parameters. One is the ratio of KH to KO times KO, where K sub O is the coefficient of lateral earth pressure at rest prior to deep foundation installation or construction. And the ratio KH over KO reflects the change in lateral earth pressure that is related to the deep foundation installation or construction, as well as loading that can, in the most general case, occur in two stages. So what I'm saying here is that this ratio, KH to KO, reflects the type of deep foundation element, how it was inserted or constructed in the ground, and it can further be broken down into coming from two different components or stages. Stage one, which is typically the more dominant, depends on the deep foundation element type and its method of installation, as I discussed previously with the spherical cavity expansion model, helping to visualize the deep foundation installation process. Stage two, which may or may not occur, is related to post-installation axial loading, depending on the specific analytical method in which this term is used. This may seem a little bit confusing at this point, but I will be illustrating this multiple times throughout the remainder of this presentation. All I'm saying here is that when we look at what is the shaft resistance of a deep foundation element, all I'm saying is that it develops in two stages and therefore comes from two components. The first stage is how do you insert this deep foundation in the ground or construct this deep foundation in the ground. And the second stage, which may or may not occur, and I'll show you when it does occur, when it doesn't occur, it relates to the post-installation axial loading. So we've seen this diagram before. I'm now going to illustrate it in a little bit different context. And this table is the result of work done by Kolhawy and associates about 40 years ago. What I'm showing you here in this table is the KH-KO ratio. And from Kolhawy's research outcomes, it's clear that K sub O prior to deep foundation installation, as well as the KH-KO ratio that reflects the aggregate result of the type of deep foundation element and the method of installing that deep foundation, Each play an outsized role in the resulting value of KH and, as a result, the shaft resistance due to sliding friction. All right, you'll notice here for drilled shafts that Kolhawy and his associates found that the ratio could be anywhere from less than 1 to 1. What this is saying is that after you've installed a drilled shaft or board pile in the ground, the horizontal stress in the ground, as defined by K sub H, can be less than or at best equal to the K sub O that existed in the ground prior to installing that drilled shaft. And the reason it can be less than K sub O is because, as I noted earlier, when you construct a board pile or drilled shaft, you excavate the soil. And this excavation can cause stress relief around the shaft as is being constructed. And this stress relief can get locked in so that the horizontal stresses you're left with after construction are actually less than what existed in the ground prior to construction. Very different if you have driven piles, where, as we saw previously, when you have a driven pile or a jack pile, you create this wedge beneath it and it expands laterally and creates these spherical cavities on either side of the wedge. The KH to KO ratio is typically greater than 1. And the reason it's greater than 1 is simply because in the process of driving or jacking this deep foundation element in the ground, you've created large horizontal stresses at the toe, and as the toe continues to go down, those large horizontal stresses remain acting along the shaft. So these findings are one of the several reasons for earlier in this presentation highlighting really the mission critical importance of determining the pre-construction KO in the ground as part of the site characterization process. Because whenever you're talking about deep foundation elements subjected to any type of axial loading, the horizontal stress in the ground prior to installation or construction of that deep foundation element is really the starting point for the horizontal stress K sub H you're going to be left with after construction. So really, again, if I can frame Kolhawy's work in a different way, what he was saying is that when you construct a deep foundation element, that the ratio KH to KO, which reflects the type of deep foundation element and how you got it in the ground or constructed it in the ground, it simply builds on the horizontal stress on the ground that existed prior to construction. And this is why K sub O prior to construction is such a really important parameter for deep foundations. Now, as I noted previously, of relevance to the present discussion is that it is at least implied, and at least as illustrated in textbooks and design manuals, even if you don't explicitly assume it, that as a deep foundation element slides vertically relative to the adjacent ground in the traditional mechanism of shaft resistance due to sliding friction, that the ground around the deep foundation element remains undeformed vertically and horizontally. All right, we've all seen the figures in textbooks and design manuals where the deep foundation element under externally applied axial load is assumed to slide neatly along the soil, and the soil kind of remains fixed in place. And this physical model is consistent with Coulomb dry friction model that, as I noted earlier, has historically been used as the physical and mathematical model for calculating deep foundation shaft resistance due to sliding friction. As we know, Coulomb-drive friction is a simplistic physical model. It's based solely on forced equilibrium between two rigid, that is, non-deforming bodies, with one body representing the soil mass in this case, spatially fixed at all times, and the other body, representing the deep foundation element shaft in this case, sliding relative to the fixed body along and parallel to an assumed planar contact surface between the two bodies. All right. Early in our undergraduate education, we've all seen these problems, maybe even in a physics course before a civil engineering course, of a block sliding on an incline. All right. So really what I'm talking about here is that block sliding on the incline. Well, the incline is the soil, the block is the deep foundation element, and the contact between the two is where the deep foundation element shaft is in contact with the soil. Now, rigid plastic shear resistance is assumed along this planar contact surface. And as I noted previously, this means there's no displacement between the two rigid bodies up until the maximum shearing resistance, called the static friction, along the planar interface is reached. Then all of a sudden, that block starts sliding down the incline at some unspecified magnitude by the residual shearing resistance that's called kinetic friction. That's very nice. Very nice model. Unfortunately, it's all wrong. And research has shown that the simplistic physical model of shaft resistance due to sliding friction is completely incorrect. A fact that's been noted by several researchers over the years and summed up in this quote by Felinius. I'll give you a second, you can read it for yourself. The bottom line is, in reality, the load transfer between a deep foundation element shaft and adjacent ground occurs as vertical shearing within a zone of soil adjacent to the shaft, not on a nice, neat, zero thickness planar interface, but within a zone of soil, with the ground adjacent to the shaft vertically deforming and settling along with the shaft as a result of this vertical shearing mechanism. And this behavior has been found independently and consistently by researchers for over 60 years. This is not a new idea. This knowledge has been around for a surprisingly long time, yet seems to have been consistently overlooked or ignored in textbooks and design manuals. Again, these are two figures from this work published by Rubinsky in '63. And again, these dark spheres are the lead shot showing the deformed pattern of soil. So what we're saying, and you could see that as we apply an axial load to the shaft, the ground does not remain fixed in place as we traditionally assume. Rather, it's going to deform, and it's going to deform within a zone adjacent to the shaft of the deep foundation element. And similarly, we could see this over here. This is a little bit darker, a little bit more difficult to see. But again, we see there is a zone of shearing that occurs. So essentially what we're saying is, if we load a deep foundation element in axial compression, it's literally going to pull down some zone of soil around that shaft. This is more recent research, and in this case, the researchers, instead of using a lead shot and taking x-rays, they used another very common technique, that is, by using layers of colored sand. Initially, these layers are, both the dark and light layers are perfectly horizontal, as you could see down here. But again, you could see that as this figure is kind of cluttered, this was in the original figure, all this clutter. But you could see that the band of colored sand is deformed around the shaft of the deep foundation as it is loaded in axial compression. All right, so the deep foundation is kind of dragging down, if you will, some zone of soil around it. Despite the fact we've known about this for over 60 years now, about what the actual physical mechanism of DFE shaft resistance is all about, there does not appear to have been any widespread recognition of it, no less development of a practice-oriented physical and mathematical model for the shear zone that develops around a deep foundation shaft that will allow us to calculate unit shaft resistance. So the state of practice for the present time remains that when you calculate the unit shaft resistance, we still use this traditional Coulomb frictional model along a nominally planar deep foundation soil interface. That having been said, the fact that in reality we have a shear zone, not a shear surface, and we have vertical displacement and deformation within the soil around a deep foundation shaft, we haven't abandoned this idea completely. As you will see, especially later in this segment, as well as in the next module on phase 2, we put this concept to great use in developing a model for analyzing deep foundation settlements. Specifically, the observed behavior of the way soil deforms around a deep foundation element shaft is central to a theory of elasticity model called the concentric cylinders model that is the theoretical core of several aspects of deep foundation behavior that are discussed in the phase 2 module of this presentation. Now, it's important to recognize that independent of the analytical model used for forecasting deep foundation shafts and toe ultimate resistances, it's long been known that, first of all, the magnitudes of relative deep foundation ground vertical displacement that are required to mobilize these two resistance modes are very different when you start from the baseline of zero displacement and zero resistance for each mode. All right, I mean, we all know by now that you need relatively small magnitudes of displacement to mobilize shaft resistance due to sliding friction, proportionally much greater displacement to mobilize toe resistance. So these facts appear to be reasonably well known and implemented into state of practice in various ways, at various degrees. Less well known is the fact the traditional assumption that is almost universally made in both practice and research that after we install a deep foundation in the ground or construct it in the ground, both the shaft and toe resistances start from a baseline of zero resistance. This is incorrect all the time to varying extents. It really depends on the specific type of deep foundation element and, more importantly, how it was installed in the ground. And I'm going to say a lot more about this subsequently. Unfortunately, despite the fact that we've known since at least the 1950s that when you install a deep foundation in the ground, especially a driven or jack deep foundation, we have what we call residual loads. Okay? So what we're saying here is that after you've installed a deep foundation in the ground, although there is no external load on that deep foundation element, there are loads within that deep foundation element shaft in the ground. There are stresses between the deep foundation element and the ground. And as I said, we've known about this. It's been talked about in the literature since at least the 1950s. Yet, surprisingly, it appears to be unknown or ignored if known by both design professionals and academicians alike up to the present, with relatively few exceptions. The point I'm making here is that even for the current state of practice, that is based primarily on the geotechnical ultimate limit state for designing deep foundations for axial load, the influence of vertical displacements on the behavior of deep foundations should not be ignored. The final topic under this segment of geotechnical axial resistance modes and mechanisms that I want to discuss is the third resistance mode for tapered deep foundation elements, called shaft resistance due to wedging. The load-bearing benefit of tapered deep foundation elements that I refer to generically in this presentation as taper benefit under externally applied axial compressive loading was recognized at least as far back in the 1950s. And I'll give you a minute to read this quote by the late Professor Ralph Peck, made in the 1950s. Now, I've covered the topic of taper deep foundation elements in extensive detail, both in a relatively recent scholarly monograph as well as a YouTube presentation that summarized the monograph. So I'm only going to touch on some key concepts and outcomes in this presentation. But if you want more information on the subject of taper deep foundations, I would direct you to my monograph as well as this YouTube presentation. So let's talk about the physical mechanism of wedging. And I want you to focus on an arbitrary fixed plane in space when I start this animation. Okay, if we focus on this fixed plane in space, essentially what we're seeing is as this wedge is advanced into the ground, the horizontal stresses at this plane, or at the level of this plane, are increasing. So wedging involves a simple basic problem in physics that uses the geometry of a wedge-shaped solid object to transform a downward acting force, right? That's what's driving it into the ground here, into one with a horizontal component that increases in magnitude as the wedge advances. I want to talk about another phenomenon called cylindrical cavity expansion. And again, I would ask you to focus on an arbitrarily fixed plane in space. Cylindrical cavity expansion simply means that we have a cylinder that we expand radially. And as we expand the cylinder radially, I think you could see that obviously we are increasing the radial stresses around this cylinder. Now, as you probably know, cylindrical cavity expansion has been used for decades now to model a variety of geotechnical phenomena and applications, especially the pressure meter test. All right? Cylindrical cavity expansion is a very good physical and mathematical model for what happens during the expansion phase of a pressure meter test. Well, we can put these two things together, and what I'm pointing out to you here is that we could use cylindrical cavity expansion to model the phenomenon of wedging and apply that to driven tapered piles. So putting these two things together, again, focusing on a fixed plane in space, what I'm saying is that think of the cylindrical cavity expansion and notice that cylindrical cavity expansion for that arbitrary fixed plane in space, cylindrical cavity expansion does a very good job of modeling both physically and mathematically what happens during wedging, that is, what happens when you either drive a tapered pile into the ground, or if you have a tapered deep foundation element, you load it in axial compression. So we see for a driven pile, this wedging occurs in two distinct cumulative stages. I told you we'd come back to this two-stage concept. Stage one is the increase in radial stress that occurs during installation. All right? Imagine you're driving a tapered pile into the ground. During the process of driving, I think you could see that the horizontal stress acting on that tapered pile will be increasing continuously. After that pile is installed in the ground, and now we're subjected to post-installation externally applied compressive loading, we're going to be expanding that wedge even more, and we're going to be increasing the horizontal stress even more, even as we load that taper-driven pile. Well, as I noted a few slides ago, the load-bearing taper benefit of tapered deep foundation elements was recognized at least as far back as the 1950s for driven piles, and was first quantified for driven piles by the seminal work of Nordland around 1960. However, the fact that what we call taper benefit develops in two stages from two distinct components, stage one installation, stage two post-installation compressive loading, was not recognized by Nordland nor in any subsequent researchers, as best as I can determine, until I pointed out this two stages of taper benefit in my monograph on tapered deep foundations that was published in 2020. So this is important because we have a relatively large body of published information relative to tapered deep foundations that unfortunately is at best incomplete and at worst misleading for both design professionals, academic researchers, because this two-stage nature of taper benefit was not recognized and defined until I published my monograph 5 years ago. For example, if you look at Nordland's analytical method for resistance forecasting, which is only applicable to driven piles, he lumps the stage one and stage two taper benefits together, although in all fairness, I don't think he really appreciated the fact he was doing that. This combining of the two stages of taper benefit is not unique to Nordland's method, and in fact, it's a feature of most resistance forecasting methods for taper deep foundation elements. Separate from that, in 1993, there was a very interesting ASE journal paper by Kodakara and Moore, and they presented a very elegant theoretical solution for taper deep foundation elements loaded in compression. But when you read that paper very carefully, you realize that their results are only applicable to the stage two taper benefit that is derived from post-installation externally applied loading. So their published results, as elegant as they are quite incomplete. And that means the conclusions and the implications they drew in their paper are, I think, misleading. And this is because they assumed that in their theoretical development that the post-installation pre-applied loading horizontal earth pressures acting along a tapered deep foundation element shaft were known beforehand, but they gave you absolutely no idea as how you were supposed to know or to be able to calculate what these were. Even worse, they assumed that these post-installation horizontal stresses were constant with depth along a shaft, which is really quite incorrect. It's interesting that the only case history that they used to show you the accuracy of their theoretical work involved a very short 4.5 meter, 15-foot long bored pile or drilled shaft that had very minimal geotechnical data. So what I'm getting at is what Kodakar and Moore did is they showed that, gee, our solution works. Well, it works for something that only has stage 2 taper benefit. I mean, when you excavate a drilled shaft or a bored pile in the ground, you get the stress relief. You don't get any increase in radial stress due to the installation process. There is no stage 1 taper benefit with a drilled shaft. Well, unfortunately, there were other researchers, El Nagar and his colleagues in Canada, as well as researchers in Japan, that used the work by Kodakar and Moore. And as a result, this follow-on work suffers from the same incomplete nature of the original Kodakar and Moore work. Again, the point I'm making here is that taper benefit has multiple components that accrue in 2 stages. And thus, how much taper benefit you get is very, very dependent on both the type of deep foundation element and, more importantly, how you install that deep foundation element in the ground. If you have a pile that is driven or jacked in the ground, you're going to get a tremendous taper benefit. Most of that coming from stage 1, the installation process, when you're creating and expanding this cavity in the ground due to wedging. Whereas with a drilled shaft or bored pile, there is no stage 1 taper benefit. You get a very slight taper benefit when you load it in axial compression, but it's really quite small compared to the taper benefit of a driven pile. Another fact that doesn't appear to be recognized in the published literature until I published my monograph 5 years ago is that driven tapered piles still retain a significant taper benefit if subjected to post-installation tensile or uplift loading. I can't tell you how many times in my professional career I've recommended driven tapered piles to a client. And they say, well, you know, they're great, but gee, in this particular structure, there's going to be uplift loading, and tapered piles have no uplift resistance. They just magically pop out of the ground. Well, the reality is nothing could be farther from the truth. And this is because the shaft resistance of a tapered deep foundation element does not suddenly disappear when you apply a tensile or uplift load to it. And as is often simplistically and incorrectly assumed. Rather, when you apply uplift loading to a tapered deep foundation element, all you do is you somewhat reduce the stage 1 taper benefit that accrued during installation. And if you don't want to believe me, the fact that driven tapered piles exhibit a significant resistance to tensile or uplift loading was demonstrated unequivocally by field research in Norway on full-scale piles, and it's reported in the published literature over 50 years ago. Okay, I'll give you the citation a bit later on another slide, but what they did in Norway over 50 years ago was they drove some taper piles in the ground, and they loaded them in compression and they loaded them in uplift loading, and they found that and they also installed some piles that had a constant diameter. And it's very interesting, what they found was that the tapered piles had essentially the same uplift resistance as the constant diameter piles. And it was very surprising. I remember when I first read the paper, but when you get into it, you understand why that happens. And this observed behavior is really understood by a physical mechanism that I call unwedging. Maybe it's not an elegant term, but it really does describe what's going on. You can think of unwedging as something that is physically and mathematically modeled using what is called cylindrical cavity contraction. So let me illustrate an animation that will show you unwedging as it applies to tapered piles. So again, I'll ask you to focus on an arbitrary fixed plane in the ground. And essentially what I'm showing you here is if we now have this wedge and now we try to pull this wedge out, notice that as we do that, the horizontal stresses don't instantly drop to zero. They simply decrease in a continuous manner. But notice that they decrease from a elevated state, okay? Because when you drove this wedge in the ground, you created very large horizontal stresses, as I showed you earlier with the animation for wedging. So because you have very large stresses acting on this wedge already, when now you unload this wedge a little bit, all you're going to do is you're going to reduce these horizontal stresses a bit. You're still going to have significant resistance to pulling this wedge out of the ground. And believe me, any of you who have ever split firewood using the old-fashioned way of a steel wedge and a sledgehammer, which I did many a time in my younger days, you know, once you've driven a wedge into a piece of wood, try pulling that wedge out by hand, okay? Lots of luck. You can't do it. So, as I said, horizontal stresses do not suddenly decrease to zero as uplift loads are applied to a wedge. Uplift loads the horizontal stresses only decrease slightly from the elevated level due to the stage 1 wedging that occurred during installation. And again, I refer you to the Holmen Island, Norway, 1969 Norwegian Geotechnical Institute test pile program. The paper on this is in Literature International Conference, a paper by Gregerson et al. In the 73 International Conference. And they showed unequivocally that the tapered piles had uplift resistance comparable to otherwise identical constant diameter piles. It's essential to treat shaft resistance of a deep foundation element that occurs due to wedging as being distinctly different from shaft resistance due to sliding friction, as there are significant differences in the magnitudes of the lateral earth pressure coefficient KH that develops in each case, and as a result, the unit shaft resistance, which of course is linear proportional to the case of H. Now, during deep foundation installation, for a driven tapered pile, the horizontal stresses acting along the shaft-sole interface that contribute to post-installation shaft resistance continue to increase behind the toe as the result of additional what I call stage 1 cylindrical cavity expansion. On the other hand, for a constant perimeter-driven pile, the horizontal stresses remain constant as there is no further cavity expansion. All right, once you generate some horizontal stress when you drive the pile toe, there is no further increase in horizontal stress behind the toe. Now, during post-installation axial compressive loading, for a driven tapered pile, the shaft resistance continues to increase as the pile settles, as we now get what I call stage 2 wedging, causes additional cylindrical cavity expansion and concomitant increases in horizontal stresses around the pile shaft. And I'll point out that cavity expansion does not reach a limiting pressure until settlements well beyond those that occur under service loads. I'm sure you're familiar from pressure meter testing that there's what's called a limiting pressure. When you expand a cylindrical cavity at some point, the pressure does not increase anymore. You reach a limit. Now, for constant perimeter-driven piles, the horizontal stresses along the shaft remain constant as the pile settles under applied load. Shaft resistance due to sliding friction maxes out under relatively small settlements, and as we know, can actually decrease with further settlement as shear strength transitions from peak to constant volume or critical state values. These are a lot of words, and I think the best way to understand these words is to just look at some simple animations that compare a driven tapered pile and a driven constant diameter pile. So again, we know that shaft resistance is proportional to the horizontal earth pressure coefficient KH, which is the product of two parameters. The KH-KO ratio, which essentially says how does KH change relative to the pre-construction KO as I install the deep foundation element. And KO, of course, is the pre-construction KO in the ground. Again, the work of Kohawi and his colleagues at Cornell showed that for shaft resistance, the shaft resistance after you install a deep foundation element in the ground always is relative to the horizontal stresses that existed in the ground beforehand. And that's what this KH-KO ratio is illustrating. So for shaft resistance due to sliding friction, this KH-KO ratio, once you create it as you drive the toe in the ground, remains constant. Okay? So as we continue to drive a constant diameter pile, for example, the horizontal stresses are going to remain constant. If we load that pile on axial compression, the horizontal stresses are going to remain constant. Now, if we have a tapered driven pile, this KH-KO ratio is going to increase. It's going to increase during installation, and it's going to increase it after installation when we load it in compression. All right, so look at these two side by side, and I think these animations really illustrate the point I'm trying to make. Whether you're installing these in the ground or after installation you're loading them in axial compression, I think it's qualitatively obvious what the horizontal stresses are acting along the shaft of each of these deep foundation elements. Okay? So the behavioral difference that these animations are showing you exists both during driving, which is what I call stage 1, as well as under post-installation compressive loading, what I call stage 2. And again, if we have post-installation uplift or tensile loading, as I've shown you earlier, the tapered pile is not going to lose very much horizontal stress. Let me illustrate some of these concepts with some case history data. I've been involved with Kennedy Airport since 1972, and I've been fortunate to have access to some very high quality data for different types of deep foundations installed there and load tests performed there. This is a figure that first appeared in my monograph on tapered piles in 2020. And what I'm plotting here is a parameter that I came up with I call compressive resistance efficiency. And this is the maximum applied load, in this case in axial compression, on a deep foundation element divided by that volume of the pile. And I non-dimensionalize this quantity by dividing it by the unit weight of water. So this is a dimensionless parameter. And in simple terms, the larger the value of CRE, the more efficient that deep foundation element is at supporting axial compressive load. So it simply says you could put more load on there for a given volume of, in this case, pile material. And on the horizontal axis, I'm plotting taper angle, and there have been a variety of tapered piles, timber, monotube, taper tube, that have been installed at Kennedy Airport since the airport was first constructed in the 1940s. And in later years, people also installed some constant diameter steel pipe piles to get some comparison. And what I'm showing you here is that although there is some scatter, that there very clearly is a linear trend that with increasing taper angle, you get increasing compressive resistance efficiency. Essentially, what this is showing you in numbers is what goes back to what Peck said in words going back to the 1950s. And that is, all things being equal, a tapered, driven taper pile will have better load-bearing capacity than a constant diameter pile. So notice that with the increasing taper angle, that we get larger values of compressive resistance efficiency, meaning that you can support more load with less volume of pile material. So when it comes to pile taper, a little goes a long way with respect to load bearing. These are very small angles. All of these angles are less than 1 degree of angle, as I defined it earlier. There's one final topic to discuss on the subject of geotechnical axial resistance modes and mechanisms. The preceding discussion has clearly indicated that the deep foundation installation process plays a significant role in determining the post-installation value of the lateral earth coefficient, KH, acting both along a deep foundation shaft as well as at the toe. And that this in turn influences both the shaft and toe resistances of a deep foundation element. A recent practice that I've seen evolve in the New York City metropolitan area, and perhaps this has been done elsewhere, is to allow contractors to use a hybrid installation methodology for driven piles, especially in coarse grain soils. Specifically, in the past, in these cases, there would have been impact driving of the pile for its entire intended embedded length or design depth. But more recently, contractors have been allowed to vibrate a pile for most of its design depth using a vibratory hammer, and then drive the pile home, as it's called, only a relatively short distance using a conventional impact hammer. I think it should. This is based on the assumption and the justification that the pile has the same ultimate geotechnical resistance regardless of how you got it in the ground, whether impact driving was used for the entire embedded length or for just the last few feet or meters of installation. And based on what I've discussed so far in this presentation, it should be obvious that this is not a given. The point I'm getting at is how you get a deep foundation element in the ground, or how you construct it in the ground, makes a huge difference on this K sub H, because now we see K sub H really is not just a single parameter. It's best understood by looking at it as the product of two parameters. K sub H over K sub O, that ratio reflects the type of deep foundation element and how we got it in the ground or constructed it in the ground. And K sub O is the pre-construction lateral earth pressure coefficient in the ground. Well, I now want to move on to the topic of deep foundation element load sources. And this is a very extensive part of this overall module, because there are now many more sources of load and displacement of a deep foundation element other than the simple externally applied load after installation. I'm going to start off with some background, and then I'll give you an overview, and then I'll talk about some topics in greater detail. So first, let me give you some background on things. Historically, as I've said now, it's been assumed that the only axial loads for which a deep foundation element needs to be designed are the post-installation loads applied at the head of a deep foundation element from the structure that is supported by the deep foundation element. This assumption is complemented by a wished-in-place model for the deep foundation element that you see in every textbook and design manual, whatever, that has several basic assumptions. We assume that the ground is passive to and remains unchanged by the deep foundation installation process, with the exception that we certainly have understood for some time now that fine-grained soils adjacent to the deep foundation shaft can be remolded during the installation process and reconsolidate around the deep foundation shaft after installation, with a final shear strength that may be somewhat different from what existed prior to deep foundation installation. After deep foundation installation, it's assumed that all material stresses within the deep foundation element shaft are zero, and the shaft and toe interfaces between the deep foundation element and ground are stress-free, so that the deep foundation ground shaft friction and toe end bearing both start from a zero load condition. This is always taken to be a given. It's also assumed that the ground is spatially fixed and stress-wise reactive only to the loads applied to the deep foundation element, and thus provides only resistance to the externally applied loads on the deep foundation element via the two traditional resistance mechanisms of shaft resistance due to sliding friction and toe resistance due to end bearing that I discussed earlier in this module. And finally, no explicit settlement calculations are performed for design purposes, but settlements are assumed to be quote-unquote small, which has led to the common perception that piles don't settle. In reality, all of these traditional assumptions related to the source of deep foundation loads, the interaction between the deep foundation element and the ground, and the negligible magnitude of post-installation deep foundation settlement under load are always incorrect to varying degrees, and they're incorrect for all types of deep foundation elements and installation methodologies, with the actual deep foundation load sources, the interaction between ground and deep foundation element, and the potential for post-installation settlement from these load sources much more variable and complex than historically assumed. To begin with, the ground is neither passive during deep foundation installation, nor spatially fixed and solely reactive to post-installation deep foundation load application. Rather, the ground can assume a much more active role both during and after deep foundation installation, and in the process, induce axial displacements and loads on and within a deep foundation element that are independent of, but as we'll see, interactive with, traditional post-installation applied loads and the axial displacements caused by these post-installation loads. In some cases, these ground-induced axial displacements and the loads they create on a deep foundation element can actually dominate the post-installation performance of a deep foundation element, to the extent that the deep foundation element and the structure they support simply go along for the ride, if you will, with the ground totally in control of things. Now, there's no shortage of published case histories illustrating the dominant role that the ground can take in the performance of structures supported by deep foundation elements, and the variety of anthropogenic and natural causes of this ground behavior. Despite this decades-long body of knowledge, the reaction in many cases from both industry and academia alike has been to simply ignore ground-induced effects and continue to use the simplistic wished-in-place model in design. However, this is certainly one of those cases where ignorance is bliss is not a defensible position. And I've always liked this quote from Aldous Huxley: "Facts do not cease to exist because they are ignored." Now, a different and much more recent development for which the body of knowledge is still developing and evolving is where post-installation axial forces and displacements originate from within a DFE shaft due to significant deep foundation element thermal changes that occur intentionally by design after installation. These thermal changes occur in what we call energy pile applications. If you're not familiar with that term, an energy pile is an application where you take a load-bearing deep foundation element, but you also use it as a heat transfer component in what is called a ground source heat pump system, and that is used to heat and cool the structure being supported by the deep foundation element. Specifically, a deep foundation element in energy pile applications acts as a heat exchanger with the surrounding ground. And the ground around the deep foundation elements is used as a thermal storage device, or a kind of, if you might think of a thermal battery to store heat. And this graphic illustrates the basic concept. You have some structure that needs to be supported on deep foundation elements structurally, but you basically kill two birds with one stone. You use those same deep foundation elements as heat transfer elements to move heat in and out of the ground. And that heat that you move in and out of the ground is used to heat and cool this building. Now, as a result of what is called the thermomechanical behavior, an energy pile will expand and contract in an annual cyclical manner for the life of the structure. So thermomechanical behavior refers to the inherent expansion and contraction of a deep found element shaft due to being used as a heat transfer element. Now, this expansion and contraction generates a site and application and deep foundation specific combination of axial displacements and axial forces over and above those that come from the structural loads. And these displacements and forces need to be forecast and accounted for geotechnically and structurally during the design of the heat pump system components, the deep foundation elements in the structure in this case. This is a very interesting application. I'll have a lot more to say about it later on in this presentation. I think it's certainly something we're going to see done a lot more in the future in the United States. I know there are some countries, especially in Europe, that are already using this very extensively. Well, having given you some background as to why we need to talk about deep foundation element load sources in considerable detail, simply because there are many, many sources. Let me give you an overview of what I will be talking about in the following segments. The ground-induced physical mechanisms that result in displacements of and loads on a deep foundation element fall into two broad independent categories depending on whether they occur as a result of the deep foundation element installation process or post-installation. Furthermore, within the post-installation category, we'll see that there are several different physical mechanisms of both natural and anthropogenic origins that can each occur independently of the other. Although both installation and post-installation ground-induced physical mechanisms directly interact with a deep foundation element shaft, they indirectly produce effects on a deep foundation element toe as well. Now, the potential importance of ground-induced physical mechanisms, especially those that occur post-installation, I can't overemphasize them enough, as under the right conditions, they can completely dominate the behavior of a deep foundation element, and as a result, a structure supported by deep foundation elements. Specifically, because ground-induced physical mechanisms can develop even in the absence of post-installation externally applied loads, there's no shortage of case history examples of a deep foundation element failing, if you will, geotechnically by settling tens of millimeters, several inches, or even meters or feet in extreme cases, even though there was no externally applied load on the deep foundation element. And this feet example is no exaggeration. I personally was involved in a project in my career here in the New York City metropolitan area where there was a marine structure, shallow water marine structure, that the pile supporting that pier actually settled feet over the span of the better part of a century. So that's not an exaggeration. In particular, there are any number of case histories where a deep foundation element has literally been pulled downward out of its cap by post-installation ground displacements and the forces they exert on a deep foundation element. And this photo is very typical of that. So here we see a structural slab that's supported on driven piles, and you can see from the irregular underside of the slab that it was poured on the original ground surface at the time of construction. So here you have the pile cap, and here you see how the pile in that pile cap has been pulled down as the ground surface settled due to post-installation settlement. And there's now very clearly a gap between the head of the pile and the pile cap. And keep in mind that especially in the past, deep foundation elements were not structurally connected to a pile cap. Nowadays, very often we do that. We do have some continuity of rebar between the top of the head of a deep foundation element and the pile cap. But in the past, that was generally not done. There was no need to do it structurally. So it made it very easy, if you will, to pull a pile, as in this case, out of a pile cap. And I know that this has happened here in the New York City metropolitan area. So although ground-induced physical mechanisms act independently of the physical mechanisms related to the traditional externally applied loads on a deep foundation element, there is an additive force displacement interaction between these two different mechanisms because they have identical geostructural cause-effect behaviors and are resisted by the same resistance modes and mechanisms that we discussed earlier in this presentation module. So before I talk about these individual load and displacement sources in detail, I'm going to talk about the common elements that they have. So first of all, it's important to note that this additive interaction should always be considered explicitly in both design practice and academic research, as the net effect of the combined physical mechanisms produces both loads on and displacements of a deep foundation element that affect deep foundation element performance both geotechnically and structurally, and therefore affect the structure that is supported by the deep foundation elements. Now, despite the fact that both installation and post-installation ground-induced physical mechanisms have been well documented in the published literature for many decades, because they tend to develop out of sight, unfortunately, even to the present, they are all too often out of mind in both design practice as well as academic instruction and research. Furthermore, even when ground-induced physical mechanisms are considered, they are sometimes dealt with incorrectly, especially in the case of post-installation mechanisms. And that, I think, is a real problem because what happens is that incorrect analytical methods are sometimes incorporated into building and design codes. And as every design professional knows, you are legally required to comply with building and design codes on a project. So your hands are very often tied by having to follow some methodology or method in a code or a standard that is incorrect, but you have to follow it anyway in design practice. So we've identified that ground-induced physical mechanisms exist, and they affect deep foundation elements of all types. And there's this mission critical need to consider these mechanisms in both design practice as well as academic instruction and research. So the next step is now to identify and discuss these mechanisms in some detail. As I said, there are two completely independent sources of these physical mechanisms. One, the result of installing or creating the deep foundation element in the ground, and the other that occurs post-installation. But as I indicated earlier, they have the same root cause, load source, and concomitant overall effect on a deep foundation element. So it's efficient to discuss this root cause, load source, and several concepts to it up front, because these basic concepts apply to all the specific cases that I will discuss in individual presentation segments shortly. I'll also point out that many of the root cause concepts I'm going to discuss are also broadly relevant to these new concerns of thermomechanical behavior of energy piles that are part of a ground source heat pump system. So this topic of energy piles and their thermomechanical behavior is something that is still relatively new, and I would suspect there's probably a fair number of civil engineers who are not even aware of their existence of energy piles. But it's important to point out that the things I'm going to be discussing here, as we will see, are applicable to energy piles. Now, the root cause of all ground-induced loads is the development of negative shaft friction that acts along a portion of a deep foundation element shaft, beginning at the ground surface and extending down some depth along the shaft. And this depth along the shaft can be anywhere from some intermediate depth, in an extreme case, could go down pretty much to the toe of the deep foundation element, although usually somewhere intermediate is more common. Now, in this application, the ground-induced negative shaft friction is called unit drag load. Again, this is a shear stress, hence the lowercase letter. Now, whether the causal mechanism of this unit drag load in a specific case is settlement of the ground surface relative to the deep foundation element, or upward displacement of the deep foundation element relative to the ground, or some combination of the two, is application specific, but the net result is the same. And we're focusing on the net result here, not so much how it got there. Now, regardless of the specific causal mechanism, the unit drag load produces an axial compressive force within the deep foundation element shaft that we call the drag load. Now, I'm showing this outside the shaft, but this is for clarity, but it is occurring obviously inside the shaft. If you're not familiar with the concept of an equilibrium plane, I introduced it earlier in this presentation. I will be using it extensively throughout the remainder of this presentation. The equilibrium plane, formerly known as the neutral plane, is an essential tool for depicting the location in vertical space along a deep foundation element shaft where several things happen. First of all, we have a change from the unit drag load to positive shaft friction for all ground-induced load mechanisms, both from installation and post-installation. And note that I've omitted toe resistance here for simplicity and clarity in this discussion. There, as we'll see later, there is toe resistance that develops as well. Equilibrium plane also defines the point in vertical space where the vertical settlements of the deep foundation element to ground are the same. So above here, the ground settles more. Below here, the ground settles less, but this is the unique point in vertical space where they have the same magnitude of settlement. It's important to note that regardless of the causal mechanism, this equilibrium plane is always an active dynamic feature. It can move up and down a deep foundation element shaft as a function of both applied load as well as time. And throughout the remainder of this presentation, I will show you several examples of how this equilibrium plane can move extensively. It could go up to the ground surface And even in an extreme case, it could go all the way down to the toe of the deep foundation element. That typically only happens if the entire soil column were, say, very soft compressible soil, and the deep foundation element was bearing on or in sound bedrock, so that the toe is essentially not settling at all. But as I said, that's an extreme case. But it does indicate that this equilibrium plane can vary substantially in a vertical direction. The single most important thing I want you to get from this discussion at this point is, and I will make this repeatedly, and the reason I repeat it till you're tired of hearing about it is simply because this is one area where a lot of codes and design manuals in the present make a mistake. And we'll see why they make this mistake. It's understandable where it came from, but I'm emphasizing this repeatedly because this is probably the single biggest issue we have at the present time with how these externally applied loads are dealt with in design practice. So regardless of the causal mechanism, note that the shear stress and resultant force from drag load never ever reduce the geotechnical ultimate resistance of a deep foundation element. And as a result, they never reduce the ultimate capacity that can be applied to the head of a deep foundation element in either axial compression or tension uplift. Okay? And I will show you some examples as we get into this why we can make this statement. So as I said, I'm emphasizing this and will emphasize it throughout the remainder of this presentation because of its importance cannot be overstated. And again, it's because of the fact that there's a widespread chronic misunderstanding of this statement here. And the reason these drag forces do not detract from the geotechnical resistance of a deep foundation element is because they are reversible. Because the ultimate, as we pointed out earlier in this presentation, the ultimate limit state of soil or soil structure interface is always reversible, simply by reversing the direction of relative displacement along a failure surface. So specifically here, negative shear friction can always be turned into positive shear friction or vice versa, simply by reversing the direction of displacement of a deep foundation element relative to the adjacent ground. Consequently, if you have a deep foundation element that is subjected to negative shear friction due to drag load, if this deep foundation element were to compress and settle sufficiently relative to the surrounding ground, as a result of putting a load at the head of the deep foundation element, for example, that drag load would completely turn into positive shear friction, which would be resistance in the case of an externally applied compressive load. Now, I'm going to illustrate this to you qualitatively, but I will, later in this presentation, I will show you a case history of measurements. These were made on the Holman Island piles in Norway more than 50 years ago. I will show you some actual case history measurements that show that this does really occur in the real world. So this is not just a hypothetical discussion. It is right now, but I will show you some actual case history data that these drag forces are reversible. All right, so notice what I've done here, all right, is I've now applied a load to the head of the deep foundation element. I've had a combination of shaft compression and settlement, and that has now reversed the shear direction in this upper part of the DFE shaft, and what had been negative shaft friction is now positive shear friction, which in the case of an axial compressive load is resistance. And I've now included the toe resistance here just so that you see the complete free body diagram of forces that is acting. Note that as a result, the equilibrium plane moves up from here to the ground surface because all the negative shear friction, the drag load, has become positive shear friction, which is resistance in this case. Now, for the sake of completeness, I'll illustrate what happens if you were to apply a tensile or uplift load. Again, we start off with no load on the head of the deep foundation element shaft. And I'll point out to you that when we apply the uplift load, the drag load is structurally beneficial, as this is now going to act as resistance. Okay, so now I've applied an uplift or a tensile load. I have an upward displacement of the deep foundation element shaft. I have elastic extension of the shaft, plus I have upward displacement. And in this case, notice what I've done. I've turned the positive shear friction here into negative shear friction. But when I have uplift loads, negative shear friction is actually resistance. Okay, as I said to you very early in this presentation, negative and positive shear friction are just absolute directions. Whether negative or positive shear friction is a drag load or resistance depends on the direction of applied load at the head of the deep foundation element shaft. We'll also see it also will, in the case of energy piles, it depends on the temperature within the energy pile. So once again, the equilibrium plane moves up to the ground surface, and I'm assuming simplistically here that we have no toe resistance. I'm fully aware of the fact that in certain soil conditions you can develop suction at the toe of the deep foundation element. For simplicity here, I'm assuming that we do not have any toe resistance in the limit as we apply this uplift load. So what I've shown you here is that regardless of which direction of applied load, the drag loads are fully reversible so that you see that it doesn't detract from the overall geotechnical resistance of the deep foundation element. So the point I'm getting at here is that drag load is always a displacement settlement in the case of compressive loading issue. So it's a geotechnical serviceability limit state issue. It is not and never is a soil strength issue. It does not affect the geotechnical ultimate limit state because the geotechnical ultimate limit state of the deep foundation element shaft never ever changes. Now, of course, you have to consider the structural ultimate limit state, given the fact that drag load imparts an axial compressive force within the shaft. So I'm not ignoring the structural aspects, but it's really the geotechnical aspects that I want to focus on at this point. Again, I'm emphasizing, perhaps to the point of overemphasis, the proper way to understand and treat drag loads in design practice, because experience has shown that this issue has been and continues to be incorrectly dealt with in building of design codes and other design-related documents that have significant legal and technical influence and control over design practice. And this is not just a point that I'm harping on. This is a point that Fellinius has made now for decades. You see here's a quote going back over 25 years now. I always like this. Beyond the name, there is nothing negative in negative skin friction. So this emphasis of how to deal with drag loads correctly is, as I said, this is not something that I'm commenting on. This has been commented on in literature for a very, very long time now, going back to actually to the 1980s. So the equilibrium plane concept has proven to be an essential tool also for the thermomechanical behavior of deep foundation elements that function as energy piles. I want to spend a little bit of time talking about that because this is a very, well, it's fairly new here, at least in the United States. It's been used in parts of Europe now for a couple of decades. It's not so new there, but it is certainly a growing, emerging technology that I think we'll see more and more of worldwide in the years and decades to come. So I want to spend a little bit of time talking about this aspect. The deep foundation element ground stress system that results from thermomechanical behavior of energy piles is much more complex than with the ground-induced loads because we have these annual reversals of expansion and contraction of the deep foundation element shaft because the temperature of the deep foundation element shaft is tied to the annual thermal cycle of heating and cooling seasons in temperate climates. Now, during the heating season, what happens is this ground source heat pump system takes heat out of the ground. Again, think of the ground in this case now as we've always been focusing on the geotechnical resistance provided by the ground. Now we're thinking of the ground as this massive thermal battery or storage unit, if you will. So during the heating system, we take heat out of the ground, and what that's going to do is going to reduce the temperature of the shaft of a deep foundation element, so it's going to contract. And the equilibrium plane now defines the point where the direction of contraction is zero. During the cooling season, we're going to take heat out of the building and put it into the ground. So now the deep foundation element is going to expand. And although it's not quite as clear here, the equilibrium plane still defines the point where there is zero displacement of the deep foundation element shaft. Above here, it expands upward. Below here, it expands downward. Now, the position of this equilibrium plane, I just for simplicity have shown it in the middle here. And for the time being, I've not shown you the stresses around the deep foundation element. I'll show that later on. The position of this equilibrium plane can vary tremendously. Obviously, if this deep foundation element were bearing on rock, most of the expansion would be perhaps upward. So in energy pile applications, the equilibrium plane is used to define different displacement and force systems involving negative and positive shaft friction in the heating and cooling seasons. And I'll show you this in more detail in the phase 2 presentation module later on. So having established the existence and general nature of both ground and deep foundation element induced displacements and forces on deep foundation elements, I'm now going to begin to show you 3 different presentation segments that will discuss each of these different mechanisms in greater detail. And I'm going to start off talking about residual loads from installation because, as we'll see, they are something that occurs all the time in every type of deep foundation element, at least to some extent. The term residual loads refers to the system of negative and positive shaft friction plus some toe bearing stress that exists after deep foundation element installation or construction in the ground and prior to the application of any externally applied axial load. Now, in the traditional wished-in-place model that we all learned in undergraduate geotechnical engineering, foundation engineering, in the traditional wished-in-place model of deep foundation elements that one sees in textbooks, etc., these stresses simply do not exist, as the deep foundation element is assumed to be stress-free after installation. It's easy to understand residual loads in this application because they're conceptually identical to the residual, or what we call rolling or mill stresses, in hot-rolled, cold-formed, and fabricated steel sections. And these are just examples that you can find in a structural engineering textbook showing you that if you had some structural steel member with no externally applied load, there's still going to be some stresses in that member, depending on how it was either hot-rolled or cold-formed or fabricated by welding sections together. Now, the residual loads that act on a deep foundation element also produce a depth-wise variable compressive force, and therefore compressive normal stresses within the structural material that comprise a deep foundation element shaft. So residual loads are both a geotechnical as well as a structural consideration. Now, in this case, the equilibrium plane is used to define the unique point in vertical space where the vertical resultant forces produced by residual loads are in vertical force equilibrium. So, of course, we have to consider the toe resistance here as well as where the axial compressive force within the deep foundation element shaft reaches its maximum value. And I'm emphasizing force because note that the axial compressive normal stress within a deep foundation element shaft may or may not peak at the equilibrium plane, because this depends on whether or not the cross-sectional area of the deep foundation element varies with depth. In fact, I will show you examples later on, some case history examples, where in the case of a tapered pile, for example, even though the residual loads are less as you get near the toe, the stresses, the compressive stresses from the residual loads are actually at their peak down here. And the reason they're at their peak is because the cross-sectional area of the pile is considerably less than up here where it has, say, a constant diameter extension. So you need to be careful. You need to be careful when you're calculating, of course, stresses within the shaft to take into account the geometry variation of the shaft if you're dealing with tapered deep foundation element. So the depth at which the axial compressive normal stresses within a deep foundation element shaft reach their peak magnitude always needs to be determined on a case-by-case basis. You can't make generalizations. Now, residual loads are the proverbial elephant in the room of deep foundations, and I say that from having been involved with deep foundations for over 50 years. And I could say that few industry stakeholders seem to want to recognize and talk about, no less address in a thorough, comprehensive manner. And this is true in both design practice and academia. And in fact, last year I made a separate presentation just about residual loads, because as I was working on this larger presentation, which I have been for some time, I realized that this issue of residual loads, certainly in some cases, is very, very important. And I'll show you later in this presentation why I made a separate presentation about this last year. This is a real problem that we neglect talking about this issue, and I'll give you some hard numbers to show you why I have this concern. It's kind of surprising that we have our head in the sand attitude, if you will, about residual loads, because the existence of residual loads, at least for driven piles, was suggested in the publications going at least back to the 1950s. And their existence was proven unequivocally in the late 1960s as the result of this research that I mentioned previously at the former NGI so-called sand test site on Holmen Island in Drammen in Norway. I say former because this test site got filled up, so the NGI now has another site they use for research related to coarse-grained soils. Now, when I looked into this, I found that there was a flurry of international research and interest and publication in the 1980s about residual loads for driven piles. And if you look here at some of the names, these are all big names in geostructural engineering. For whatever reason, this research appears to have gone nowhere and has now been forgotten by most, although Fellinius has continued to research and write about residual loads with regularity. It's kind of surprising to me that we don't talk about residual loads because the recognition of drag loads due to global settlements, which I'm going to talk about next segment, also originated in the 1960s, but that research has continued unabated to the present. And I find this surprising because global settlement is a potential deep foundation issue only in very specific geological settings or conditions, whereas residual loads are a potential deep foundation issue in all conditions. Now, largely due to Fellinius' research efforts in recent decades, it's now recognized that residual loads can develop with many, and I put most or all because I think there's a lot of gaps in our knowledge, but certainly with many types of deep foundation elements, in addition to driven piles. This is not just a driven pile phenomenon. It can exist with jack piles, and it can even exist with drilled shafts or bored piles. Although certainly the relative magnitude of residual loads varies widely depending on the specific type of deep foundation element, and more importantly, its method of installation into or creation within the ground. There's still a lot of fundamental research that needs to be done to investigate residual loads, especially for some of the newer types of deep foundation elements. Many of them are proprietary, that are drilled or torqued into the ground. Anybody who follows the deep foundation industry in recent years knows that there's been a tremendous amount of development of new types of deep foundation elements in the way that they are created in or inserted into the ground. And I have to wonder if the people who are promoting these new technologies that own these technologies, I wonder if they're undertaking the necessary research into residual loads. If they have, it doesn't appear that they publicized it as best as I could tell. Now, while it is known with certainty at the present time that residual loads are especially significant with driven and jack piles, we also know that for driven piles, residual loads are the most significant with tapered piles, such as the monotube and taper tube brands. And this appears to be related to the, if you will, 2 steps forward, 1 step backward nature of conventional pile driving. You know, we tend to think of conventional pile driving of being a monotonic pushing of the pile into the ground. And although the pile does advance into the ground, certainly as we continue to drive it, it does that in really kind of a 2 step forward, 1 step backward way. Let me first illustrate this with a simple qualitative graphic. And then I'll show you on the next slide some measurements of what I'm depicting here. So what I'm showing you here is when we impact a pile as we drive it into the ground, it will advance and then retract somewhat, advance somewhat, and then retract somewhat. That's why I call it 2 steps forward, 1 step backward. Now this slide shows you some research that was published back in 2017. What we're looking at here on the horizontal axis is time. And on the vertical axis, we're looking at the displacement of a pile into the ground. And each of these spikes is a hammer blow. To make this a little bit more visually obvious, I'm going to invert it. Okay, so what we're looking at here, and again, this is the time axis, is here's a hammer blow. All right, so we impact the pile, it goes into the ground, but notice how it rebounds, oscillates around, and then stabilizes, and then we have the next hammer blow. So this is what I mean by 2 steps forward, 1 step backward. Yes, the pile is advancing into the ground, some net, what we call set. There's no doubt about that. For each hammer blow, we do get a net penetration into the ground, but it is not monotonic. It advances and retreats somewhat, advances and retreats somewhat. So the point I'm getting at is this complex nature of advancing a pile into the ground by traditional impact driving really creates a scenario where these residual loads can develop. Now, despite the overwhelming body of knowledge going back many decades now that residual loads exist, the current design state of practice, and this is true for most academic research as well, is to simply ignore them and continue to use the traditional wished-in-place stress-free model for installed deep foundation elements. That, as I said, is always incorrect to varying degrees, depending on the type of deep foundation element. In my opinion, this approach to dealing with residual loads is, by simply not dealing with them, is the net result of at least 4 reasons. One is ignorance of the subject. And I can attest to that firsthand because I will tell you that in my formal education, through all my degrees, none of my professors ever taught me that residual loads existed. Second, we can have simple dismissiveness of the subject. You know, people say, yeah, I heard about it. Let's move on, nothing to look at here. Third is the belief that such loads exist, but they are relevant in routine practice so they can safely be ignored. Fourth is the belief that such loads exist, but their effects disappear completely with post-installation externally applied loading so they can be ignored. There's a little bit of a subtle difference between 3 and 4. In both cases, they are ignored, but the reasons for ignoring the existence of residual loads is subtly different. Well, again, this is another one of those ignorance is bliss situations that is not defensible. But certainly, the last 2 items are legitimate. People saying, yes, I know they exist, but they go away when I applied load to the deep foundation, so I don't need to deal with them, or they don't create any problems. Now, I'm going to address these 2 points together. The ignorance I can't deal with. I'm not going to waste my time to try to argue against outright ignorance. But certainly these last 2 are legitimate concerns, and it's worth spending some time to illustrate why, yes, they exist, but no, it's not safe to ignore them. And I'm going to separately discuss the effect of residual loads on both geotechnical and structural behavior, as, of course, both aspects are mission critical for deep foundation element performance after installation. And I will be using case history examples from 2 sites for which I have access to sufficient data. One is this NGI site at Holman Island in Drummond that was discussed in detail by this paper by Gregerson et al. That I referenced earlier. This was presented at an international conference in 1973. And I'm going to be discussing things I've learned from my decades of research at Kennedy Airport, which again, I have discussed in much greater detail in a tetralogy of white papers that you can access and download at your convenience from my ResearchGate website. I also discuss the Kennedy Airport results in my 2 YouTube presentations. So I'm first going to discuss the effect of residual loads on geotechnical behavior, as in both the current design methodology based on the geotechnical ultimate limit state and the proposed changed state of practice based on serviceability, residual loads are important. As we'll see, residual loads have an overall positive effect on the geotechnical behavior of deep foundation elements subjected to post-installation axial loading. But there can be some very serious negative consequences if residual loads are not properly accounted for. So, while it's perhaps safe in some ways to ignore residual loads geotechnically, it is definitely not safe in other ways. And as we'll see, it's not safe to do so structurally. The reason it's not safe to ignore residual loads geotechnically is because they produce data interpretation errors that are always on the unconservative and therefore potentially unsafe side, because they result in a deep foundation element that has an actual geotechnical safety margin. And again, no one is arguing that we should not build a safety margin into deep foundation elements subjected to axial load. I mean, that's a given. No one's arguing against that. What we're talking about in this presentation is how do we best do that? Again, the traditional way is focusing on the geotechnical ultimate limit state. The better way that I'm trying to show you in this presentation is to focus on the geotechnical serviceability limit state. But certainly safety exists in both cases. So the problem I'm getting at here is that if we ignore residual loads, our geotechnical safety margin is less than what we think or we'd like to have. Well, these are the data from Holman Island. I created these plots using the data that Gregerson et al. Presented in their paper. And yes, it was a lot of work to scale off all of these data points from plots on a graph. So this is a bit complicated. Let me walk you through this slowly so we see what we're looking at here. So we're looking at the depth below ground surface along one of the test piles that they installed, 16 meters long, a little bit more than 50 feet long. And I'm going to be looking at things under 3 separate load cases. What I'm showing you here is on one plot, I'm showing you the interpreted case of H. All right? Because again, the horizontal effective stress acting along the shaft is K sub H times the vertical overburden stress. And on this plot, I'm showing you the KH K0 ratio. Both of these, both KH and the KH K0 ratio, are useful metrics for reflecting drag load. All right, where these are negative, that's a drag load. Where they're positive, the negative is negative shaft friction. Positive numbers are positive shaft friction. So both of these are useful because, as we can see from this equation, they relate to the horizontal effective stress acting on the pile shaft. And as we know, the shaft resistance, unit shaft resistance, is linearly related to the horizontal effective stress. Now the KO interpretation here I did personally. Although the data came from the Gregerson et al. Paper from 1973, I was very fortunate that someone kindly gave me a set of raw data for a piezo cone sounding that was done just within the last few years at Drummond Island. So I was fortunate to have access to the raw data for a piezo cone sounding, and I did all the data interpretation of that piezo cone sounding myself. So I did not rely on any data from somebody else for that aspect. So the KO values are values that I calculated. I'm sorry, it was actually a seismic piezo cone sounding. So that's my own personal interpretation. First thing I want to note, and this dash green curve is and again, these were instrumented piles, so this is how Gregerson et al. Got the data in the piles. This is the residual loads after installation, and one of the things we want to notice is that about 50% of the ultimate toe resistance was mobilized as residual load And that's not an uncommon number, certainly for driven or jack piles. I'll show you some other case history data for both driven piles and jack piles. And residual tow resistances, numbers like 50% are certainly very, very common. In some cases at Kennedy Airport, I'll show you it approached 100%. And this is a very important outcome to highlight. And here's the equilibrium plane under residual load. So the equilibrium plane was more than halfway down the pile shaft in this case. By the way, this happened to be a pile. In this test pile program, they drove both constant diameter as well as tapered piles. This happens to be the constant diameter pile. Now this pile was loaded in compression to 65 millimeters, or about 2.5 inches of pile head settlement. And Q90 is a Norwegian parameter. I won't get into how it's determined. I talk about it in my other publications. But for our discussion purposes here, think of this parameter Q90 as basically being the geotechnical ultimate limit state value. So the point is that this pile was loaded until it settled substantially so that we can feel comfortable saying that the geotechnical ultimate limit state was mobilized along the entire pile shaft. So 1/2 of Q90 we could assume to be the maximum service load level. We see that the equilibrium plane has come up a bit. All right, so some of the negative shaft friction, for example here, this negative shaft friction has been converted to positive shaft friction. We also see this here. This negative shaft friction has been converted to positive shaft friction. So this puts numbers, actual case history numbers, on things that I showed you on an earlier slide. And that is that because we can reverse the direction of failure, if you will, in a soil structure interface, we can always turn negative shaft friction into positive shaft friction if we have enough settlement. All right, and this is why I said we never ever reduce the ultimate geotechnical resistance of a deep foundation element for negative shaft friction or down drag loads. We never reduce it because, at least in principle or theory, we could always get rid of those residual loads if we applied enough load at the head of the deep foundation element. Now in this case, they had to load the pile completely to geotechnical failure to get rid of all the negative shaft resistance. All right, so to go from here under residual load conditions, no load at the head of the shaft, to transfer all of this negative shaft friction to positive shaft friction, negative shaft friction to positive shaft friction, they had to settle this pile about 2.5 inches, 65 millimeters, in order to get rid of all the negative shaft friction and bring the equilibrium plane up to the ground surface. And I should point out that this was, for the most part, a fairly loose sand at this site. So this is, I think, this paper is provides us with an outstanding case history example to put numbers on things that I talked about in concept a few slides ago. The negative shaft friction, regardless of where it comes from, you could always turn it into positive shaft friction, which is resistance in the case of compressive loads, simply by applying enough load at the head of the deep foundation element to make it compress further as well as to settle. And another important thing, and this is now going to factor into things I'm going to show you, especially in the phase 2 module later on, that notice that most of the action going on here, when I go from zero load on the pile to failure load on the pile, notice that most of the reversal of stress is happening up here in the upper portion of the pile. relatively less change in shaft friction down here, and that's because a good portion of the positive shaft friction, the resistance, was already mobilized just by installation. All right? That's what this positive shaft friction here means under residual loads. I've already mobilized something like half the geotechnical resistance to the lower portion of this pile. And same thing with the toe. I mobilized half the toe resistance just by installing this pile in the ground. And again, I'm highlighting, note the dynamic, ever-changing nature of the equilibrium plane as the external load is applied. This just illustrates what I said to you earlier on. And again, as I point out, the post-installation externally applied axial load was accommodated primarily by shaft friction. In this case, reversing drag load into resistance along the upper portion of the deep foundation element shaft. And it's interesting, in this case, the pile had to basically be loaded to the geotechnical ultimate limit state in order to overcome all the effects of residual load. Now, certainly here in the United States, I think a lot of people have heard the phrase, a driven pile is a tested pile. I know that the driven pile industry likes to use this as a catchphrase in their advertising. And I think we can now add to that a driven pile is a pre-settled pile. And that's because residual loads, which are very significant in driven piles, are to deep foundation elements what pre-stressing is to Portland cement concrete. Both residual loads in driven piles and pre-stressing in Portland cement concrete selectively preload and pre-stiffen the load displacement response of the overall structural system. Now, as I pointed out to you, residual loads preload specifically the less stiff toe resistance, about 50% in this example from Drammen Island, Norway, to approaching 100% in some cases at Kennedy Airport that I'll show you later on. And that's actually very, very beneficial because we basically get rid of, we already mobilized toe resistance, which, as we know, generally takes a lot more displacement to mobilize. And this causes post-installation externally applied load to resist it primarily by the stiffer shaft resistance, in this case turning negative shaft friction into positive shaft friction. I always like this quote by Bucky Fuller, don't fight forces, use them. And this is certainly one of those cases where we should make use of the fact that we have residual loads. And again, as Fellini has said, there's beyond the name, there's nothing negative in negative skin friction. And I keep emphasizing this because the state of practice in the US, Europe, and elsewhere uses the deep foundation element ground system stiffness measured in a static load test as the primary metric for determining the geotechnical ultimate limit state of a deep foundation element. And I showed you this earlier in this presentation on that slide that showed you about a dozen different methods for interpreting ultimate limit state, most of which depended on displacement. So in this case, residual loads are clearly beneficial geotechnically, but the emphasis here is only if they are interpreted correctly. And I'll show you what I mean by that in a minute. But before we move on, I want to show you another interesting thing that came out of the Holmen Island, Norway test program. There were two piles. The curve shown in red was constant diameter. The one shown in blue was tapered. Here we're plotting the residual load after installation as a function of depth. These two piles had the same 16 meter, roughly 50-foot length. That's the constant diameter, and this is the tapered. And the tapered angle is very modest. These were precast, pre-stressed concrete piles. A taper angle is very modest. It's approximately that of a timber pile in the eastern United States. But notice that the tapered pile had considerably more residual load. And I'll show you that we found the same thing at Kennedy Airport. So we've already said a driven pile is a tested pile and it's a pre-settled pile, and we can add to that taper makes it even better. And again, this is nothing new. The late Professor Ralph Peck noted this almost 70 years ago in a Highway Research Board publication. Well, as with a lot of things, you get some bad with the good. And unfortunately, there could be some serious negative consequences of a geotechnical nature unless residual loads are correctly accounted for when performing various resistance verification tests in the field. Now, to begin with, consider the effect on the traditional static load test that is used to estimate the geotechnical ultimate limit state of a deep foundation element, usually using some displacement-based criterion, such as the Davison offset method that is ubiquitous in U.S. practice. I'm going to first show you a case history involving a jacked pile. And experience indicates that installation effects are similar to that of a driven pile. Again, jack piles are not that popular in the U.S. as best as I can determine. They are popular in parts of Asia. And this is from a paper by Felinius. You see the geologic profile at the site. And the toe of the deep foundation element is about 15 meters below the ground surface. So not quite 50 feet. And you notice that in this case, there are really significant residual loads. This is a very, very classic pattern of the distribution of residual loads. This was a constant diameter pile, by the way, jack pile. And in this case, about 40% of the ultimate toe resistance was mobilized during installation. So as I said a while ago, jack piles are very similar to driven piles. For the Norway piles, we found 50% toe resistance mobilized by installation. Here's 40%. I'll show you some examples later with tapered piles at Kennedy Airport where it was closer to 100%. Now this jack pile was instrumented, and this was the interpreted axial load distribution that was measured. Unfortunately, it was wrong because this is the true resistance, and the reason that the measured resistance was wrong is that they did not correct for the residual load. So the true resistance is the residual load that existed before the gauges were zeroed and external load was applied and measurements were made. Okay, so they jacked this pile in the ground. They zeroed the instruments and applied an external load axially and said, okay, this is what we measure from the external load. This is the load distribution in the pile. Well, it's not, because they didn't add to it the residual loads that were already locked in there. So this is what we call the true load distribution. We're going to see this type of behavior many, many times before the end of this presentation, where we have a significant residual load distribution, some measured distribution that does not consider it, and therefore the true distribution is something significantly different. This was the pile load test for that paper. This is the static load test curve that was measured, and this is what we would typically measure in practice. And using the Davison offset limit, this would be we would interpret this, oh, this is the geotechnical failure load, right? Something like 6,400 kilonewtons. If you're using the European toe displacement criterion, this would be the failure load. So if we applied the conventional safety factor of 2, we would say that this jack pile had an allowable load of what? About 3,200 kilonewtons. The problem is that if we now interpret that same behavior but include residual loads, the toe load is false because we think the toe load starts at 0, whereas in reality the toe load starts here. The shaft resistance is false because, again, we think the shaft starts at 0 when actually it starts at a negative number. It doesn't quite show up that well on this plot, but the net shaft resistance is negative. Again, under residual loads, the load at the head of the pile is 0. So if you have an initial toe load, you have to have a net negative shaft load. So if we plot up the true resistances, recognizing, for example, a toe load settlement curve does not begin here. It actually begins here and then continues on. This is using the same Davison offset limit criteria. This would be the failure load, all right? About 4,600, 4,700 kilonewtons. So we think we had an allowable load of about 3,200 kilonewtons, but really with a safety factor of 2, but in reality we have a safety factor a little bit less than 1.5. And this is what I said earlier. The problem with neglecting residual loads is that you got to take the bad with the good. And the bad is that unless you interpret the test curves correctly, you're going to overestimate the resistance you have. And that's what I'm showing you here. Now, of course, this is a false, this is just somebody's arbitrary criterion for the failure load. And I'm just pointing out to you that there's a reduction in the safety margin based on the offset limit interpretation, which is just an arbitrary interpretation. However, of course, in the real world, there can only ever be one true, if you will, geotechnical ultimate resistance. And it has to be the same. And we can see that if we look at, in this case, fortunately, the jack pile was loaded to about 70 millimeters of axial displacement, so almost 3 inches of axial displacement. So they jacked it into the ground enough to overcome all of the negative shaft friction from residual loads, turn it into positive shaft friction. And as we could see that if you load, as in this case, this pile enough, you're going to turn all, and we saw that in the Norway pile, you're going to turn all the negative shaft friction into positive shaft friction resistance. And you're going to measure the one and only true geotechnical resistance, which in this case is about 6,000 kilonewtons. So this shows you the danger of using some arbitrary criterion, especially the Davison limit criterion, which everybody in the United States seems to love. I'm not a fan of it, obviously. It's got a lot of problems. It was never meant to be used the way it used. The problem with using these arbitrary displacement-based criterion, whether it's the Davison limit in the US or the European limit, is that you can actually overestimate your geotechnical resistance. You think you have more resistance than you really have because you're not properly accounting for the residual loads. And I think, again, this is a really nice way of illustrating also that residual negative shaft friction does not take away from the ultimate geotechnical resistance. But sometimes you've got to load that deep foundation element relatively significantly in order to see what that true geotechnical resistance is. It's interesting to note that the conventional static load test indicates a plunging type of failure, right? It implies that we build up a peak and then it drops off and we reduce, where in reality none exists. Notice that in the real world, the geotechnical resistance, although it drops down, it continues to increase at a very slow rate as we continue to load this pile. Again, notice that this implies a plunging failure where there is no plunging failure. Now, before we go further, in order to understand why the shaft and toe resistances as typically measured in a static load test are false, as the previous curves were labeled, it's informative to trace in some detail what is happening along different portions of a deep foundation element shaft as a conventional static load test with compressive loading is performed if we consider the existence of residual loads from installation. So what I'm going to show you in the next few slides are why we see this false behavior that I indicated on the preceding slide. Okay, so what I'm going to be showing you on these next few slides is essentially what happened, what we saw previously in those NGI Holman Island, Norway test piles a few slides ago. We're going to see what happened on a qualitative basis. So here we see typical residual load distribution, negative shaft friction, a transition zone, positive shaft friction, some toe resistance, and here's the equilibrium plane. And here we see the force within the pile shaft. Again, the force is always maximum at the equilibrium plane. Whether or not the stress is always maximum depends on the geometry of the pile shaft or the deep foundation element shaft. So no load at the head of the deep foundation element, but we do have load at the toe. So now we apply a load to the head of the deep foundation element. And let's first see what happens in the upper portion of the shaft where we have negative shaft friction to begin with from the residual loads. Now, the traditional assumption we make in the Wishton Place model, where there are no residual loads, is that we start at zero load and we go up to some failure load, and we can call this the true shaft resistance for this upper portion here. This true shaft resistance never varies. It stays true no matter what. The reality, of course, is different. The reality is that we have start from a negative shaft friction in this upper portion, and as we apply load at the head of the deep foundation element, we go up to the failure load. So we traverse a much longer path because we first have to reverse the negative to zero and then from zero to positive. And that's why we call this a false shaft resistance. In earlier slides, when I showed you things labeled false shaft resistance, or why I said we tend to overestimate shaft resistance, if you had an instrumented deep foundation element where you ignored residual loads and your load measurements began after installation of the deep foundation element, this is what you're going to measure. You're going to think this is the shaft friction in this upper portion of the shaft. But it's false, because you're measuring first having to reverse the direction of frictional resistance and then increase it in the positive shaft friction direction. What made the test piles at Holman Island, Norway in the 1960s so different is they installed the instruments and zeroed them while these piles were laying on the ground prior to installation. So they were able to measure correctly residual loads. Now, they also extracted these piles from the ground and zeroed the strain gauges after they extracted them from the ground. So the research was quite solid. We could put a lot of faith in the numbers that they reported in the Gregerson et al. Paper in 1973. But that was the major difference why they were able to measure the residual loads, is that the load measurement instrumentation was installed prior to installing the piles in the ground, not afterward, as is done in the vast majority of cases. Now let's look at what's going on down here, the lower portion of the deep foundation element shaft, where we initially have some positive shaft friction. Again, the traditional assumption is we start from 0, go to failure load, and again, this would be the true shaft resistance for this lower portion of the deep foundation element. However, the reality is we start with some initial positive value and then go up to the failure load. So if this is all you measure, you're measuring a false resistance. You've underestimated the shaft resistance down here compared to the true value. Well, let's look at what's happening at the toe. Is a bit more complex. Again, the traditional assumption is we start with 0 and we go up to some load that we might consider a failure load, although in many cases the toe resistance might continue to increase very slightly with increasing settlement. That, of course, would be the true toe resistance. But what happens in reality is quite complex. During installation, we go from here to here, and we get some relaxation and come back down to here. So at the end of the installation process, we're at this point down here. What happens when we apply the load now at the head of the deep foundation element is that we first retrace our steps on the unload reload loop, and then go on to the virgin curve until we reach some level we consider to be failure. So we're going to measure a false toe resistance. We're going to underestimate the toe resistance. This explains why, and I will show you some case histories later, this explains why in a lot of instrumented load tests, static load tests on deep foundation elements, researchers report very small, sometimes almost negligible values of toe resistance. They say, oh, look, everything's being carried by the shaft, nothing by the toe. Well, you're wrong. That's because your instrumentation is all wrong. Your instrumentation is getting a very incomplete picture of what is going on. You've completely ignored the toe resistance that has already been built up. And this is especially a problem with driven piles, especially driven tapered piles or jack piles, because driven piles, especially driven tapered piles, develop a tremendous amount of toe resistance. They pre-mobilize anywhere from 50 to 100% of the toe resistance, which from a behavioral perspective is good. You've already pre-stressed the toe resistance, which normally takes a lot of displacement to mobilize. Again, shaft resistance only takes a few millimeters, a fraction of an inch of displacement to mobilize. Toe resistance takes a lot more displacement. So residual loads are very, very good because you've already pre-mobilized a substantial portion of the toe resistance. We're going to get a much stiffer response, and we'll see more of this later on. And again, the toe resistance is incorrect because we've ignored the residual toe load. And as I said, the reality is that in some cases, this toe resistance may actually continue to increase slightly. This is the genesis of Fellinius's opinion that there is no such thing as an ultimate toe resistance, is that in some cases, especially if we look at relatively small magnitudes of settlement, this toe resistance can continue to increase at a very slow rate with additional displacement. Now, just for the sake of completeness, I'm going to illustrate what happens to the same deep foundation element if now we apply a post-installation tensile or uplift load. All right, so now to this initial condition that we have, I'm applying an uplift load. What happens in the upper portion of the shaft? Well, we're starting with an initial negative shaft friction, and we're actually just going to build to some slight amount of additional shaft friction because, again, in uplift loading, negative shaft friction is positive resistance. So we got to be careful about that. In this lower portion down here, we're starting at some positive shaft friction. We have to reverse that to 0, and then ultimately negative shaft friction, which is resistance in this case. So we get a reversal of what we saw with the axial compressive loading. With toe resistance, again, we start here. We have to decrease the toe resistance to 0. Now, in most cases, and certainly simplistically, the toe resistance will simply stay at 0. Just for the sake of completeness, I'm pointing out that in certain conditions, it is possible to develop some suction at the toe. So I'm just showing you this qualitatively for the sake of completeness. So returning now to the general discussion, there are bigger problems with instrumented static load test as neglecting residual loads leads to interpretation of shaft resistance being too large and toe resistance being too small. And I showed you that already for this jack pile case history that Fellini has presented. This was a very typical case where the measurements within the jack pile shaft only were zeroed after it was installed in the ground and external load was applied. As a result, it completely ignored the 40% of the toe load that was already mobilized just by installation. So if this is all you have, the measured results, you'd say, oh, this has this toe resistance, and I have much more shaft resistance. But the reality is when you consider the residual loads, the equilibrium plane is quite low in this case. It's quite close to the toe. Again, this jack pile is only 15 meters long. The equilibrium plane is more than 13 meters in the ground. So your measurements are neglecting the mobilized toe resistance from residual load. So the true resistance is something quite different. You have much more toe resistance, much less shaft resistance. I'm going to show you some case histories that are near and dear to my heart. These were done at Kennedy Airport, a test pile program just about 30 years ago. I was not involved in this test pile program, but Fellini was, which is why he is the senior author of the paper that discusses this case history. You're going to be seeing there were two piles, pile 2, pile 3. Pile 3 was they had some problems with installing pile 2. They hit some obstructions during installation, so the pile 3 is actually the more reliable data, but pile 2 is still useful. We're going to be looking at these many times throughout this presentation in different contexts. So these were monotube type J piles. Type J is the intermediate taper. You had, as you can see there, just about 20 meters long, so about 65 feet in length. You had a constant diameter section, and then you had a 25-foot long tapered section. So the monotube pile, if you're not familiar with this is a closed toe steel pipe pile. It has a tapered lower portion, a constant diameter upper portion. This is cold form steel. This is driven into the ground by impact, and then you concrete the core with fluid concrete afterwards. Now in this case, the load measurement instrumentation was installed inside the steel pipe after driving and prior to concreting, which are very, very common. Closed toe steel pipe piles, some people call them shell piles, are very, very common in the New York City metropolitan area. Sometimes they're constant diameter, sometimes they're tapered. The ones at Kennedy Airport are almost all tapered, similar to this. So the measured loads that are depicted here by the dashed blue curve were based solely on measured strains within the concrete core during the static load test. Static load test, unfortunately, did not go to a high enough level of settlement. I would have liked to have seen a little bit more settlement, especially in pile 3, but it is what it is. Now note that the measurements implied that, again, these piles were loaded to close to the geotechnical ultimate load. The measurements implied that there is basically no tow resistance. So you might look at the measurements and say, wow, look at this. These piles have almost no tow resistance, so I got everything is carried in friction. Well, nothing could be farther from the truth. Because you have a very significant residual load in both cases. And these residual loads indicate that almost 100% of the tow resistance was mobilized just by driving. Now, one of the things I want to point out, because of the way these measurements were made, the compressive stresses in the steel pipe from residual loads were ignored. We're going to see the implication of this a little bit later on. So here's the equilibrium plane after driving under residual load conditions. Again, quite low. These were about 20-meter embedment, and we could see that the equilibrium plane is about 17 meters into the ground. So this is a very typical distribution of residual load for this type of taper pile. And as I said, almost 100% of the tow resistance was mobilized as residual load. So now the true load is substantially different from the measured load, because the true load is the measured load plus the residual load. And clearly you have even though this tow diameter is only 8 inches, so about 200 millimeters roughly diameter, even though the tow diameter is fairly modest, you have a fairly significant tow resistance that the measurements completely did not pick up because they ignored residual loads. So the true load gives you a much different picture of how these piles were carrying load geotechnically. And this is the point I'm getting at about residual loads, that, there's the good and the bad. Overall, geotechnically, they're positive, but the bad part is, unless you correctly interpret the positive results, you can really get some negative interpretations. And the reason I'm emphasizing this so much is, I'll make the point later on more formally, that unfortunately these kind of measurements from instrumented load tests are where we get our resistance calculation methods from. And we'll see now why just about all resistance calculation methods underestimate tow resistance and overestimate shaft resistance. So, as I said, this has very serious implications, as there are countless resistance forecasting methods that have been and still are in everyday use in design practice that were either developed or calibrated using distributions of shaft and tow resistance inferred from instrumented static load tests that were not corrected for residual loads. And unfortunately, forecasts of shaft resistance that are too large combined with tow resistances that are too small are two wrongs that do not make a right. You can't say, well, okay, the shaft and tow resistance is wrong, but they cancel each other out and I get the right answer. No, you don't get the right answer. You get the wrong answer every time. And again, this is not just me, John Horvath, talking. As recently as earlier this year, Fellinius made this point in the chapter of his Red Book where he talks about pile load tests. Forgetting that piles are subjected to residual force throws the most elaborate instrumentation and analysis scheme to the wind. All right? You wind up with a case where bad data are worse than no data at all. It's interesting to note that these same issues with getting incorrect results by ignoring residual loads exist with newer resistant measurement methodologies that are based on dynamic measurements. This is from another Fellinius paper where he shows the results of some dynamic measurements. In this case, measurements made using the proprietary CapWAP software. Right? This was an interpretation. As you know, CapWAP can give you an interpretation of shaft and toe resistance distribution along a deep foundation element. And as you could see, it was incorrect. It's incorrect because these are the residual loads. Here's the, again, very, very common residual load distribution where you get this bulge down near the toe of the deep foundation element. And as a result, the true distribution is substantially different than what the CapWAP interpretation gave. In this case, you had, it looks like about maybe 20%, something like that, 25% perhaps, of the toe resistance was mobilized. I'm going to show you on this slide, note that the interpreted residual loads in driven piles based on these wave-based field measurements such as CapWAP have the same qualitative distribution as the interpreted residual loads based on instrumented static load tests that I showed you previously. So what I'm showing you on this slide is that the distribution of, this is the wave-based measurements. This is a driven pile static load test. This is a jack pile instrumented static load test. And you'll notice that the residual load interpretation in all these cases is very similar. It's of interest to compare these estimates of residual load to the measurements that were made in the Holman Island test piles. That's what I want to show you here. Oh, this graph gets a little bit complicated. What I'm trying to show you here is that the interpreted residual load profiles are reasonably similar to what was measured in the Holman Island test piles back in the 1960s. So here are the two Kennedy Airport test piles I just showed you, pile 2, pile 3. Very significant toe resistance mobilization. And these distributions broadly agree with the actual measurements. There are a total of 4 different test piles driven at Holman Island. 2 that were constant diameter, 1 that was tapered, and 1 that was a half tapered, half constant diameter. So what I'm just trying to show you with this slide is that the interpretations of residual load are not just some figment of somebody's imagination. They were a very broad agreement. And by the way, notice the way the scales I've plotted here. I'm showing you here the relative residual load in a pile. So this is a dimensionless number from 0 to 1. This is the residual load divided by the ultimate geotechnical resistance. So this allows us to compare apples to apples. And similarly for the depth, I'm showing you the depth below ground surface normalized to the embedded length of the pile. So it goes from 0 to 1. So even though all these piles are very different, this allows a comparison. And you can see here in the Holman Island pile, especially this this solid blue curve, this is the Holman Island, what they call pile BC, which was the upper half was constant diameter, lower half was tapered. You see in Holman Island, the peak mobilized residual load was about half of the ultimate geotechnical resistance, quite substantial. So certainly with driven piles and jack piles, residual loads are very, very substantial. Now, with other types of deep foundations that Fellinius has looked at, he's looked at drilled shafts, for example. Perhaps surprisingly, there are residual loads in drilled shafts, although they do tend to be very modest. I think what we do need in the profession is we need to have residual load measurements made for a lot of these drilled pile technologies, as well as some of these piles that are screwed or torqued into the ground. I think it was a necessity that we do some high quality measurements to see what the residual loads are on those types of deep foundation elements. So I want to move on. I want to talk about the effect of residual loads on the structural behavior of a deep foundation element. Now here, the results are almost all negative, so we got to be very careful because although the thesis of this presentation is that we need to change the way that we design deep foundation elements for axial loads from the geotechnical ultimate limit state to the geotechnical serviceability limit state, we always need to consider the structural ultimate limit state. We can never forget that. We can never leave that behind. The reason residual loads can be problematic structurally is that unlike with geotechnical behavior where we can always reverse negative shaft friction to positive shaft friction, once we have axial compressive loads locked in from installation, residual loads, they don't disappear when we apply externally applied loads, at least in axial compression. So stated another way, the effect of residual loads from installation cannot be reversed or erased by the application of post-installation compressive loads, at least structurally. An additional issue is that unlike with geotechnical behavior where residual loads impact only deep foundation behavior under axial loading, the structural effects from residual loads can affect behavior under horizontal and moment loading as well. And this is because the compressive normal stresses from residual loads are additive to and cumulative with the normal stresses created by the flexure of a deep foundation element shaft that resists from horizontal and moment loading. And I'll show you what I'm talking about qualitatively in a minute. Okay, these next few slides are going to get a little complicated, so let me make sure we go through them slowly. We've seen these plots before. These are simply from the Holman Island test program in Norway, and showing you the distributions of drag load, negative shaft friction, positive shaft friction as a function of depth under different load conditions. I'm now going to introduce a second plot, and what I'm showing you here is the axial compressive force in these piles in kilonewtons. Kips are down here if you want imperial units. Again, these are 16-meter long piles, a little bit more than 50 feet. So first let's look at the residual load case. All right, so here's the distribution of shear stresses along the pile shaft at the toe, equilibrium plane, and this is the axial force in the pile. And again, this is of the 4 piles they tested. This is the 16-meter long constant diameter pile. So of course, under residual loads, you have no load at the head of the pile, but notice that the loads, of course, the forces reach a peak at the equilibrium plane and then drop down. Now, because this is a constant diameter pile, the axial compressive stresses in the pile shaft will also peak here at the equilibrium plane. Well, what happens if I apply the maximum service load of 230 kilonewtons, which is 1/2 of the ultimate geotechnical resistance? The equilibrium plane, of course, moves upward. We convert some of the negative shaft friction to positive shaft friction, which is resistance in this case. We now have a 230 kilonewton applied load at the head. But notice that this is not the peak force in the pile shaft. The peak is actually down here at the equilibrium plane. So we apply 230 kilonewtons at the head, but the peak force is actually 275 kilonewtons. This is important because let's say we were designing these piles to be production piles, and we were designing for the service load case. Normally, we would think this is the maximum service load in the pile shaft, and the service load would only decrease with depth, so we would say, okay, if I'm checking my stresses in the pile shaft, here's my maximum applied service load divided by the pile cross-sectional area, and I have a certain safety factor. But the reality is your safety factor is lower than you think, because actually the peak forces in that pile are 20% higher than you think. And therefore the peak stresses in the pile are 20% higher, and therefore the safety margin you have structurally is less than you think. All right, so this puts some hard numbers on the point I'm trying to make, that neglecting residual loads certainly can be problematic geotechnically and can be problematic structurally as well. On this slide, I want to illustrate a point I made a little while ago, and that is residual loads in piles structurally not only affect piles subjected to axial loading, but also lateral and moment loading. Let's say you had an application where you had, in addition to vertical loads, you had significant axial moment loads, or even if you didn't have any axial loads. I mean, I've certainly have seen in marine applications, I've seen piles that were basically just used as what we call fendering or berthing piles, where they basically have no structural load applied at the head, but all you do have a horizontal load from the vessel impact. So the point I'm trying to show you here is that, as we know, under shear and moment loading of a deep foundation element, that the moment distribution will typically look something like this. The maximum moment is going to occur something below the ground surface or mud line. The interesting point here is that notice that the peak force due to residual loads is going to be below the ground surface, and the peak moment and stresses from lateral moment loading will also occur below the ground surface. So the point I'm getting at is these two peaks can be very close to each other, and the axial compressive stresses you get from residual loads are of course going to be additive to the positive and negative compressive stresses, normal stresses that you get from the shear and moment loading. Well, I want to look at those Kennedy test piles from 1994 again, and now we want to look at, in this case, we're going to look at the structural details. Now, this is going to get kind of complicated, so let's go through this slowly. So I'm going to focus just on pile number 3. Now what I'm showing you here is I am showing you the residual load that has been normalized to the maximum applied load and expressed as a percent. So it goes from 0 to 100%. And this just shows you how the residual loads increase as a function of depth, as a function of applied load. And this shows you the normalized depth below the ground surface. And this is the transition point between the constant diameter and tapered section of this monotube pile. And again, what this is showing you is that at the toe, we've mobilized 100%, near almost 100% of the ultimate toe resistance is mobilized as residual load. So again, this distribution is the percent of the ultimate resistance that is mobilized as residual load. All right, this is where things get a little bit complicated. On this graph, I'm going to be showing you the applied load in kilonewtons. Kips are down here. Again, normalized depth. We see the transition between the constant diameter and tapered sections. And here I'm going to be showing you stresses. Now, again, these are concrete-filled steel pipe piles, so we're going to be looking at both steel stresses and concrete stresses. Let's first look at what's happening in the steel pipe. Again, with these monotube piles, as with pipe piles in general, closed-toe pipe piles in general, you drive them into the ground with the inside closed toe with the inside hollow. So here's the residual load in the pile. Here's the equilibrium plane. And here's the stresses, megapascals and kips per square inch, of the residual loads in the pile. Now, this is an interesting case where, as I pointed out to you previously, what you have to be careful of structurally with residual loads is even though the force is at its maximum at the equilibrium plane, the stresses are not necessarily at their maximum. And this is a case in point. So here's the equilibrium plane, but the maximum stresses in the steel shell or pipe occur down near the toe. And that's because although the residual forces decrease below the equilibrium plane, the stresses increase because the cross-sectional area of steel continues to decrease in this tapered section. So this is where you got to be careful when calculating stresses from residual loads in a tapered pile. So very significant, right? About 25 KSI. Right? Quite significant stresses. Right? About 150, 160 megapascals. Now let's bring the concrete stresses in the concrete core into the picture. Now, as you know, when you design a pile that has a composite cross-section, in this case a closed-toe steel pipe pile filled with concrete, you do a simple calculation to apportion how much load and stress is carried by the steel shell and how much is carried by the concrete core. And you do that by doing a simple calculation by assuming that the strains are the same in the steel pipe and the concrete core. So the strains are the same, but of course the moduli of the two material are very different, and this is going to give you the stress in each component. So this is what I say based on the traditional stress-free wished-in-place model, where neither the concrete core nor the steel shell has any stress after insulation. This would be the theoretical load shared between the two. Okay, this is a very simple calculation to do. Those of you in design practice, I'm sure have done this a million times. So based on the traditional stress-free wished-in-place model, we think this is the load sharing. We think this blue curve, solid blue curve here is the stress in the steel shell, and we think the solid dark red curve here is the stress in the concrete core. All right, very nice. Very wrong, because we have ignored the residual loads. All right, we've ignored the fact that the steel shell is already significantly pre-stressed, especially down in the tapered section, whereas the concrete core, until it is poured and hardens, it carries no load. So this is the actual shared load, and this dashed blue curve shows you the stresses in the steel shell, which are the theoretical plus the residual. And you notice their maximum stresses in the steel shell are almost 30 KSI, almost 200 megapascals. Very, very high. Whereas in the concrete core, the dash curve, the concrete stresses in the concrete core are much less than you think are there. In fact, down near the toe, the concrete core is not doing anything. It's not carrying any load in this case. So this is a very important point about residual loads structurally. They can be extremely problematic when you have especially a driven pile with a closed toe steel shell or pipe that is then concreted after installation. If you use your traditional Wishton-Place model to apportion the stresses in the material, you're going to be significantly in error. You're going to grossly underestimate the stresses in the steel shell, and you're going to grossly underestimate the stresses in the concrete core. I've never heard anybody talk about this, but yet it's very clear. This is what happens. And here you see the difference. This is what you think you have in terms of stresses in the steel shell. This is what you really have. This is what you think you have in terms of stresses in the concrete core. This is what you really have. And notice that in the steel shell, there's almost 100% overstress in places down here within the tapered portion of this pile. Right? That is certainly not negligible, to use a double negative. That is not negligible. Now, separate from but related to the material normal stresses within a deep foundation element shaft that are due to residual loads from installation are the manufacturing residual stresses we talked about previously. Nowadays, the steel pipe that we use is almost always spiral welded as opposed to seamless, which was predominant in the past. All right, when I started out in this business some 50 or so years ago, steel pipe piles, whether constant diameter or tapered, were made out of seamless steel pipe. In fact, specifications I was used to dealing with did not allow spiral welded steel pipe, where you take a strip of steel, you turn it into a circle, and then weld the spirals. And that was because they had a lot of quality problems with the spiral weld. And it was not uncommon. You could be driving a spiral welded pile, and the spiral welds would fail, and the pile would literally split apart during driving. They've gotten much better with that, to the point where for the last couple of decades, all I see, at least here in the New York City metro area, is spiral welded pipe, whether constant diameter or tapered. And this is what spiral welded pipe looks like after installation. This happens to be a slide that was taken at Kennedy Airport some years ago. And you can see the spiral welds here. I always like this slide. This was actually it was the upper portion, constant diameter portion of a tapered steel taper tube pipe pile that was driven to Kennedy Airport. And what happened here is that the pile was not aligned properly in the leads. So during the driving process, the pile hammer was not impacting the pile uniformly at the head. It was hitting stronger on one side, and actually caused this had been the head of the pile during driving, and you could see it yielded. You get this very nice accordion-shaped yielding at the head of the pile. And this piece was cut out after the pile obviously was rejected and removed. But I like this slide, the positive part of the slide. It shows you that spiral welded pipe has come a long way. That here you can see the spiral weld here. I mean, the classic guideline for good welding is that the weld should be stronger than the parent material on either side. And that's what we're seeing here. This weld was stronger than the yield strength of the steel, which collapsed like an accordion up here. Anyway, the point I'm getting at is a point I made previously, and that is that we do have these mill or residual stresses or rolling stresses in steel members. I've never seen these mill stresses or rolling stresses ever talked about when we're talking about checking the stresses in a deep foundation element. It's not even mentioned in the published literature, no less discussed. The significance, of course, is that these residual or mill or rolling stresses are really additive and cumulative with the normal stresses from residual loads as well as post-installation loading. So to sum things up, residual loads from deep foundation element installation impact both the geotechnical and structural behaviors of a deep foundation element in multiple ways, so that, in my opinion, residual loads should always be considered both in routine design practice, certainly in academic research, especially when the outcomes of academic research produce analytical methods that we use in design. This is both valid for the current design state of practice based on the geotechnical ultimate limit state, as well as for the change practice based on the geotechnical structural limit state that I'm talking about in this presentation. What we really need at this point in time is for everybody to recognize and accept the fact that residual loads exist, and it's mission critical that we consider these residual loads for all types of deep foundation elements, both in design practice and academic research, and that we deal with them correctly. Again, these are facts that are not going to go away simply because they're inconvenient. We need to revisit this research that was done back in the 1980s, where people were trying to come up with user-friendly ways to forecast residual loads during the design process so that we can incorporate them in the design of deep foundation elements. So, having talked about residual loads from installation, I now want to talk about things that happen after installation, starting with the post-installation global settlement. Post-installation global settlement of the ground around and possibly beneath the deep foundation element is due to physical mechanisms that are external to and unrelated to the deep foundation element itself, but produce effects on the deep foundation element that can be relatively significant to the point where a deep foundation element fails geotechnically, even with no externally applied load. And I showed you an example of this earlier, of a pile that was pulled out of a pile cap. Obviously had no load on it. The physical mechanisms that result in global settlement can be a result of human activity or naturally occurring. Now, historically and still in the present, the focus has always been primarily on human activities that generally cause an area-wide increase in vertical effective stress within the ground at sites that are underlain by fine-grained soil strata. These stress increases are typically the result of a permanent increase in surface loads. Generally, this is the result of placing fill to what we call raise the grade as part of a project that also involves deep foundation installation to support a structure or structures. But we can also have long-term groundwater drawdown. This is usually the result of groundwater extraction for water supply at sites that are underlain by fine-grained soil strata, and these can have the same effect. Now, more recently, there's been increasing interest in sites with coarse-grained soil that can potentially be impacted by transient naturally occurring phenomena such as earthquakes that cause soil densification, with long-term consequences in the form of permanent settlements that are broadly identical to long-term gravity loads on site with fine-grained soils. Now, these seismic-induced settlements are most commonly the result of liquefaction. However, it's important to note that research has shown that some seismic densification in saturated coarse-grained soils can occur even when the calculated safety factor against liquefaction is greater than 1. So regardless of the specific physical mechanism, it is relevant to again note that only a relatively small displacement of several millimeters, a fraction of 1 inch, between a deep foundation element shaft and the ground around it is required to mobilize shaft friction. Well, for historical reasons, the long-term gravity conditions that affects most sites underlain by fine-grained soils is addressed first. It's interesting that this phenomenon began to be regionally recognized and formally studied as far back as the 1960s in several countries such as Japan, Norway, and the United States, although it was reportedly noted anecdotally in publications for some undefined period of time before that. The physical mechanism involved here is typically some anthropogenic, some human activity that causes a more or less permanent increase in vertical effective stress on an underlying stratum or strata of fine-grained soil, and this results in settlement of the ground surface that usually continues for some period of time that can be years or even decades in some cases. I've seen sites here in New York City metropolitan area, very thick fine-grained soil deposits where the time to complete consolidation approaches 100 years in some cases. Now, as I said, the most common example of what's causing this is an aerial fill placement, what we refer to as raising the grade, at a site where deep foundation elements either have been or will be installed. And of course, this could be exacerbated by additional fill placement in the future to compensate for settlements, as this creates and perpetuates a never-ending cycle of fill and settle, fill and settle. Another common example, and certainly I've seen this doing projects here in New York City harbor area, another common example, an open body of water, is the never-ending cycle of natural sedimentation and settlement of the mudline. You could get the same never-ending cycle of filling and settling. In this case, the filling is occurring naturally due to sedimentation in a body of water. Now, regardless of the specific physical mechanism involved, the effect of global settlement on a deep foundation element is much more complex in its implications and consequences and resulting effects on the analytical process compared to the residual loads from installation that we just talked about. And there's several reasons for this. First of all, ground settlement, which is the driving cause of this problem, varies over time. The post-installation externally applied loads on a deep foundation element may vary over time as well. And the same activity that caused the global settlement in the first place will, in most cases, cause a permanent increase in vertical effective stress in the ground, and thus result in increase in the soil shear strength. So this change in soil shear strength will in turn increase both the negative and positive shaft friction as well as toe resistance that produce the ultimate geotechnical resistance of a deep foundation element. So what we're saying here is that you can actually have the geotechnical resistance of a deep foundation element increase over time as the effective stresses in the ground increase. So there's a lot of different things going on, and these things it's not a one-time only thing as with residual loads from installation. These are things that are occurring continuously over some period of time that can be many decades. So the net result is that now time becomes an essential variable in the analytical process, so that you need to now bring the design life of a structure supported by deep foundation elements into consideration. Now, as with residual loads, there are both geotechnical and structural aspects that need to be considered when it comes to global settlement. The heart of the problem is the down drag, which is the deep foundation element settlement that occurs due to the ground settling around and possibly below a deep foundation element, with the magnitude of this down drag equal to the magnitude of global settlement that occurs at the equilibrium plane. So clearly this is a settlement or geotechnical serviceability limit state issue. It's not a strength or geotechnical ultimate limit state issue. And then we have the drag loads caused by the down drag that occur within the deep foundation element shaft. And clearly this is a structural ultimate limit state issue. Now it's important to note that in any situation involving global settlement, either the settlement, the geotechnical serviceability limit state, or the structural ultimate limit state can be the more critical issue, but they will never reach peak criticality together. But the overall most important thing to recognize is that note that in no case is there ever a geotechnical ultimate limit state issue. And this gets back to something that I was emphasizing earlier in this presentation and will continue to emphasize, that all of these cases involving drag loads are never reduce the geotechnical ultimate resistance. Now, as with residual loads, the negative shaft friction that results from global settlement and produces drag load must always be balanced by a combination of positive shaft friction and resultant force plus toe resistance. What is different in this compared to what we looked at previously with residual loads is we now have to consider an externally applied load at the head of the deep foundation element. And you only apply the unfactored dead or permanent load, Q sub D, at the head of the deep foundation element when you're doing an assessment of the effects of global settlement. Now, note that for many structures, the unfactored dead load or permanent load does not change during the life of the structure, although there can be situations where this load may change if there are permanent modifications made to the structure after its initial construction or some other factor. So you have to, there might be a case where you have a situation where you have to go back where the dead load on the structure has changed, and you have to consider that change in the dead load. Note that the externally applied live load, Q sub L, is never ever included in this force equilibrium assessment, as there will be an increase in the resistance that is matched exactly by a reduction in the drag load as live loads are applied to the head of a deep foundation element. And again, we saw this previously, where the deep foundation element shaft will compress and settle further when the live load is applied. So if you apply live load to a structure, this will always cause some of the negative shaft friction that contributes to drag load to reverse into positive shaft friction that provides resistance. And we've now seen this happen, that negative shaft friction is always reversible to positive shaft friction if you have some additional displacement of the deep foundation element shaft. And I'm just illustrating that to you here, where if I add in some live load, I'm going to get some additional shaft compression plus additional settlement that will change some of the negative shaft friction to positive shaft friction, which is resistance in this case. And you note that the equilibrium plane moves upward as the live load is applied. So we've seen this before, that the equilibrium plane is always a dynamic active feature of deep foundation elements. It can always go up and down for any number of reasons, as a function of time, as a function of load application. So the bottom line, it means that the geotechnical effects of global settlement on a deep foundation element are always a deep foundation settlement or serviceability limit state issue. They are never a soil strength ultimate limit state issue. Here's an interesting case history from the 1960s, republished by Felinius. You see this in many, many publications. This was an interesting study done in Japan. This was a closed-toe steel pipe pile. You see the dimensions and the lengths over here. That was observed over a period of several years. And what's very interesting is that you could see the ground surface settlement changed over time. All right, there was about 125 millimeters, roughly 5 inches of additional ground surface settlement over a period of several years. This is all fine-grained soil. And as a result, this caused the head of the pile to settle an additional 60 millimeters, or about 2.5 inches. And eventually, the equilibrium planes stabilized at about a depth of about 30 meters, or about 100 feet. And again, the overall embedded length of this pile was 43 meters, or 141 feet. So again, the equilibrium plane is relatively low in the along the pile shaft. And you can see how the drag load developed over time, and eventually reached a value of about 3,000 kilonewtons, or 680 kips, which caused a substantial stress in the pile shell of about 165 megapascals, or 24 kips per square inch. All right, and notice that this was a pile that had no externally applied load. All right, this was just a freestanding pile that was installed for observation purposes. Notice that over all this time, the load at the head of the pile remained 0. So all of this increase in settlement, notice how the equilibrium plane originally was up here and eventually dropped down to here as the settlement of the ground changed over time. And this continued to pull the pile down as the equilibrium plane dropped. So this was a freestanding pile that was always in equilibrium just from the stresses imposed by the ground settling around it. Now, the reason I'm emphasizing a lot of these points about how to properly deal with global settlement is that the current understanding of the true nature of how global settlement affects deep foundation elements, that is a combination of the geotechnical serviceability limit state in the form of settlement and the structural ultimate limit state of the shaft materials, evolved over time because the original understanding that existed in the 1960s and 1970s was quite different. And I can attest for this on a first-hand basis. Again, I began my professional career in 1972, working in the New York City metropolitan area. And this is an area where, in many places, global settlements are an important design consideration in practice. So, I was very aware of the state of practice with respect to global settlements that existed at the time of the early 1970s. Originally, the drag load on a deep foundation element due to global settlement was viewed as a permanent, unchanging design load in the same category as externally applied loads, dead and live loads. So you would sit down and you would calculate the estimated drag load, and you would deduct that from the theoretical geotechnical resistance of a deep foundation element to come up with a usable geotechnical capacity for that deep foundation. So the drag load was subtracted from the ultimate geotechnical resistance in addition to the dead load from a structure, the live load from a structure, determine what was left over for an allowable deep foundation capacity. If you want to read a really excellent example of the original design practice, original design philosophy on how to deal with global settlement for deep foundations, I would suggest this paper by York, Miller, and Ismail. I'm a bit biased. These were all former employees of the Port Authority of New York and New Jersey. I worked with them in the early 1970s. That's where I started my professional career. They were writing about a project at Newark Airport in New Jersey. I was not involved in this project at the time. I was heavily involved at Kennedy Airport, but I certainly, working in the same office with them, I knew of this project. And the Newark Airport site, when it was extensively redeveloped in the late 1960s, early 1970s, is underlain by a significant stratum of fine-grained soil. And so certainly they were aware of global settlement, but you can see from this quote, this is how it was dealt with. Right? Allowable pile loads were determined by deducting 75% of the computed drag down load from the design capacity. So as I said on the preceding slide, the way things were done originally is you would calculate the drag load. Here they call it drag down load, but you would calculate the drag load, add it to the dead load and the live load you got from the structural engineers. You would subtract that from the geotechnical ultimate resistance, and that would give you the quote-unquote allowable capacity of the deep foundation element. And by the way, the deep foundations they were talking about here, these were closed-toe steel pipe piles, constant diameter. They were driven to shale bedrock. And that's a scenario when you have a deep foundation element that extends through compressible soil to bear on or in sound rock. That's a scenario where the structural ultimate limit state tends to govern. The settlements tend to be in this case, piles are fairly modest because they're all end bearing on rock. So it's not much more than the elastic compression of the pile shaft. But you can get a very, very large down drag load simply because the equilibrium plane is almost at the toe of the pile. I should note, if you read this paper, that the interpretations of the load measurements were made on numerous instrumented piles, but they all suffer from the fact that the piles consisted, as I said, of a closed-toe, constant diameter steel pipe. that was concreted after installation. So like those test piles at Kennedy Airport, they installed the steel pipe, placed the instruments inside the pipe, and then concreted the core. So if you read this paper, you will find that the measurements from the instrumented pile load tests are incorrect because they did not consider residual loads. Residual loads were not, they knew about global settlements, but they were not aware of residual loads at the time. And this was a case where there were undoubtedly significant residual loads that were unfortunately not considered to get the true load distributions. Another aspect of the test program that York et al. Discussed in their paper that's relevant to what we're talking about here is that they instrumented and monitored piles that supported an elevated roadway as opposed to one of the terminals at Newark Airport. And they did this intentionally so that they had complete control over live loading. So before these roadways were open to the public, they did some tests where they could move vehicles on and off the elevated roadway in the vicinity of the test piles in order to measure the effects of live loads. They were interested to see how live loads might affect the drag loads on the pile. So with this in mind, it's interesting to, I'll quote two statements they made in their paper in the conclusion section that are relevant to what we're talking about here. First of all, they said the application of structural loads obliterated the effects of drag down loading, and the application of transient loading reduced the drag down loading. So I worked with these people at the time. I was not involved in this project, but I remember discussing things with them because I was involved in pile design at Kennedy Airport. And I remember at the time they were surprised that the application of live load would actually reduce the drag load. Because again, keep in mind that thinking at the time was that drag load was always going to be there. So that's why you had to add it to the dead load and live load, because it was never going to change over time. But their observations simply confirm what I've already said to you and showed you previously, that the effects of negative shaft friction are always completely reversible if you cause a pile to settle enough. Now, in this case, they were not able to get rid of all the drag load because since the piles were end bearing on rock, when they applied live load, that would simply create some elastic compression. It really didn't cause the pile toe to settle at all. So they were limited as to how much drag load they could remove, simply because they were limited as to how much they could get the pile head to settle. So as I said, these statements support the discussion earlier in this module that the application of live load to the head of a deep foundation element simply reverses negative shaft friction from down drag to positive shaft friction as resistance, which supports the current understanding that drag load should never be treated as a permanent design load as was done in the past. And again, as this is what I showed you previously, that when you apply a live load, what it does, it causes some additional settlement at the head of the pile shaft and will reverse at least some of the negative shaft friction caused by down drag. And this is what they were able to measure at Newark Airport in the 1970s. The fact that some of the drag load was removable by application of live load. In any event, this original thinking of how to deal with drag load resulted in numerous situations where, after deducting for drag load, deep foundation element had no allowable capacity left over for externally applied loads, at least on paper. So has been noted in technical publications authored by Fellinius numerous times in past decades, it appears that there are still some design professionals who have not gotten the memo, if you will, on how to properly deal with drag load caused by global settlement, and still cling to the flawed logic of the 1960s and 1970s, as I've explained here. Unfortunately, there are some design codes and manuals that adhere to this original, now deprecated way of doing things, where they consider drag load from global settlement to be a never-changing design load that you have to add to dead load and live load. So, as I noted earlier, in recent years, interest in the effect of global settlement has broadened from the traditional focus on long-term increases in vertical effective stress on sites underlain by fine-grained soil to include sites underlain in whole or in part by coarse-grained soil, and physical mechanisms that are transient and dynamic in nature, such as earthquakes that can cause seismic liquefaction and seismic densification in coarse-grained soils. The significance of seismic liquefaction and densification is that permanent ground settlement that can affect the deep foundation element occurs not only within the zone or layer of soil that liquefies or densifies, but all the soil strata above that layer. So this results in additional settlement of the deep foundation element, and therefore the structure supported by the deep foundation element, and both of these occur relatively quickly. So unlike with global settlement from, say, a fine-grained stratum that compresses over a period of years or decades, where the settlements increase slowly, when you have something like seismic densification and liquefaction, these settlements can occur very, very quickly. Now, a review of recent and current publications such as the California Transportation Department Caltrans Geotechnical Manual, as well as papers by Fellinius that discuss the subject, reveal a complex relationship between the ground and a deep foundation element during and after a seismic event where liquefaction occurs. During an earthquake, coarse-grained strata that liquefy temporarily lose their strength. This changes the vertical force equilibrium of the system, consisting of the externally applied load, any pre-existing drag load from residual loads and global settlement, shaft resistance, toe resistance. So all of these forces acting on the deep foundation element and will tend to result in some immediate settlement of the deep foundation element as it establishes a new vertical force equilibrium. So when a coarse-grained stratum liquefies and temporarily loses its strength, the geotechnical resistance is going to temporarily decrease. Now, after an earthquake, there will be permanent vertical compression of the coarse-grained stratum that liquefied, and you're going to get settlement of all the strata above that liquefied stratum. What a lot of publications overlook is that even coarse-grained strata that do not liquefy can densify and compress as the result of seismic shaking. I've seen reports where, people did studies for a project and they said, well, we looked at liquefaction. It's not going to happen, so you don't have to worry about settlements. Well, just because the safety factor against liquefaction may be greater than 1 does not mean that the earthquake cannot cause some settlement. And this is an interesting graph that I found in the Contech CPT design manual. This is one of the documents I showed you earlier in this presentation. What we're looking at here is the safety factor against liquefaction and the post-liquefaction volumetric strain that occurs. And I want to focus on the zone where the safety factors are between 1 and 2, and the fact that you could still get some post-liquefaction volumetric strain even though you theoretically are not going to have any liquefaction. All right, so you could still get some not insignificant volumetric strain, certainly enough to generate drag load. So the aggregate of these vertical compressions, both during and after seismic liquefaction and densification, will produce negative shaft friction and thus drag load along those portions of the deep foundation element shaft that were perhaps previously subject to positive shaft friction and shaft resistance. And this is going to result in additional settlement of a deep foundation element that develops very rapidly in order to reestablish overall vertical force equilibrium. And this comes from a paper by Felinius and Siegel. And what they're illustrating is what happens if you have a stratum that liquefies. These are the distribution of drag load and resistance during liquefaction below the neutral plane. So notice that when you get liquefaction, you're going to get a sudden increase in settlement of the deep foundation element, because what happens? This stratum liquefies, it compresses, and even if that compression is fairly modest, it's going to cause everything above it to settle. And that's going to increase the drag load, and is now going to cause the head of the deep foundation element to settle. And again, the thing that's important here is this occurs all very rapidly. You know, again, unlike with the more common case of fine-grained soil where the drag load and the settlement can develop over a period of years or even decades, when you have drag load develop as the result of seismic activity, the settlement of the deep foundation elements can occur very quickly. We're talking about a matter of minutes, for example. Well, I now want to move on to the third and final source of loads on a deep foundation element, and this is a more detailed discussion of the thermomechanical behavior of energy piles. Deep foundation elements used in energy pile applications present some unique and interesting technical challenges that did not occur previously in all the preceding millennia of deep foundation usage. First of all, there is a thermomechanical component of deep foundation element axial force displacement behavior that is unique to energy piles, and it's completely independent of, but additive to, the previously discussed geostructural force displacement behaviors related to residual loads from installation and post-installation global sediments. Now, thermomechanical behavior occurs because the temperature within an energy pile shaft is constantly changing over time. And typically this occurs in a cyclical pattern over the time frame of a calendar year that is related to heating and cooling seasons in a temperate climate. These thermal changes cause volumetric changes in the energy pile shaft materials that result in cyclical axial displacements and forces. Now, there are also horizontal displacements of the energy pile shaft due to Poisson effects of the axial forces. The thermomechanical behavior of an energy pile has the potential to dominate overall foundation behavior. An unanswered question, at least as far as I could tell, having done some research into energy piles now, the unanswered question at this time is whether these thermomechanical axial displacements and forces in an energy pile are fully reversible for each annual thermal cycle, or if there is some irreversible cumulative effect in one behavioral direction or the other over time as the result of what is called ratcheting in geostructural applications that involve earth retaining structures. If you're not familiar with ratcheting in earth retaining structures, I've done a lot of research with this over the years. This is the result of the inherent nonlinear hysteretic behavior of geostructural systems, such as integral abutment bridges, that are inherently subjected to many annual cycles of thermal loading during their design life. There are many geostructures, especially earth retaining structures, that go through annual temperature swings. And these annual temperature swings can lead to ratcheting. And in the case of integral abutment bridges, ratcheting occurs. Lateral earth pressure on the abutments permanently increases over time. And at some point in the future, and it can even be decades later, can cause structural distress or even the structural ultimate limit state or collapse failure of an abutment. I discussed the phenomenon of ratcheting in detail in my monograph on earth retaining structures, and you could get an overview of the subject in my YouTube presentation. That's a summary of this monograph. Now, if ratcheting were to occur with energy piles, I'm not saying it will, but it certainly is a very realistic possibility. It would likely exhibit itself as a combination of displacement and forces in one direction or the other that would continue to increase over time. Now, this ratcheting is not necessarily bad. It just is something that we need to anticipate during design because these geostructures that go through temperature cycles, for example, integral abutment bridges, and in this case, energy piles, these would be expected to have a fairly long design life. So we need to anticipate any ratcheting effects for the design life of the geostructure. Now, as a direct result of the seasonal heating and cooling within an energy pile shaft, the temperature within the ground adjacent to the energy pile changes as well. Now, recognize that this is intentional and is actually a mission critical component of ground source heat pump applications, as the ground around an energy pile is, as I've said to you before, it's treated as a thermal heat storage device. I like to think of it as a thermal battery that can store up and release energy, store up and release energy. Think of it as a rechargeable battery. So, but instead of storing electricity, it's storing heat, just another form of energy. Now, it's typically assumed that the geothermal changes do not result in volumetric or shear strength changes within the thermally varying portion of the ground. I'm not sure this has been studied much, if at all, to date. Certainly is an interesting question, but for the time being, the assumption is that the only effect of the temperature change is on the deep foundation element itself, that is the energy pile, not on the ground, not on the ground strength. So it's assumed that the ground around and beneath the energy pile is spatially fixed and provides a constant geotechnical resistance throughout the design life of a structure supported on energy piles. Another unique aspect of energy pile applications is that the stiffness of the structure supported by the energy piles becomes an explicit part of the problem and its solution. This is because the externally applied load at the head of an energy pile is, at least in principle, not known beforehand during the course of an annual thermal cycle. Rather, the load at the head of an energy pile is, and again, this is at least in theory or principle, part of the calculated outcome during the design phase, as it can be larger or smaller than the design dead load on the energy pile from the structure in the absence of thermomechanical behavior. And it depends on how the thermomechanical changes that are produced at the head of the energy pile interacts with the structure. Specifically, there will be some combination of vertical displacement, up or down, depending on the thermal season, and vertical force change, increase or decrease, again, depending on the thermal season, that is produced at the interface between the head of an energy pile and the overlying structure. Now, what portion of these annual thermal changes occurs as vertical displacement versus vertical force change depends on the vertical stiffness provided by the overlying structure. Now, as noted previously, the thermomechanical behavior of an energy pile is separate from, but mechanistically additive to, the geostructural behavior of an energy pile that comes from residual loads from installation and global settlement after installation, as I discussed earlier in this presentation module. The additive nature of thermomechanical behavior to the other behaviors of an energy pile is discussed in this paper, which is a good introductory overview of the thermomechanical behavior of energy piles. And in this paper, the authors first talk about the thermomechanical behavior and then overlay the thermomechanical behavior on the geotechnical and structural behavior of energy piles. So the bottom line is, this is a very complex analytical situation, because you now have multiple sources of load and displacement that are occurring independently, but they produce the same basic effects in terms of axial displacements and forces. So all of these effects have to be overlain and added together in a complete design. Now, in the slides that follow, for clarity and to focus on the topic currently under discussion, which is the thermomechanical behavior of energy piles, I'm only going to show you the thermomechanical aspects of the problem. But it's important to emphasize that these thermomechanical aspects need to be overlain on the basic geotechnical and structural aspects of a deep foundation element that is serving as an energy pile. Right, so as I said, in practice, analysis of an energy pile requires combining the thermomechanical behavior and the geostructural behaviors into a single analytical model. The thermomechanical behavior of energy piles requires several specific considerations during the design process that are unique to energy piles. First of all, for reasons that are illustrated subsequently, it's always necessary to consider two thermomechanical design cases. One is what we call the peak heating season, and this is when the energy pile is typically at its lowest temperature, as heat is extracted from the ground via the energy pile and supplied to the structure. The other case is the peak cooling season, and this is when the energy pile is typically at its highest temperature, as heat is extracted from a structure and put into the ground, again via the energy pile. And again, I'll show you this graphic. The energy pile is basically acting as a pipe or conduit. It's a heat transfer element. The heat is not stored so much in the energy pile itself as in the ground around the energy piles. So you have a structure that you want to heat and cool using geothermal heat, and the energy piles are basically the conduit to connect the structure to the ground. It's the ground that is around the energy piles that is the heat storage device, the heat battery, if you will. So it's the ground that is the battery, the storage device. The energy piles are simply the thermal connection between the ground and the structure. The primary desired outcome for each design case is the vertical displacement. Both settlement and heave can occur at the head of the energy pile as a function of time for the design life of the structure supported by the energy pile, so that the serviceability limit state of the structure can be assessed. Also important for each of these two design cases are the temporal variations in the magnitude and depth-wise distribution of axial forces and normal stresses, and the normal forces and stress increments from thermomechanical behavior can either be compressive or tensile within the energy pile shaft. And these stresses are used for assessing the structural ultimate limit state safety margin of the energy pile shaft materials. Now, determining the depth of the equilibrium plane remains a mission-critical component of the overall calculation process, but the nature of energy pile ground stress state defined by the energy plane, equilibrium plane, is very different for each of the two design cases, as I will show you subsequently. The stiffness of the energy pile end-bearing mechanism plays a very significant role with respect to both the geotechnical serviceability, as reflected in the energy pile axial displacement, as well as the structural ultimate limit state, as reflected in the normal compressive stresses within the energy pile. And by end-bearing mechanism, I'm talking about the tow resistance of the energy pile. And this is especially true for the peak cooling season design case, when the energy pile shaft temperature is at its highest value, and the energy pile shaft tends to expand in length. So, as we'll see, as it expands in length, it's pushing at the ground beneath the tow, it's pushing upward on the structure, and then there, of course, is going to be shear resistance along the side of the shaft. But it's worth reiterating a point that I've already made several times, that at no point is the geotechnical ultimate limit state ever a crucial design consideration. So as we saw with residual loads and global settlements, a soil failure, if you will, the soil ultimate limit state is never the issue here. It's always serviceability of the deep foundation element, how much it goes up or down, as well as the structural safety of the deep foundation element shaft. Well, achieving these mission-critical calculated outcomes for energy piles is both complicated and challenging. The root cause of this complexity is that for any relatively slender structural element undergoing thermal changes, I'm sure you've all seen this in some structural engineering course, these changes are nominally one-dimensional in nature in a direction parallel to the longitudinal axis of the structural element. There are always two limiting conditions of thermomechanical behavior based on the boundary conditions at each end of the element. On the one hand, we have what we call the free end condition, where there is no restraint against longitudinal displacement. This produces the largest possible magnitude of longitudinal displacement due to temperature change, but no change in longitudinal force from that temperature change. And this is the equation I'm sure you've all seen before for calculating that length change based on the original length of the object and the change in temperature and the coefficient of thermal expansion of the structural materials involved. The fixed end condition is when we have no longitudinal displacement. The structural element is locked in at each end. And this produces the largest possible magnitude of change in longitudinal force due to temperature change. And here's the equation for calculating that force. Depends on the cross-sectional area, Young's modulus, the material, temperature change, and again, the coefficient of thermal expansion of the materials. Now, in most practical applications, actual behavior falls somewhere in between these two limiting conditions. That is, the boundary conditions at either end of the structural element are neither perfectly free nor perfectly fixed, but have some restraint against longitudinal displacement. This intermediate type of end boundary condition, which is applicable to energy piles as it turns out, means that thermomechanical behavior typically produces some combination of longitudinal displacement and longitudinal force. The challenge, of course, is quantifying the end boundary conditions on a site and project-specific energy pile applications. So how much change are we going to get in terms of longitudinal displacement versus longitudinal force? Now, published work to date, such as that 2012 geotechnique paper I showed you previously, indicates that energy pile behaviors typically falls between the two thermomechanical limiting conditions, although there are some unique complications and complexities. And by the way, in this paper, they did look at some actual energy piles that had been installed and were instrumented and monitored. So it's not just a theoretical exercise. There were some actual observations to compare theoretical calculations to. First of all, unlike many thermomechanical applications in structural engineering, the boundary conditions at each end of an energy pile, in this case the head and toe, generally have very different stiffnesses, so offer different amounts of restraints. In many structural applications, the boundary conditions at each end of the structural element are similar, if not identical. But that's not the case with energy piles. You have very, very different axial stiffnesses at the toe and the head. Now, as I'll show you in the phase 2 module of this presentation, the stiffness at the toe of an energy pile is straightforward to quantify for analytical purposes. So calculating what the stiffness is at the toe of an energy pile is quite doable in routine practice. It's what happens at the head of the energy pile that gets challenging, because this involves the stiffness of the structure as defined by a vertical force displacement relationship at the head of the energy pile. So, think of how the energy pile, the head of the energy pile, is connected to a structure, let's say via a pile cap. So if this energy pile at the head wants to go up and down, it's going to have restraint from the structure pushing the structure up and down. And what is actually going to occur is very application and structure specific. You can't generalize it. Well, in principle, this involves a fairly complex structural analysis to see what the vertical stiffness of a structure is at the point where it contacts the foundation. I think a practical way to deal with this, at least in preliminary design, is to simply bracket the problem. And you do this by performing separate analyses, assuming the limiting conditions at the head of the energy pile, that is, free end and fixed end. So what I'm saying here is that I think a practical way, certainly in preliminary design, when you have energy piles, you can always calculate the toe stiffness. That's not an issue. But for the head stiffness, you simply run two analyses, one with a free head condition, one with a fixed head condition, and you bracket the problem. Now, if there's a substantial difference between the two, well, clearly that means you need to do a more complex, more complete structural analysis. If the difference between the two is modest, you might forego a more complex analysis. So by bracketing the problem at the head of the energy pile, you get the maximum possible values of vertical displacement and vertical force and stress at the head of the energy pile. Now, unlike a typical structural element undergoing thermal-induced physical changes that is only supported at its ends, an energy pile develops additional restraint against longitudinal displacement from shaft friction due to sliding friction. And if you were to have a tapered energy pile, you would have wedging and unwedging as well. So this is yet another complication with energy piles. It's not just the axial restraint at the head and toe we need to model. We need to model the fact that the energy pile is sliding along the ground along the entire shaft. So we need to take this shaft friction into account. when calculating the thermomechanical axial displacements and forces. So this means that the stiffness, the modulus, if you will, of the ground and the shear strength of the ground along the energy pile shaft both play a role that must be taken into account. And this point was also made in this 2012 geotechnique paper that I showed you previously. They looked at various stiff and soft ground conditions, to use colloquial terms, just to show that the ground stiffness plays a role as well. So in summary, it appears that deep foundation element design and energy pile projects requires routine consideration of at least 4 design cases based on combinations of peak heating and cooling seasons, and for each of these peaks, the limiting conditions of free and fixed end connection between the deep foundation element and structure at the head of the energy pile. In each of these 4 design cases, the thermomechanical effects have to be combined with the geostructural effects of residual loads from installation and post-installation global settlement that were discussed previously. I'm going to show you the qualitative graphical illustrations of thermomechanical behavior during the peak heating and cooling seasons on the following slides. And again, this is only the thermomechanical aspect of the problem. You have to combine these thermomechanical effects with the geostructural effects to get a complete solution. So let's first look at the peak heating season. This is when heat is extracted from the ground to go into the overlying structure. And again, the deep foundation element acting as an energy pile here is the conduit for this heat extraction. This is going to cause the energy pile to cool down and to therefore shrink. So you're going to generate axial forces that are tensile in nature. You will generate tensile reactions at either end of the energy pile and contractive displacements at each end as well. You're also going to generate shear stresses along the energy pile shaft and the ground. Positive shear stress, shaft friction here, negative shaft friction here, and here's our old friend, the equilibrium plane. And on the next slide, I will define what the equilibrium plane represents in this application. Note the interesting change here. Everything we've looked at up till now with residual loads and global settlements, the negative shaft friction, if it develops, is always in the upper part of the deep foundation element shaft, whereas here it's down near the toe. So in the peak cooling season, we put heat into the ground, from the structure into the ground. So the energy pile is going to heat up and tend to expand. You're going to get expansive forces at each end, expansive displacements at each end, and the shear stresses along the energy pile shaft will be negative in the upper portion and positive in the lower portion. Now in this case, the energy plane defines the point in vertical space where the thermal induced displacements within the energy pile shaft are at a minimum and reverse the direction in which they act. The thermal induced forces within the shaft are at a maximum and reverse the direction in which they act. Note that the point within the energy pile shaft where the thermal induced normal stresses within the shaft are at a maximum depends on whether the shaft has a depth-wise constant perimeter or is tapered. So we saw this previously with global settlements and with residual loads, that you've got to be careful that when you have a tapered deep foundation element, the normal stresses within the shaft tend to peak at a different location than where the normal forces peak. And the equilibrium plane also defines the point in vertical space where the interface shear stresses between the shaft and adjacent ground change sign. So we can see that the outcomes from an energy pile analysis is that you want to look at certainly the forces and the stresses within the energy pile itself. So you could evaluate the structural safety margin, and you need to look at the displacements, especially at the head of the energy pile, that are going to affect the serviceability of the overlying structure. Now note that the analytical model I showed you ignores the Poisson effect that is known from published work to occur with energy piles. In that 2012 geotechnique paper I showed you previously, they instrumented the energy piles, and they also measured the radial expansion and contraction due to Poisson effects. And now I did some published research about 15 years ago with Regis Colasanti, and our work, and it was theoretical in nature, our work illustrated that omitting the Poisson effect may be reasonable for energy piles, although this does require verification. So certainly this is one of those many aspects like ratcheting that I think remain to be researched with energy piles. Okay, so we finished talking about the various load sources on deep foundation elements. As you now see, they are many and varied, many more potential load sources in addition to the traditional externally applied load at the head of a deep foundation element after installation. Before moving on to talking about geotechnical axial resistance determination, is one last topic to talk about with deep foundation ground interaction, and that is post-installation changes in the geotechnical resistance. And I'm talking about here changes in the geotechnical resistance that are due solely to the passage of time and are not related to increases in resistance that occur as the result of physical mechanisms related to global settlement that I discussed previously. Now, historically, it was recognized that the geotechnical resistance can change after you install a deep foundation element, and these changes were referred to colloquially using terms such as soil freeze when there was an increase in resistance, and soil relaxation when there was a decrease in resistance. Now, at one time, it was thought that these temporal changes in geotechnical resistance only occurred in soils with a significant fines content that underwent undrained shear during deep foundation installation, especially during pile driving. Pore pressure changes occur, of course, during constant volume condition of undrained shear, and these pore pressure changes can be positive or negative, as we know, depending on the state of the soil relative to the critical state prior to deep foundation installation. So as pore pressures equilibrate over time after deep foundation installation, the shear strength of the soil can either increase or decrease, result in the so-called freeze or relaxation in shear strength and concomitant geotechnical resistance. We're talking about something different here. In recent decades, there's been increasing interest in and use in routine design of the fact that some deep foundation elements, and this is especially true of driven piles, especially driven tapered piles, can exhibit relatively significant temporal increases in geotechnical resistance, even in conditions where the subgrade soils are predominantly coarse grain in nature with little or no fines content. So we're talking about here soils where we would not expect pore pressure issues to occur during and after driving. Now, one of the seminal studies of this phenomenon involved driven piles, and most of them were monotube tapered steel pipe piles that were installed at Kennedy Airport in the late 1980s as part of an extensive pre-construction foundation test program. The findings of the test program that are related to temporal increase in geotechnical resistance were presented and discussed in a landmark ASE paper by York, Brucey, Clementi, and Law that was published in 1994. Now, although the existence of the temporal gain in geotechnical resistance in coarse-grained soil has now been verified a number of times around the world in different research studies, the actual physical mechanism that is responsible for this increase in resistance is not identified with certainty. Fellinius has suggested that since the increased geotechnical resistance in coarse-grained soil is not due to changes in effective stress in the ground that result from equilibration of pore pressures, it's due to a change in ground stiffness. So this suggests that the geotechnical resistance of deep foundation elements is, at least in part, a function of ground stiffness, not ground strength alone as viewed historically. Now, this hypothesis of deep foundation resistance being governed by ground stiffness has been advanced independently by others in recent years, and I will touch on this a bit later on in this presentation, as it's a promising, useful methodology for analyzing and designing deep foundation elements for axial loading. Note that consideration of the temporal changes in geotechnical resistance for all types of soils complicates the consideration of residual loads, global settlements, thermomechanical behavior of energy piles, as changes in the position of the equilibrium plane that are due solely to post-installation changes in geotechnical resistance and ground stiffness need to be considered. So clearly this is an area where future research is still required. Well, let's now move on to the fourth of four major topics I'm talking about in this Phase 1 module, and that is the geotechnical axial resistance determination. And I'm going to start off by talking about some background as to the nature of this topic. The final topic I want to discuss in this Phase 1 presentation module is the determination of the geotechnical axial resistance of deep foundation elements. This is really an essential mission-critical task for which the state of practice has undergone considerable evolution over the last 2 centuries, and that evolution continues to the present. There are 2 broad conceptual approaches for doing this. One is what we call resistance forecasting, and again, I like the word forecasting and not prediction, in which the geotechnical resistance is calculated prior to installation of a deep foundation element, typically using what is called a static analysis methodology that is based on an assumed site-specific soil conditions and project-specific deep foundation element type, geometry, method of installation, depth of embedment, etc. And then we have resistance verification, in which the geotechnical resistance is measured either during or after installation of a deep foundation element by any number of methodologies. Now, nowadays, these 2 approaches are usually seen by most people as being complementary in routine practice, although there is no shortage of products where much more emphasis is placed on the verification approach, at times even to the complete exclusion of forecasting. And this is allowed by at least some building and design codes. So where the emphasis is between these 2 certainly varies, has varied over time, and varies even in the present. Now, historically, resistance verification was done routinely for at least a century before methods for resistance forecasting emerged. So for this historical reason, I'm going to talk about resistance verification first. Consistent efforts to rationally verify the geotechnical resistance of deep foundation elements during and after their installation can be traced back to the early decades of the 19th century and were broadly coincident with the emergence and recognition of civil engineering as a professional discipline that was distinct from military engineering. And we're talking about the time, around the time that organizations such as American Society of Civil Engineers in the United States and similar organizations in Europe were established. Now, from the early 1800s into the 1950s, resistance verification was limited to field methods using blow counts observed during pile driving in so-called dynamic formulas, and then confirmed by performing static load tests. This state of practice, which was the state of knowledge at the time, reflected the state of knowledge at the time, was reflected in Terzagh's seminal English language textbook that was published in 1943. And I showed you this quote earlier in this presentation. And basically Terzaghi is saying, in very simple terms, well, there's no way we can calculate what the axial resistance of a deep foundation is. This state of practice, which was more or less unchanged for over a century, did begin to change rapidly after World War II, 1950s, with the development of analytical methods for forecasting geotechnical resistance based on an assumed installed geometry of a deep foundation element and using concepts and principles from at that time, the relatively new applied science of soil mechanics. The development of the so-called static analysis methods began in the 1950s and continues to the present, although over time there's been a marked shift toward developing what are called direct methods that are purely empirical in nature, and they're based on correlations and develop parameters that are measured in some in situ test, such as a standard penetration test or cone penetrometer, as opposed to what are called direct methods, also called rational methods, that are based primarily, if not completely, on soil mechanics principles and fundamental soil properties obtained from site-specific pre-construction site characterization program. Now, with the development and evolution of digital computers, the miniaturization of electronics, the development of cellular communication, the trend in recent decades has been back towards much greater reliance on field methods conducted during or after deep foundation installation, and nowadays almost always is based on some solution from the one-dimensional wave mechanics, and this is used as the primary methodology for geotechnical resistance determination. So the point here is that we certainly have seen ebb and flow of the emphasis of how we determine or verify the axial resistance of a deep foundation element. Now, given the mission critical importance of geotechnical resistance determination on project of any size, where a deep foundation element is used for axial load bearing, it's essential for design professionals to understand all the nuances, the pluses, the minuses, the good and the bad, for all the different methodologies and methods that are used for this purpose. And note that this knowledge and understanding should include methodologies and methods used in the past, as in many cases they're used to develop and calibrate methods that we use in the present. Now, in the detailed presentation and discussion of methodologies and methods for geotechnical resistance determination that follow, two dominant field methodologies, static load tests and dynamic measurements, are discussed first for historical reasons, because as I noted, We were using these long before we were sat down and did static analysis calculations. And also for the fact that in recent decades, things have come full circle to where these field methods are often more dominant in routine practice than office-based static analysis methods. So certainly with field-based one-dimensional wave mechanics methodologies, there's more reliance than ever on making field measurements that determine axial resistance. Well, for historical reasons, I'm first going to talk about load tests. Now, as I've already noted several times throughout this presentation, static load tests have long been considered to be the gold standard for the post-installation determination of geotechnical axial resistance of deep foundation elements. This is going back to at least the 19th century, and that's well before the evolution of modern geotechnical engineering. And this remains true in the present, even though there are now field testing alternatives for estimating geotechnical axial resistance during the deep foundation installation process. We have dynamic methods based on one-dimensional wave mechanics that are used either during deep foundation installation in the case of conventional pile driving, or after deep foundation installation in the case of deep foundations created or installed by some other process such as drilling. And then we have rapid methods that are intermediate between static load tests and dynamic methods. And these typically involve some proprietary technology to apply a force of relatively short duration to the head of a deep foundation element after installation. And the data reduction for these methods requires that you have to filter out the dynamic component from the static component of resistance. Now, in general, the stated or at least implied goal of a load test, static or otherwise, is to determine the geotechnical ultimate limit state, or failure load, if you will, of a deep foundation element. Although in some cases, and this is especially true when the deep foundation element is founded on or in bedrock, the goal is often more limited. That, for example, to verify that the deep foundation can adequately support some predetermined magnitude of externally applied load, such as twice to the design capacity. And the common term you often hear for this is, say, double design load. Right? I'm going to run a load test at double design load, which simply means twice the desired maximum geotechnical capacity. Now, the many issues that can affect the measured outcomes of a static load test I've discussed in numerous publications and presentations over the past 25 plus years. I've performed static load tests since, been involved in performing static load tests on deep foundation elements since the very first weeks of my professional career in 1972. So I've seen really how the practice and technology for performing static load tests has evolved over the last 5 decades. And I've talked about that many, many times in past publications and presentations. So I'm only going to present a summary here, and I'm going to focus on those issues that I think are most relevant to the theme of this Phase 1 presentation module, and that is improving the status quo as a necessary prelude and foundation for the Phase 2 module of changing the status quo. So I have a lot of comments about performing static load tests, and I'm just focusing on the ones that are most relevant to this presentation, which is things we need to do a lot better than we have been doing. Now, the issues I'm going to discuss fall into 2 broad categories. One are factual details, for which I think there's ample physical evidence to support the stated theses. Second, I'm going to present some professional opinion, but that opinion has fact-based arguments to support the stated theses. Factual details for both the basic non-instrumented static load test as well as the more advanced instrumented static load test are addressed first. before I give you my opinion about things. Now, both non-instrumented and instrumented static load tests require measuring axial force and displacement, both settlement as the result of loading and rebound as the result of unloading at the head of a deep foundation element. And this is done at intervals that are typically decided before the start of the test. Instrumented static load tests also require data acquisition at each load application interval for the various instruments that are either attached to or embedded within a deep foundation element shaft at various steps that generally range from near the head to near the toe of the deep foundation element. Now, although a wide variety of instrument types have been and are used for such tests, the most common that are used for instrumented static load tests measure axial force at a point, axial strain over some relatively short distance, axial displacement at a point, and this is typically done using telltale rods. And as a result, axial load, axial normal stress, and axial displacement can be determined at various depths within the deep foundation element shaft for different levels of externally applied axial load and displacement at the head of the deep foundation element. Now, because of the wide variety of instruments that have been and can be employed in instrumented static load tests, presentation, discussion of factual details about data acquisition and interpretation of these instruments are beyond the scope of this presentation. If you want a nice introduction to the subject, I suggest that you look at the latest copy of Fellinius' so-called Red Book that's available online. He talks quite a bit about instrumentation in static load tests, instrumented static load tests. Now, with respect to force measurements at the head of a deep foundation element, which is done whether the static load test is instrumented or not, it's long been documented that a calibrated electronic load cell is an absolute necessity for this purpose, regardless of the type of test being performed. And this is because the pressure readings of the hydraulic jack that is typically used to apply the force yield equivalent force values that are always incorrect on the unconservative and thus potentially unsafe side. What I mean is the inferred force values from jack pressure indicate that the deep foundation element is carrying more load than it really is. And this is true no matter how well calibrated the jack is beforehand. Now, with respect to vertical displacement measurements at the head of a deep foundation element, conventional measurements that are made using dial gauges resting on a reference beam and tension wires right against a scale and mirror always yield results that are too small in magnitude and thus overestimate the DFE ground interaction system stiffness, which is also unconservative and potentially unsafe. And this is because the supports of the dial gauge reference beam and the tension wire settle slightly as the deep foundation element is loaded, as the supports for the reference beam, etc., cannot realistically be placed far enough away from a deep foundation element and the load frame to avoid interference. Now, unlike with force measurements, the measurement error associated with traditional vertical displacement measurements in a static load test is not widely known, but I can attest to this firsthand as on multiple occasions in multiple environments. And by multiple environments, I talk about in terrestrial applications and shallow water marine applications for marine facilities. I've been involved in static load tests where special efforts were made at my request to also record vertical displacements using high precision optical survey that was referenced to a test-specific deep-seated benchmark, and this was typically done using what we call a Boros type anchor, and this benchmark was placed relatively far away from the deep foundation element being tested. So what I'm talking about here is I've had multiple opportunities to compare the results or the measurements from dial gauges and things like that to very high precision optical surveys that were referenced to a benchmark that there was great certainty was simply not moving, at least during the duration of that load test. I want to show you some qualitative outcomes of that I've observed and others have observed as well. And this is a conventional way we plot static load test result, the applied load force and the settlement here. And let's say this is what you typically measure. And as is common, you have some geotechnical quote-unquote failure line. And in the United States, this is typically the so-called Davison offset method. So from this, you would say this is the geotechnical ultimate limit state, the geotechnical failure load. This is what you think you have from this deep foundation element. Well, in reality, if you were basing these measured loads on jack pressure, they're typically going to be too high by about 20%. And using the conventional dial gauges and tension wire, the settlements you measure are going to be too small by about 10%. So the reality is that your actual load test curve looks something like this. And therefore, this is really the quote-unquote geotechnical failure load you have. All right? It's always going to be something less than what you think you have. And therefore, if you base your design on what you think you have, in reality, your safety margin is going to be less than what you think you have for that deep foundation element. So again, the mensuration errors in load tests are always incorrect on the unconservative and potentially unsafe side. Now, moving on to comments that involve my opinion, the overarching impression based on my over 50 years of firsthand experience with static load tests, and these are tests performed primarily in the New York City metropolitan area, is that there's been a steady decrease in overall technical quality, largely as a result of the commoditization that was discussed earlier in this presentation. Commoditization has produced what I call a race to the bottom mentality among all project stakeholders. And I have to blame project owners for some of this, in addition to design professionals and construction contractors. This race to the bottom has resulted in static load tests being viewed and treated nowadays as simply one of those necessary evils, if you will, of engineered construction as required by statutes such as building code, etc. It's right up there with taking concrete cylinders and performing compaction tests on compacted soil. So, unfortunately, I've seen static load tests being placed in the same league as performing compaction tests on saw fill or taking cylinders of fluid concrete at a job site. That is a menial, repetitive task to be performed by someone with the lowest acceptable level of training, skill, and requisite licensure or certification, and always at the least cost. Right? Commoditization has brought this obsession with doing things at the least cost. Now, this attitude towards static load tests typically results in having load tests performed by the lowest bidder for the service, which is often a local testing laboratory that does the minimum a code requires and allows, that is, relying solely on jack pressure. There are many codes that still allow nothing more than jack pressure measurements for load measurements. So this renders the measured results of static load tests worse than worthless, as they are potentially dangerous because they always provide an overly optimistic and thus potentially unsafe estimate of the load-bearing capacity and stiffness of a deep foundation element, and this is presented under a veneer of legal acceptability because the static load test has been certified by someone with a professional license. You'll always find somebody who's willing to put their professional engineering stamp and seal on a static load test. So this provides a false sense of security as to the veracity of the test outcomes. I said it before and I say it again because it's worth saying. Bad data are worse than no data at all. At least with no data, you know that you don't know the answer. But with bad data, you think you know the answer and you see somebody's PE stamp on something, so you think it's got to be correct. It's got to be the correct answer, but it's not. Now, an even more egregious, disingenuous practice that I've observed in recent years is when a deep foundation element fails a static load test because the desired minimum load settlement value is not reached. Again, this is typically the result of applying that Davison offset limit line to a load test curve. You don't get the results that you want to get. So what is often I've seen done, and I've seen this personally, not with projects that I have been directly involved in, but I'm talking about projects where I have been given data by others to allowed to use legally for research purposes. So I've had a chance to review load tests performed by others. So I have personally seen this happen. And what's often done is people game the system, as I call it, and they simply rerun the static load test the next day or a couple days later. And codes are typically silent on whether or not this is acceptable. Codes say run a static load test, but it doesn't say, gee, you can't run more than one test on a given deep foundation element. So they rerun the test a day or two later, and they present the results as being an independent test. And in every case that I've seen where this was done, the deep foundation element magically passed the retest. Now, here's an example, and I've whited out the names and stuff for confidentiality. This is an actual report submitted to a project owner by a licensed professional engineer. All right. So this is the actual test curve. I didn't redraw it. I've simply blanked out the information that indicated when and where this was done. All right, so you see here settlement curve first attempt, which failed as it turned out. Settlement curve second attempt, which you see a noticeably stiffer response, and magically it now passed the desired test. And by the way, note that this is that bad practice of using tons as a force unit. All right, so 100 tons is really 200 kips. So there's the first attempt. There's the second attempt that passed. Now, in reality, such a retest is not an independent test, but simply a continuation, an unload-reload loop, if you will, of the original test, in which in the retest, the deep foundation ground system on the second attempt has been stiffened by the original failed test. So this is what you see, but this is what you really got. What you really got is the first attempt, loaded, unloaded, and then you start what amounts to a reload loop and a second unload loop. So this second test is not an independent test. It's just a piggyback on the results of the first test. And because you have loaded the system initially, you've pre-stressed it, if you will, pre-strained it. So it's no surprise that it is stiffer on the second attempt. And this is due to the hysteretic nonlinear behavior of soil and soil systems. As I noted earlier in this presentation, my opinion about the generally poor quality of many static load tests that are performed these days renders the results from such tests more fool's gold than gold. But my opinion is not unique and is shared by others. I don't want you to think that this is just John Horvath's view of the world. I think this quote by Felinius, it's from his chapter in his so-called Red Book, current edition of his Red Book, chapter 8, where he talks about the analysis of results from static load test. Nothing is so bad, however, that it cannot be made worse. And I think that sums things up when it comes to the current way that a lot of static load tests are performed. Now, the root cause of many of these criticisms about static load tests is the fact that for many years now, the global state of practice for dividing the geotechnical ultimate limit state, or so-called failure load, in a static load test is some arbitrary settlement magnitude at the head of the deep foundation element. As I noted earlier in this presentation, there's an abundance of methods that have been proposed for this purpose, and they tend to produce a large range of results for a given application. All right, this is the slide I showed you earlier, and you can see the range of over 200% of forecasts for a single static load test curve. This is just different opinions as to what constitutes the quote-unquote failure load. And here you see the common Davison offset method that's used in the United States and the 10% settlement criterion that's very popular in Western Europe. Now, with particular reference to the Davison offset method that has long been preferred metric in U.S. practice for defining the geotechnical ultimate limit state or failure load in a static load test, if you read the relevant literature, you know that this method was never intended for use with static load tests. The so-called Davison offset method was proposed relatively early in the technical evolution of the one-dimensional wave equation to analyze driven piles by the late Professor Tom Davison of the University of Illinois at Urbana-Champaign. And Professor Davison was an early fan and devotee of the wave equation to the point where he eschewed other analytical methodologies. He was, all in on the use of the wave equation for forecasting the geotechnical resistance of driven piles. So it kind of makes the use of Davison's methodology with static load tests all the more ironic, because Davison was not a fan of static load tests, and he developed this method for not static load tests, but for wave equation analyses. Again, I'm not the only one who's said this. There are any number of papers where that people have written over the years that basically says the Davison offset method was never meant to be used with static load tests. Why do we continue to do that anyway? An additional complication is the fact that failure to correct a load settlement plot of static load test results for residual loads can lead to misleading interpretation of these results. When any of the settlement-based failure criterion are used, and again, I showed you a slide to illustrate this earlier in the presentation. All right, this is the slide I showed you, that unless you correct for residual loads, the application of the offset limit, meaning Davison's method here, you see typical static load test is measured. You forecast a much greater quote-unquote failure load for that deep foundation element than exists in actuality. So you put all these results together, as well as other issues, I draw the following conclusions with respect to static load tests. I feel that defining the geotechnical ultimate limit state, whatever you want to call it, ultimate capacity, failure load, whatever, using some arbitrary settlement-based criteria lacks theoretical logic and basis, and I think really should just be abandoned. Yes, it's easy to use, but it's just because something is easy to use is not justification for using it if it gives you poor outcomes, inconsistent outcomes. In fact, any settlement-based criterion is inherently susceptible to further uncertainty and error due to the presence of residual loads from installation. The only logical and theoretically defensible alternative is to perform a static load test to relatively large magnitude of settlement, and here I'm talking about several inches or tens of millimeters, so that the effects of residual loads are overcome and the measured load approaches the true value of the geotechnical ultimate limit state. Note, however, that even at relatively large settlements, a deep foundation element may not exhibit a plunging failure, but may continue to show a relatively small increase in resistance with increasing settlement. And that's just part of the game. All right, I've showed you this previously. if you run a test out to a large enough settlement, you're going to overcome the results of residual loads. And even if the test is run incorrectly, it will tend to coalesce around the true ultimate geotechnical ultimate resistance. But notice that this is continuing to increase at a slight rate. So you're still not guaranteed to have a singular geotechnical failure load for that deep foundation element. Load application should always be monotonic in equal increments. Again, this is not just me talking. Fellinius says the same thing. That are held for the same duration and absolutely no unload-reload cycles. I certainly started out in this profession where people thought that they were getting some useful information from unload-reload cycles, but in reality, unload-reload cycles just complicate the test results, and they don't provide you with the information you think you're getting. So unload-reload cycles are essentially worthless for the intended purpose of defining the geotechnical ultimate limit state, and only distort and corrupt the overall measured results. So we need to do away with unload-reload cycles during static load tests. In no case should a repeat or do-over of a load test of a deep foundation element ever be allowed. The rationale and justification performing non-instrumented static load tests is also highly questionable, as even if performed correctly, such tests provide very limited usable results for the time and cost incurred in performing them. As we all know, static load tests are very expensive. That's one of the reasons why they tend to give them to the low bidder these days. It's very expensive anyway. So for the rather significant expense you're going through, you get very little usable information from a non-instrumented static load test. So you can make an argument that only instrumented static load tests should ever be performed, as they provide much more useful information in the form of site-specific parameters related to the depth-wise variation of axial resistance, and it justifies the incremental cost involved in performing such tests. And again, that's not just me, in my opinion. This is shared by others. I'll let you read this quote from Fellinius's Red Book. Well, I think enough said about static load tests. I think you get the point here. Let's now move on to talking about dynamic measurement. Axial resistance verification of deep foundation elements during the deep foundation installation process can be traced back to the mid-19th century. For the better part of a century that followed, the analytical methods that were developed were all based on a methodology that assumed the deep foundation element, which are of course all preformed piles during that time frame, was a rigid object during the installation process, which was impact driving only during that time frame. The first analytical methods to be developed beginning circa 1850 were all based on the so-called work equation. The work equation equated the geotechnical ultimate limit state of a driven pile with the theoretical magnitude of work in the form of pile driving energy put into the final hammer blow as reflected in the final pile set, that is, magnitude of penetration of a pile. All right, very simple concept. You put a certain amount of work into getting a pile in the ground, that pile now owes you back something in the form of geotechnical resistance. Algebraic equations for use in routine practice that derive from the work equation include the Sanders formula, Merriman formula, and the Trautwein formula. Now, as the 19th century progressed, research and development attention shifted to using the theoretical equation for the impact of two rigid bodies. This is an algebraically complex equation in its complete form that contains numerous parameters such as coefficient of restitution, and various researchers over the years made different simplifying assumptions with respect to these parameters. And this explains why, although there is only one equation, eventually there was a proliferation of different algebraic equations. And in Chellis's 1961 edition of his book on pile foundations, he identified 22 different equations, and there are even more now. And these all evolved from the same basic equation. In the US, at least, the most famous of these algebraic equations that came out of the impact of two rigid bodies is the Wellington formula, that is more commonly known by its alternative name, the engineering news formula. And the link of these two names is the fact that Andrew Mellon Wellington was a civil engineer. He was specialized in railway engineering, and at the time he was editor and part owner of the engineering news, so that's why the Wellington formula wound up being called the engineering news formula. By the way, in a lot of books and publications, you will see this incorrectly called the engineering news record formula. That's incorrect. At the time this formula came out, there was a publication called the engineering news. There was a separate publication called the engineering record. Now, as time went on, these two publications merged and they became engineering news record, now known as ENR, but it is just the engineering news formula. By the early 20th century, it was beginning to be recognized that these so-called dynamic formulas that were based on the assumption of a rigid driven pile really left a lot to be desired, for the very simple reason that in a given application, the different formulas tended to yield unacceptably wide range of calculated results. Again, there's something like 24 different formulas. So you apply those formulas to a given pile and you will see a surprisingly large range of results. In addition, during the same early 20th century time frame, it was found in both in the United Kingdom and the United States that cracking was observed in precast Portland cement concrete piles. And at the time, Portland cement concrete as an engineering material and reinforced concrete was an emerging technology that people were investigating. So you want to note that these early precast concrete piles were steel reinforced but not pre-stressed. The dynamic formulas in use at the time provided neither an explanation nor insight as to why if a pile behaved as a rigid body when it is impacted during driving, it would exhibit tensile cracks. You think about it. This is really a rigid body and you impact it, which implies you put a compressive force in that pile. Why would it exhibit tensile cracking? It didn't make sense. It was inconsistent with those dynamic formulas. Now, the breakthrough in understanding the true mechanics involved in impact driving of piles occurred in the United Kingdom and is attributed to David Victor Isaacs. And in 1931, he published a paper that identified that driven piles are not rigid. They behave elastically during the driving process. And he proposed modeling the elastic behavior using the equation of one-dimensional wave transmission. Now, there was a lot of follow-on research to Isaac's work, and it was extended. And it was also performed in the UK by William Henry Glanville and his colleague. Now, given the unambiguous historical record of how the one-dimensional wave equation came to be used to physically and mathematically model pile driving, I have always thought it was kind of curious as to why, when you look at the published English language literature, the literature tends to give sole credit for the development of the wave equation to pile driving to E.A.L. Smith. And Smith was a mechanical engineer, not a civil engineer, by education and profession. And people tend to cite his 1960 ASC paper as being the seminal landmark resource on the subject of the one-dimensional wave equation applied to driven piling. Well, in reality, Smith had actually presented his work on the one-dimensional wave equation to driven piles as early as 1954. But since he was a mechanical engineer by education and profession, he did this at a ASME annual meeting, Society of Mechanical Engineers annual meeting, although this fact is generally neither mentioned nor referenced in the civil engineering literature. I don't mean to beat this to death, but I think credit is deserved where credit is due. And I think the reason this credit has been given to Smith is simply he had the fortune to be in the right place at the right time. All right, he was working for the Raymond Concrete Pile Company, which was later known as Raymond International, and Raymond had international recognition and reach in the 1950s. I know when I started out in the profession in the early 1970s, Raymond was probably on the downside of their corporate evolution in terms of driven piles, but they were still a big name. But certainly in the immediate post-World War II years, 1950s, 1960s, Raymond had an international reputation, and they were doing major projects throughout the world, not just in the United States where they were based. So again, Smith was simply in the right place at the right time. The right time being that after World War II was the development of hardware for digital computers was progressing rapidly, and Raymond was a large enough corporation that it had access to digital computers, even at a time when they were largely just mainframe computers used for research applications. And there's also money to be made because pile driving was a big thing for offshore oil exploration and extraction after World War II. Unfortunately, when Isaacs and Glanville and others did their work in the UK in the 1930s, they were constrained by the computational era, tools of the era, slide rule, pencil, and paper. And then you had the outbreak of war in Europe in 1939. So Isaacs and Glanville and others who really invented the wave equation for driven piles really were in the wrong place at the wrong time, unfortunately. Well, in any event, it's unambiguous that after 60 plus years of increasing use of the one-dimensional wave equation, it's become an indispensable tool for all deep foundations, not just driven piles. This is because there are now several tools for investigating deep foundation elements of all types that have been developed that make use of one-dimensional wave mechanics. I have two broad criticisms of the one-dimensional wave model. One is that the model does not properly account for deep foundation elements with a depth-wise variable perimeter such as driven piles. This is because the simplistic spring and a dashpot soil model that is used to model soil resistance both along the shaft and at the toe only accounts for shaft resistance due to sliding friction and toe resistance due to end bearing. So it does not properly account for shaft resistance due to wedging and the increase in radial resistance that results from the expanding cylindrical cavity of the taper section of a deep foundation element as it is driven into the ground. So the one-dimensional wave model, I know there's approximate ways of dealing with tapered piles. You step the diameter, but that still does not capture what is going on. All right, you simply are not capturing the wedging effect. The second criticism is that I showed you earlier in this presentation, the one-dimensional wave model as implemented in software such as CapWAP that does not always properly account for residual loads from installation. And you recall that I showed you this slide earlier where there was a difference between the true resistance and the CapWAP inferred resistance because of the inability of CapWAP to properly include residual loads. Well, I now want to move on to the final topic in this segment, and that is discussion of static analysis. Now, although routine practice in recent decades has continued to rely more and more on deep foundation element resistance verification using field testing methods that are based on one-dimensional wave mechanics, Deep foundation resistance forecasting prior to deep foundation installation that is based on static analysis calculations still remains an essential tool for this purpose. As you know, there are two distinct categories or types of static analysis methodologies that are used for geotechnical axial resistance determination. And they differ in how they use the raw data, which is primarily nowadays from in situ field tests, but sometimes from lab testing, to produce a calculated outcome of geotechnical axial resistance. Now, in the so-called indirect methodology, it's also referred to in the literature as the rational methodology. You take the raw data, you first generate material properties from site characterization, and then you put them into some analytical methodology, which very often is generic, meaning it could be used for any type of deep foundation element, and you get a calculated outcome. With the direct methodology, you take the same raw data, but now you plug it into an application-specific analytical methodology, and you get the calculated outcome directly. And for obvious reasons, this is very popular. You don't have to go through any intermediate calculations. And, you know, there are all sorts of empirical equations for these direct methodology methods that's easy to solve with spreadsheet or proprietary software. Now, there are numerous specific methods for each of these two methodologies, and there's also hybrid methods that contain elements of both methodologies. Now, in view of the current state of knowledge concerning deep foundation elements, as discussed throughout this presentation up to this point, there are some broad critical observations that can be made about static analysis methods in general. First of all, methods are based on soil properties that exist in the ground prior to deep foundation installation, and the effects of installation are either ignored or in some way empirically incorporated into a specific method. There are soil properties such as the pre-installation value of the coefficient of lateral earth pressure at rest, KO, that are now recognized as being important parameters that unfortunately are not explicitly considered in most analytical methods. At the present time, deep foundation elements with a depth-wise variable perimeter, such as tapered piles, are at best modeled approximately, and this is typically by empirically modifying the resistance mode of shaft friction due to sliding friction, and the different models for doing this tend to produce widely varying results. The static load test data used to calibrate some indirect methods, and more importantly, used to develop the empirical correlations necessary for direct methods, have generally ignored residual loads. And this is a real big issue, because as a result of this, the vast majority of resisting forecasting methods that are out there nowadays, and have always been out there, tend to overestimate shaft resistance and underestimate toe resistance for the simple reason that they use the so-called false resistances for shaft and toe, as I illustrated to you earlier in this presentation. If you don't correct for residual loads, you're always going to tend to think you got more shaft resistance than you really have, and you're going to have less toe resistance than you really have. Well, given the sheer number of different indirect and direct methods for resistance forecasting that have been proposed since research and development of static analysis methods started in earnest in the 1950s, it's certainly well beyond the scope of this presentation to offer a comparative assessment of all these countless different methods. I don't even know how many different methods are out there. I never tried to sit down and count how many. So what I'm going to do, I'm going to look at a limited number of methods were chosen for discussion, and then based on several criteria that I came up with. First of all, I wanted to use methods that I felt were representative of indirect, direct, and hybrid indirect direct methods. I wanted to use methods that already are and have been used for some time in practice, at least in some form. And I want to use methods that, based on my over 25 years of research, are practical to use in routine practice. I wanted to use methods that are amenable to modification and include some of the issues I listed and discussed in the preceding slide with respect to KO and tapered piles, things like that. All right, so they wanted them to be amenable to extension to include tapered deep foundation elements, especially. Now, with respect to tapered deep foundation elements, it's important to reiterate an important point I made earlier in this presentation more than once, that the so-called taper benefit that is the result of the greatly enhanced increase in the KH value acting along the deep foundation element shaft compared to deep foundation elements with a depth-wise constant perimeter. And again, this is reflected in the KH-KO ratio. This so-called taper benefit derives from two distinct components or stages that are complementary and cumulative as they occur in different stages of installation and loading. So again, I want to emphasize that so-called taper benefit occurs and accrues in two stages. Stage one is during the installation of the deep foundation element, which means that the type of deep foundation element and its method of installation are the primary variables. All the available information I've ever seen suggests that stage one is the much more significant contributing factor to taper benefit, all right, because you create a cavity at the toe of a tapered driven pile, and then you continue to expand that cavity as the tapered pile is driven further into the ground. So a taper-driven pile would be expected to exhibit considerably more taper benefit, a larger KH-KO ratio, than a tapered board pile or drilled shaft. The stage two of taper benefit reflects the axial loading of a deep foundation element after installation, which means that both the direction of loading, compression versus tension or uplift, as well as the taper angle and the magnitude of axial displacement are primary variables. Now, in general, resistance forecasting methods don't differentiate between these two stages of taper benefit. More times than not, they simply lump them together. So a thorough understanding of the theoretical basis of a given analytical method is always essential. As I said, most methods that are out there lump the effects of the two stages of taper benefit together. Understandably, they're very difficult to separate, with the implied assumption that post-installation loading is axial compressive to the geotechnical ultimate limit state. But as I pointed out to you earlier, there are methods that only consider the taper benefit of post-installation axial compressive loading. That's the work of Kodakara and Moore. So first I want to consider in detail an exemplar method of indirect methodology that is based on fundamental geomechanics principles. And I've always been I will admit, I am very partial to indirect methodologies. The attraction of them and the inherent benefit is that they are transparent as to how input data are used to provide a calculated outcome. So you see what's going on at every step of the process. All right, you see how the raw data are converted into fundamental soil parameters and properties, and you see how those fundamental soil properties and parameters are plugged into some equation to give you a final result. You can see how sensitive the final result is to variations in any of the soil properties. So again, I will admit I have always been biased and very preferred indirect methodologies. So as I said, it's because all stages of the analysis are transparent. Now, in my experience and opinion, understanding the sensitivity of a calculated result to changes in the value of an input parameter is really a key intellectual tool when performing geotechnical and geostructural analyses. I go back to my days of academia, especially undergraduate education. And one of the hardest things to tell students was, I think to be a good civil engineer, you need to, whatever your specialization is, you need to develop a feel for how sensitive some calculated result is to a change in a material property. That's a very important tool. Students always, they do what they used to call plug and chug, right? Just give me some numbers, plug it in an equation, bang it in my calculator, I give you an answer. A classical example of what I'm talking about is shallow foundation bearing capacity using the traditional three-term solution. I've done a couple of white papers on this subject that you can find if you're interested in it. And what I'm talking about is one could debate forevermore whose solution is the quote-unquote best. Right? I've seen all sorts of debates. So Hansen versus Meyerhoff versus Terzaghi versus Vesage versus so-and-so. There are many different solutions for the traditional three-term shallow foundation bearing capacity equation. And they differ in the geometry of the failure surface that some researcher assumed. All right, so this person assumed it went this way, this person assumed it went that way. So you're going to get a little bit different values of the end parameters. But at the end of the day, the fact is that the single most important factor influencing the calculated result of the gross ultimate bearing capacity, Q ultimate, is not whose solution you use, but the assumed value of the angle of internal friction, phi. And this is because of the logarithmic mathematical relationship between phi and the dimensionless end values of each of these solutions. So although the end values for each solution are a little bit different, if you use phi of 30 degrees versus 35 degrees or 40 degrees, I don't care whose solution you're going to use, you're going to get a tremendously different answer. So the point is that when you're doing a shallow foundation bearing capacity solution calculation, I could care less whose solution you want to use. I mean, I have my personal preferences of what I think is best, but where you should put your effort, what I'm getting at is where you should put your effort is to determining an accurate value of phi for that particular calculation. So the method that I chose to illustrate here is the so-called Nordland method. I think is a fine example of an indirect methodology for several reasons. It's one of the earliest methods. It was first proposed in 1963, revised extensively in 1979. I would say a lot of people know about Nordland's original work. Very few people know about his later work. In fact, I will admit I did not know about his later work until later years. And Nordland was the first method to explicitly consider driven tapered piles in a rational manner. No surprising, given that he worked for Raymond Concrete Pile Company, and their stock and trade was driven tapered piles. The so-called Nordland method has stood the test of time well. The New York State Department of Transportation still uses the method for all types of driven piles. It's relatively unique among resistance forecasting methods in that one of its parameters reflects an estimate of how the phi angle of the soil increases due to the densification that is assumed to accompany pile installation by impact driving, which makes both pile type and the embedded pile volume problem variables. There are some significant caveats and drawbacks to note about the Nordland method I don't think a lot of people are aware of, and this is based on my use of the Nordland method in research for almost 30 years and in practice for longer than that. First of all, it's limited to driven piles and predominantly coarse-grained soil. You can accommodate fine-grained strata, but only in an approximate manner. It's applicable to compressive loading only, as it lumps the two stages of installation and post-installation compressive loading taper benefit together. it requires the use of field end values. And this is a point a lot of people don't appreciate. And not just any field end values, but by implication, the field end values as would have existed circa 1960 when Nordland finalized his method. So whenever I use the Nordland method, I use what we now call N45 because I think that best reflects the field end values circa 1960. Typically in the United States at least obtained with a cat head and rope type of drive system. Unfortunately, the Nordland method requires use of several hand-drawn charts, so it makes it cumbersome and time-consuming to use. Although I've seen some proprietary software, such as the Federal Highway Administration's Driven program, where people have apparently digitized Nordland's charts. I'm not aware how exactly they did that, but obviously to put those hand-drawn charts into a computer program, you had to digitize them in some manner. Several method parameters are empirical, and Nordland in his paper never really explains where they came from, and I think they reflect his professional opinion based on his many years of experience working for Raymond, and they were likely based in whole or in part on static load test results that were uncorrected for residual loads. Now, Nordland in his papers, he kind of implies that he suspected that something like residual loads existed, but he really didn't know how to deal with them, so he didn't correct for them in any way. As a result, what I call the original Nordland method of 1963 and the revised Nordland method of 1979 are capable, if properly applied, and this is especially true with respect to using the appropriate field end values, are capable of accurately forecasting the total geotechnical ultimate limit state, although both versions over-predict shaft resistance and under-predict toe resistance, which is no surprise. This is typical of most static analysis methods, whether indirect, direct, or a hybrid, that were calibrated or based on uncorrected static load tests. Now, beginning in the late 1990s and continuing to the present, I developed and subsequently refined what I call the modified or Nordland or Horvath method to eliminate several method components as originally defined by Nordland that I think really hampered its use, in, especially with computer solution, as well as to take advantage of the many advances in geotechnology in general and site characterization in particular in the over 60 years since Nordland first published his method. Specifically, what is arguably the most original and key element to the original and revised Nordland methods for calculating shaft resistance, that is the relationship between the earth pressure coefficient KH and pile taper angle, that Nordland portrayed using hand-drawn curves on a chart. I replaced these with a simplified bilinear algebraic expression that's amenable to computer solution. I then replaced KH with the product of the KH-KO ratio, which again reflects the effects of installation and subsequent applied loading and compression, and KO that reflects the pre-installation starting point. The unsubstantiated and unverifiable empirical shaft resistance components in both versions of the Nordland method, and especially the effect of the embedded pile volume on the phi angle, I discarded those and I replaced them with soil properties developed from site characterization based on piezocone and seismic piezocone soundings. The toe resistant method used by Nordland, which was the classical solution published by Berezantsev et al. In 1961, I discarded that and I replaced it with several different methods that use stated knowledge site characterization outcomes. And that would be the, I talked about these earlier, this would be the Vesage spherical cavity expansion model, as well as Cole-Howey's compressibility factors for use with traditional bearing capacity solutions. In my experience, they've given much better correlation with actual toe resistance. So the research has shown that this modified Nordland or Horvath method produces reasonable qualitative and quantitative results that do a pretty good job of matching the true shaft and toe resistances, assuming they've been corrected for residual loads. And I've illustrated this in several publications over the last 25 plus years that I noted earlier in this presentation. So there are several research reports, academic research reports, and later white papers that are out there where I go through this so-called modified Nordland or Horvath method in detail. So I'm not going to go through it here. You can access these documents at no cost on my ResearchGate website. I want to move on and next consider an example of hybrid indirect direct methodology. Hybrid methods offer some of the analytical transparency of indirect methods, but with one or more empirical, what I call black box components. So you need to use them perhaps with some greater care. So an essential first step before using any hybrid method is to fully understand how the empirical components are determined and quantified for use. The hybrid method I've chosen for presentation and discussion here is one of the oldest static analysis methods in use. First appeared in the published literature back in the late 1960s. This is the so-called beta method that, depending on the publication, has variously been attributed to the late Lawrence Barham, Professor John Berland, or Professor Bengt Felinius, either alone or in some combination. For reasons that will become clear subsequently, I'm going to call this original Barham, Berland, Felinius version of the beta method simply as the original beta method. The hybrid nature of the original beta method derives from the fact that it has both a theoretical indirect method component and an empirical direct method component. The indirect method component is that it relates the unit shaft resistance, R sub S, to the vertical effect of overburden stress along a deep foundation element shaft. And of course, you have to calculate this overburden stress in an application. The direct method component is that it does so by an empirical dimensionless parameter beta that is defined as follow. So it says the unit shaft resistance, which is a stress, is equal to beta, which is a dimensionless parameter, times the vertical effect of overburden stress, which is, of course, a stress. Now, beta lumps together the soil type, the pre-installation lateral earth pressure coefficient KO, the type of deep foundation element and installation methodology as reflected in the KH-KO ratio, the soil deep foundation interface friction angle delta. All of these are lumped into one parameter that is based on back calculation using values that are measured in instrumented static load tests. So the way that beta values have been determined is people run instrumented static load tests. They measure the shaft resistance due to sliding friction, R sub S, presumably at geotechnical failure. They calculate the overburden stress, and then from this they get the beta value. Okay, so beta is equal to the measured in instrumented static load test shear resistance along a pile shaft, the calculated overburden stress at the depth at which the shear resistance was measured. And I've expanded that here just to show you how we can break down exactly what goes into the beta value. So as I said, it reflects, if you go through this, you see it reflects the KH-KO ratio, the K sub O prior to installation, and tan delta, where delta is the friction angle between the soil and deep foundation element shaft. Now, similarly, the unit tow resistance, R sub T, at the geotechnical ultimate limit state is related to the vertical effective overburden stress at the toe of a deep foundation element using an empirical dimensionless parameter capital N sub T that lumps together all three components, NC and Q and gamma, of a traditional bearing capacity solution, as well as the various shape and embedment factors that go along with a traditional bearing capacity equation to calculate the gross ultimate bearing capacity. So again, N sub T is determined by measuring the gross ultimate bearing capacity at the toe of a deep foundation element and dividing it by the vertical effective overburden stress at the toe. Now, the original beta method has proven to be wildly popular in practice and very enduring, not only in practice, research as well, because it's relatively simple to use, yet employs empirical parameters that are rooted in actual load test data. So although there is an empiricism, it's pretty clear where they came from, and anyone can run an instrumented static load test and determine their own beta values. So this gives the method an aura of theoretical rigor and applied legitimacy and accuracy. However, in my opinion, the original beta method suffers from three significant technical flaws, as one significant omission. Although none of these is fatal, each of these can be overcome in a rational, straightforward manner. And I would like to illustrate that because I think the beta method is a useful method to use. So because the basic beta concept is sound, despite these flaws and omissions, improved versions of the original beta method can readily be developed, and I'm going to illustrate that to you at least qualitatively. The first technical flaw, in my opinion, is the fact that the vast majority of instrumented static load tests that have been used over the past 50 plus years to populate the beta and N sub T databases were likely performed on driven piles. And as I've discussed now throughout this presentation, driven piles are a type of deep foundation element that tends to exhibit significant residual loads from installation. And it's highly unlikely that the load test data used to populate the existing beta and N sub T databases were corrected for residual loads due to installation. So the existing databases for beta and sub T are based on load test data that have not been interpreted properly. As a result, the original beta method suffers from the same flaw of most, if not all, resistance forecasting methods that rely on uncorrected static load tests, in that the shaft resistance is overestimated and toe resistance is underestimated. But again, this is not a fatal shortcoming in the underlying beta concept, but a deficiency in the databases that have been used to date to quantify beta and N sub T parameters. So we can readily address this flaw going forward by correcting data from instrumented static load tests for residual loads and creating new databases of the beta and N sub T parameters based on these corrected data. The second technical flaw I want to address is that the beta values are generally assumed to be only a function of soil type, whereas I think they should logically be a function of the type of deep foundation element as well as installation methodology. The rationale and resolution of this second flaw is actually linked to the third technical flaw, which is that even if the data from instrumented static load tests are corrected for residual loads, experience indicates that the calculated beta values for the same type of soil, same type of deep foundation element, same method of deep foundation element installation often exhibit relatively significant variation or scatter within depths that are relatively close to the ground. And This is a very typical result. This happens to be from the 2024 edition of Fellinius's Red Book. And what we're looking at here is the beta coefficient or parameter as a function of depth in meters. And these citations are from various publications. And you can see a very definite trend line. At shallow depths, very high values of beta, a lot of scatter in those high values, and that scatter tends to decrease and coalesce to smaller values of beta with depth. In my opinion, I think what this means is that beta values need to be a function of the pre-installation stress state in the ground as well, a point that I noted previously, and I will illustrate that in a bit. So both the second and third technical flaws, as well as the ways to overcome these flaws, can readily be understood by expanding on the theoretical relationship of beta that I showed you earlier. So this is the fundamental definition of beta. It's equal to the K sub h times tan delta. If we expand on K sub h, that's equal to the KH-KO ratio times KO. And if we expand on tan delta, it's the tangent of the delta over phi ratio times phi angle. And this simply reflects that the frictional resistance between soil and some structural material tends not to be a fixed value, but a fixed ratio, depending on the original. Out of many years of habit, I still call this phi angle. I realize the correct pronunciation is phi. So if we note that the KH-KO ratio reflects the type of deep foundation element and its method of installation, and KO values prior to deep foundation installation often exhibit significant depth-wise variation, with larger values in the near surface, where the yield stress ratio, what we used to call the over-consolidation ratio, tends to be greater in magnitude for any number of natural and anthropogenic reasons. And let me show you what I'm talking about. This is the curve that I showed you previously. We see in the near surface environment, we've got a fair amount of scatter as well as high values. Let's look at a typical profile of K sub O at Kennedy Airport. All right, this is based on my assessment of piezo cone, the size of a piezo cone readings. This is a very typical profile from Kennedy Airport of the KO values. Now, if we rotate this 90 degrees, we see that the trend line looks very much like the trend line of KO in this coarse-grained soil deposit. In fact, if I now take the KO plot and I superimpose on it Fellinius's plot and his trend line at the same scale. All right, so I've changed the vertical scale so both of them have the same vertical scale. You could see that the trend line from Fellinius's plot very nicely follows the general trend in KO that we observe at Kennedy Airport. And this trend of KO at Kennedy Airport has been found at many other sites by many other researchers. Also want to point out that delta over phi also reflects the type of deep foundation element. That is it made out of steel or wood or Portland cement concrete? And of course, the phi angle reflects the soil type. So we put all these thoughts together and come up with an expanded definition of beta, what I call the modified beta method. First and foremost, this modified method needs to be based on new databases that were created from instrumented static load tests that are corrected for residual loads and are performed at sites for which a state of knowledge site characterization is performed in order to define a site-specific depth-wise profile of KO. These new databases should tabulate values of not beta, but beta over KO in order to remove the effects of soil stress history. Furthermore, these tabulated values of beta over KO should be subdivided based on soil type and deep foundation element material types as opposed to soil type alone, so that the unit shaft resistance in the modified beta method can be calculated for a specific site as follows. Right? It's equal to beta over KO times the vertical effect of overburden stress. And again, this beta over KO ratio is going to be for specific types of deep foundation elements. So the beta over KO ratios come from a database based on soil and deep foundation element types. K sub O is defined on a site-specific basis from site characterization. Well, I took these one step further and created the extended beta method, where beta parameter is a function of the deep foundation element taper angle as well. So note in this case, the tabulated beta over KO values include both stages of taper benefit from installation as well as from post-installation axial loading to the geotechnical ultimate limit state. So in concept, you should have separate beta over KO values for deep foundations loaded in compression versus tension or uplift. So in summary, the state of knowledge indicates that while the basic beta concept remains valid, it is essential that going forward in time, new databases for both shaft and toe resistances need to be created using data from instrument and static load tests that have been corrected for residual loads from installation. In addition, the arithmetic definition of beta needs to be extended so that it is a function of the KH-KO ratio, KO, the delta over phi ratio, and phi. And clearly this indicates that the beta parameter is not just a simple function of soil type, as has been assumed for the past 50 plus years, but it's actually a very complex function of soil type, the stress state in the ground prior to deep foundation installation is reflected in the KO value, and I think this takes away a lot of the scatter that we do observe in practice. The type of deep foundation element, the material it's made out of, and its geometry, the method of installation or construction, the direction of post-installation externally applied axial loading, especially for taper deep foundations. So all of these factors need to be incorporated into any updated and improved version of the beta method. Next considered is an exemplar method from the direct methodology category. All methods in this category are by definition purely black box in nature, meaning that data are input and a result comes out, but the exact process of the analytical engine, if you will, that gives you the calculated results is typically opaque and known only to whomever developed the method. The method I've chosen for presentation here is one that's relatively modern origin, and it's based on the piezocone and seismic piezocone data. It was developed in the 1990s as an outcome of the doctoral research of Dr. Abulfazi Islami, and this was conducted at University of Ottawa in Canada under the direction of Professor Felinius when he was still on the faculty there. Well, consequently, it was originally referred to in the literature as the Islami-Felinius method, but I've noticed that over the years the name has changed and morphed to now it's called the Unicone method. So these are the same method. You just see different names, and the older literature uses this name, the newer literature uses this name. For reasons that become clear, I refer to this as the original Unicone method. This original Unicone method is a classic example of a direct methodology, as both the shaft resistance and unit toe resistance are each linearly related to an empirical parameter that is quantified using post-process QCFS-U2 data from a pisocone or seismic pisocone sounding. The empirical parameters for shaft and toe resistance were calibrated using a database of measured results from instrument and static load tests. A drawback of the original Unicone method is that it relies on printed charts and tables that, again, like with the Nordland method, don't lend themselves to digitization, so it's not easily solved using a spreadsheet or other generic software. Earlier in the century, Professor Fawad Niazi developed, as part of his doctoral research at Georgia Tech under the direction of Professor Paul Main, what Niazi has variously referred to in his publications as an enhanced or modified version of the original Unicone method. And this enhanced or modified version was based entirely on a new database of static load test results and included entirely new empirical correlations for the unit shaft resistance that varied with deep foundation element type, driven, jacked, and drilled, as well as unit toe resistance. And these were all defined using arithmetic equations, so they are easy to program to a spreadsheet or other generic software. However, what I call the Niazi Unicone method suffers from the same flaw as the original Unicone method, in that the static load tests used for the databases on which both versions of the Unicone method are based were not corrected for residual loads. As a result, both the original and Niazi versions of the original Unicone method tend to overestimate shaft resistance and underestimate toe resistance. And again, this is a common theme we have seen with the so-called static resistance calculation methodologies. As with the original beta methods, it's obvious that either version of the Unicone method would benefit from being recalibrated using a database of static load test data that are corrected for residual loads. Also, as with the original beta method, either version of the Unicone method can be extended for use with taper deep foundation elements, either by developing new empirical coefficients for shaft resistance that includes taper angle as a variable, or by applying a taper correction factor to the empirical coefficients for shaft resistance that were developed for deep foundation elements with a constant perimeter. And this is actually this latter alternative of developing a taper correction factor is something that I've looked into in recent years. This discussion of static analysis methods concludes with a discussion of miscellaneous topics that are all related to the fact that historically the two stages of deep foundation installation, what I call stage 1, and post-installation externally applied axial loading, which I call stage 2, have with few exceptions been lumped together for the purposes of developing static analysis methods for forecasting the geotechnical ultimate limit state and axial loading. This merging of the two stages has proven to be adequate when deep foundation elements with a depth-wise constant perimeter are used, as all the changes in the stress state around the deep foundation element shaft that contribute to shaft resistance, and again this is reflected in the KH-KO ratio, can reasonably be assumed to take place during the cylindrical cavity creation that takes place during the stage 1 installation. However, deep foundation elements with depth-wise variable perimeters, such as taper piles, are much more complex to deal with. To begin with, if they are installed by driving or jacking, they will have a much larger KH-KO ratio than a constant perimeter deep foundation element at the end of stage 1 installation, due to the wedging effects of continuous cylindrical cavity expansion that follows the initial cylindrical cavity creation at the deep foundation element toe. Tapered piles and other tapered deep foundation elements will have additional changes in the KH-KO ratio during stage 2, which is the post-installation applied loading, as the result of either further cavity expansion under axial compressive loading or cylindrical cavity contraction under axial tensile or uplift loading. To date, there has been no comprehensive theoretical development that integrates the different modes of cylindrical cavity mechanics. Creation as the toe of a deep foundation element is advanced into the ground, expansion and contraction. So as a result, the static analysis methods for forecasting the geotechnical ultimate limit state of tapered deep foundation elements under axial loading have resorted to a variety of approaches to deal with the two distinct stages of KH-KO ratio development for deep foundation elements. Now, as I've discussed previously, most indirect, direct, and hybrid methods, such as those discussed in some detail earlier in this module segment, simply combine stages 1 and 2 into a single result that is valid for compressive loading. Also, as I've noted previously, there has been some theoretical work to separate the effects of stages 1 and 2, with the most notable being the work of Kodakara and Moore in Australia that was subsequently used by Professor Manandhar and his colleagues in Japan for coarse-grained soils only, as well as Professor El Nagara and his colleagues in Canada also for coarse-grained soil only. However, and unfortunately, as I pointed out earlier, the solution developed by Kodakara and Moore and adopted and adapted by others only calculates the taper benefit due to stage 2 post-installation axial loading and compression. And it leaves it up to the end user to estimate the taper benefit, if any, of the stage 1 installation. Also, as I've said previously, available evidence indicates that for taper deep foundation elements that are installed by driving or jacking, most of the taper benefit unfortunately derives from stage 1 installation, not stage 2 compressive loading. So the theoretical work of Kodakara and Moore, as well as the follow-on work by others, is really of little practical value. And believe me, I've spent quite a bit of time over the years to research Kodakara and Moore's work, as well as the work by Manandhar and El Nagar and their colleagues. So in this regard, it's relevant to note that the one deep foundation element case history that Kodakara and Moore used to quote-unquote validate their theoretical work was a relatively short tapered board pile or drilled shaft for which no taper benefit during stage 1 would be expected. So I think enough said on that topic. Well, for the sake of completeness, it's worth mentioning that some researchers, Felinius being the most prominent by far, have chosen to take a more simplistic approach to dealing with taper deep foundation elements, using what I call a donut on a stick model, in which the shaft resistance due to wedging under post-installation axial compressive loading is modeled as the sum of two parts. One is a shaft resistance due to sliding for a fictitious constant diameter stick approximation of a portion of the actual taper deep foundation element, plus the toe resistance due to end bearing for a fictitious projected bearing area, what I call the donut, that is also approximates a portion of the actual taper deep foundation element. So this donut, if you will, is just a downward projection of area of the actual taper deep foundation element. Now, this model may be visually and intuitively pleasing. However, it doesn't even remotely replicate the actual cylindrical cavity mechanics that occurs with taper deep foundation elements that results in shaft resistance due to wedging. More problematic, I feel, is that there's no known published research to support the use of this donut in a stick model as being even an acceptable approximation of reality. Look, I'll be the first one to say that there's nothing wrong with using simple models to represent something that's more complex. But the problem is, if you're going to propose and use a simple model, that it's incumbent upon you as a researcher to show that this simple model does approximate the real thing. And I've never been able to find any published work by Fellinius to show that his donut on a stick model approximates the behavior in actual deep foundation element. And my own personal research into this that I've documented in other publications is that this does a very poor job. This donut in a stick does a poor job of replicating actual taper deep foundation element behavior, at least for taper driven piles. The final comment I want to make on the topic of static analysis analytical methods concerns the depth-wise distribution of taper benefit as defined by the KH-KO ratio in a given application. Now, historically and to date, this has typically been assumed to be constant. This KH-KO ratio is constant both for simplicity as well as due to the lack of evidence to the contrary. However, if you think about it, it's clear that under both stage 1 installation as well as stage 2 post-installation axial loading, that the relative amount of cylindrical cavity expansion that occurs at a given depth in the ground as a taper deep foundation element is driven in stage 1 and displaces vertically under applied loading in stage 2, that this relative displacement of the cavity is non-uniform. So the increase in the KH-KO ratio is possibly non-uniform as well. And this is clearly a topic that merits further research. Well, I'd like to close out this Phase 1 module with a denouement that will use some case history results to support the wide variety of things that I've discussed in this module. Although the overall goal of this presentation is to promote the use of the geotechnical serviceability state displacements as the primary metric for the analysis and design of deep foundation elements subjected to axial loading, quantification of the geotechnical ultimate limit state or geotechnical failure will still remain an essential part of the deep foundation element design process, both during and after the transition to focusing on geotechnical serviceability. Since the 1950s, this quantification of the geotechnical ultimate limit state has always had two complementary components: forecasting the ultimate limit state prior to deep foundation installation, primarily using what we call static analysis methodologies that are based on an assumed embedded depth of a deep foundation element. And then this is followed up by field verification of the ultimate limit state, either during or after deep foundation element installation, using a variety of static and dynamic methodologies. Now, as discussed in this presentation module, each of these components, but especially the field verification using traditional static load testing, requires substantial improvement over the status quo that I feel has been allowed to slip into mediocrity or worse in recent decades, due in large part to commoditization of many aspects of the field verification component in particular. This improvement to the status quo also needs to include consideration of technical subjects such as residual loads from installation that have been known for decades now but are either not dealt with properly or simply ignored completely. And as I said before, facts do not cease to exist because they are ignored. Ignoring facts will not make them go away, will not make them not have an effect. Now, specific topical areas where improvement to the current state of practice are mission critical, in my opinion, include the following. The concept of an equilibrium plane that until recently was called the neutral plane, where negative and positive shaft friction plus toe resistance are vertical force equilibrium, needs to become a basic part of foundation engineering education, research, and practice for deep foundation elements, as it is an indispensable tool for the proper understanding and design-related treatment of both residual loads from installation and post-installation global settlement. A corollary is that the post-installation equilibrium plane is a dynamic feature in that it is temporarily varying as a result of variations in externally applied loads, as well as changes in magnitude of global settlement. The fact that residual loads exist to varying extents in all types of deep foundation elements after installation needs to be universally acknowledged, and ways to estimate these residual loads on a routine basis need to be developed for use during the design phase of a project. As I showed you, there were some efforts going back to the 1980s where people were trying to develop these methods, but that development just kind of fizzled out. We need to resurrect it and advance it. A corollary is that techniques need to be developed to correct all static and dynamic methodologies that are used for field verification of the geotechnical ultimate limit state for residual loads. The negative shaft friction and downdrag that develop as the result of post-installation global settlement need to be dealt with properly as a geotechnical serviceability, that is, deep foundation element settlement issue, plus structural ultimate limit state issue, as the geotechnical ultimate limit state of a deep foundation element is never affected by global settlement. As I've noted in this presentation, some people appear to have gotten this message, but it is not universal. The still evolving technology of energy piles needs to be recognized by a broader segment of stakeholders involved with deep foundation elements, so that the thermomechanical effects of energy pile installations are properly dealt with and integrated with the geostructural effects of residual loads from installation and post-installation global settlements. Long-term observation of actual instrumented energy pile applications are especially needed in order to refine current design methods and especially to see if ratcheting behavior, that is the long-term buildup of displacements and forces in one direction along an energy pile longitudinal axis along the energy pile shaft, needs to be a design issue. This, to me, as I've learned about energy piles, strikes me as the real big unknown. Is there, during the design life of an energy pile, is there this ratcheting behavior that builds up forces and displacements in one direction of the pile or the other? The way in which static load tests are performed and interpreted also needs to be changed completely. Load should only be measured using calibrated electronic load cells and mensuration methodologies, preferably automated, for measuring deep foundation element head settlement that are not affected by deep foundation element settlement need to be adopted. I think the days of reading dial gauges and tension wires on mirrors really needs to be retired. There is at best only ever one true ultimate geotechnical load for a deep foundation element. Consequently, the use of settlement-based criteria such as the Davison method in the United States or the 10% settlement criteria in Europe to define the geotechnical ultimate limit state should be abandoned once and for all, as they are arbitrary and subject to interpretation error due to the effects of residual loads on load settlement curves that are based solely on measured data. Load should be applied monotonically in equal increments with only minimal hold times and continued until several inches or tens of millimeters of settlement occurs at the head of the deep foundation element, at least in all soil conditions. I fully realize this is not realistic if you have a deep foundation element that is bearing on or in bedrock. But wherever possible, we need to extend the loads until we get a relatively substantial amount of settlement so that the true ultimate load can be reasonably determined. And of course, we should recognize that in some cases it will never max out. It may continue to increase at a very reduced rate. Whenever possible, instrumented load tests should be used in lieu of non-instrument load tests, and the results interpreted with due consideration of residual loads. And all of these points are summed up on these curves that I've shown you previously now a couple of times. And that is, there is only at best one true ultimate geotechnical resistance. And the surefire way to try to measure it, to get the residual loads out of the system, are to have settlements at the head of the deep foundation element of several inches, tens of millimeters. Now, eventually, all static analysis methodologies, whether indirect, direct, and hybrid, that are used in design practice and academic research, need to be recalibrated to reflect residual loads. Site characterization has always been the cornerstone of any geostructural investigation of any size and importance. And towards that end, greater use should be made on deep foundation projects of state-of-knowledge site characterization that is achievable nowadays with in situ testing methods, especially the pisocone and seismic pisocone. Now, for deep foundation elements, the pre-installation values of KO and the small strain shear modulus G max, or G naught if you prefer, strongly influence the geotechnical ultimate limit state as well as the serviceability limit state, so are essential mission critical interpretive results from the post-processing of site characterization field data. The importance of KO in particular is the underlying reason for using the KH-KO and beta over KO ratios in static analysis methods for calculating shaft resistance, instead of the usual traditional KH and beta as we have done historically. KO also affects toe resistance, as horizontal, not vertical effective stresses in the soil control bearing capacity at a deep foundation element toe. And to put some of these thoughts together, here's a typical subsurface profile from Kennedy Airport from cone penetrometers. This is in the so-called central terminal area. And again, at Kennedy Airport, we have Pleistocene strata, two sand strata, the Belmore and Merrick formations. We have a Holocene organic stratum, and we have a Holocene organic sand fill, hydraulic sand fill. And this is a plot of yield stress ratio, what we used to call over-consolidation ratio. And this is a plot of KO. And this is from one particular pisocone, but I have looked at dozens and dozens of pisocones and seismic pisocones that have been taken at Kennedy Airport over the last several decades. And these results are very representative. They're very, very, very typical. So as we know, the unit shaft resistance of a deep foundation element is proportional to K sub H, the horizontal, dimensionless horizontal earth pressure coefficient acting along the shaft after installation. And this is true whether the deep foundation element is constant diameter or tapered. So the shaft resistance is proportional KH times the vertical effective overburden stress. And as I've shown you now in this presentation, this is better reflected in the KH-KO ratio. And this reflects all of the collective results of two stages. Stage 1, the installation of the deep foundation element, and stage 2, the axial loading, which could either be compressive or tensile or uplift. So the KH-KO ratio represents the net effects of installing and loading the deep foundation element, and of course KO is the coefficient of earth pressure, lateral earth pressure prior to installation. So this is a really very significant outcome of decades of research that started with Professor Kolhowie and his colleagues at Cornell, that really for a deep foundation element, the final K sub H builds on the K sub O that exists in the ground prior to installation. That's a very powerful conclusion. All right, so as I said, this is post-installation, this is pre-installation, and this reflects all the installation issues. Now, historically, for the first several decades at Kennedy Airport, just about all of the structures and elevated roadways and major light poles were supported on driven timber piles, and these piles tended to fetch up, as we say, within the top, maybe 5 to 10 feet, 1.5 to 3 meters of the upper glacial aquifer, the Pleistocene bearing stratum. So the piles were relatively short, and a good part of why these tended to achieve their desired resistance was, notice the elevated values of KO here. I think this played a very significant role in the ability to get the desired pile resistance from relatively shallow embedment. And you see this high value of KO, these high values of KO come from the fact that the yield stress ratio in this upper part of the Pleistocene sands is quite high, whereas with depth you tend to get more normal consolidation. And you see why now we divide the upper glacial aquifer into two strata. There are distinctive characteristics between the Belmore and the Merrick, and these show up very nicely, by the way, in interpreted cone penetrometer soundings. You see the difference in yield stress ratio as well as KO. So I'm going to show you two typical results using these two symbols, a red square and an orange circle. And this is a plot that shows you measured axial load. Here's kips, kilonewtons are down here. These tests were originally performed in imperial units, so I'm showing imperial units primary. And here's a settlement at the head of the piles, inches and millimeters over here. And fortunately, these piles were loaded to very large, relatively large settlements, so we could get a sense of, we could remove all the effects of residual load and get a sense of the true geotechnical ultimate resistance. And if you look at both the red square, which is the shallower of the two piles, and the orange circle, which is the slightly deeper of the two piles, the interesting thing is, notice that even after the effects of residual load have been overcome, these don't exhibit a plunging failure. So certainly Fellinius's point that he's made many, many times now over the last several decades, that defining a single unique value of the ultimate geotechnical resistance of deep foundation can be problematic. These are certainly exhibiting that trend. You know, clearly we've maxed out all the shaft resistance, but it's also clear that even after the effects of residual load have been removed, these piles are still picking up some additional resistance with further embedment in both of these cases. And this again points out the difficulty in trying to define a single value of ultimate geotechnical resistance. In many cases, we will continue to see a slight increase with increasing penetration of the pile in the ground. And to put things in context, at the time these piles were driven, this was in the early 1970s, the sought after usable resistance or allowable capacity, if you will, of timber piles at Kennedy airports was 30 tons. These are what were called colloquially 30-ton piles, which means with a safety factor of 2, they would have a allowable load of 60 kips or ultimate load of 120 kips. And you can see down here that would mean in terms of SI metric units, an ultimate resistance of about 540 kilonewtons, and about half of that, 270, for the working load. So you see this pile, the deeper pile, certainly met that criterion without a problem. This pile is a little bit shy of it, although I suspect if we kept pushing it in the ground a bit more, it might eventually get there. Now, at the time in the early 70s, one of the things that was explored with some pile load test programs, and I can say this firsthand because I was an entry-level engineer and I was the one out in the field doing the pile load tests, and then following up with analyses in the office afterward. One of the things that was being investigated in the early 70s was staying with timber piles, but seeing if we could go to what were called then 40-ton piles. And this would be an ultimate geotechnical resistance of 160 kips, so not quite 720 kilonewtons, which would be an allowable load of 80 kips, or about 360 kilonewtons. And the pile was driven somewhat deeper for that. You can see the yellow triangle here, and here was the load test on that pile. The load test was terminated at about 20 millimeters, about a little bit more than 3/4 of an inch of settlement, for the only reason is that the load test frame ran out of capacity. And I can say that with great certainty simply for the reason I was out there that night when this load test was being done. This pile had much more geotechnical resistance than had been estimated, and this was a typical dead weight static load test. And I can remember, to the surprise of all, even though this was over 50 years ago, I can still remember it as if it happened last night. To the surprise of all involved, load was being applied, and literally the reaction beam and the dead loads were being jacked off their timber supports. Simply ran out of capacity to apply load in the system, which is why the test had to be terminated. And clearly, this test had not reached its geotechnical ultimate resistance. I mean, this would have been a satisfactory, quote-unquote, 40-ton timber pile had it actually been used as a production pile. Now, ultimately, as it turned out, timber piles were not used for future construction at Kennedy Airport. There are other considerations I will talk about in the Phase 2 module, which is coming up shortly. But the main thing I want you to get from these plots here are the high values of KO in the upper part of the Pleistocene bearing stratum. I think go a long way for why piles were able to fetch up, as we say, with relatively modest embedment, 5 to 10 feet, 1.5 to 3 meter embedment into the Pleistocene sands. These high KO values, again, that was a starting point for the unit shaft resistance. So combine that with the natural taper of timber piles, and there was quite substantial shaft resistance, as well as relatively significant toe resistance. The timber piles that were used structurally at Kennedy Airport typically had a toe diameter of about 8 inches, so roughly 200 millimeters, just to put some numbers on it. So the point I'm trying to show you here is that KO plays a significant role in the geotechnical resistance of deep foundation elements. Well, that concludes the Phase 1 presentation module, as well as Part 1 of this presentation. I thank you very much for your time and effort to view this Part 1 of this presentation, and I invite you to continue on to view Part 2. In Part 2, I will show you how easy it is to design deep foundation elements for settlement and the serviceability limit state. Again, thank you for your time in viewing up to this point.